Section 1 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. CORBIN. Digging with Dynamite. Most people are afraid of the word explosion and shudder with apprehension at the mention of dynamite. The latter particularly conjures up visions of anarchists, bombs, and all manner of wickedness. And yet the time seems to be coming when every farmer will regard explosives of the general type known to the public as dynamite as among his most trusty implements. It is so already in some places. In the United States, explosives have been used for years, owing to the exertions of the DuPont Powder Company, while Messrs. Curtis and Harvey and Messrs. Nobels, the great explosive manufacturers, are busy introducing them in Great Britain. It will perhaps be interesting first of all to see what this terror-striking compound is. One essential feature is the harmless gas which constitutes the bulk of our atmosphere, nitrogen. Ordinarily one of the most lazy, inactive, inert of substances, this gas will, under certain circumstances, enter into combination with others, and when it does so, it becomes in some cases the very reverse of its usual peaceful, lethargic self. It's as if it entered reluctantly into these compounds, and so introduced an element of instability into them. It's like a dissatisfied partner in a business, ready to break up the whole combination on very slight provocation. And it must be remembered that an explosive is simply some chemical compound which can change suddenly into something else of much larger volume. Water, when boiled, increases to about 1,600 times its own volume of steam. And if it were possible to bring about the change suddenly, water would be a fairly powerful explosive. Coal burned in a fire changes, with oxygen from the atmosphere, into carbonic acid gas, and the volume of that latter which is so produced is much more than that of the combined volumes of the oxygen and coal. When the burning takes place in a grate or furnace, we see nothing at all like an explosion, for the simple reason that the change takes place gradually. That is necessarily so, since the coal and oxygen are only in contact at the surface of the former. But if, however, we grind the coal to a very fine powder and mix it well with air, then each fine particle is in contact with oxygen and can burn instantly. Hence, coal dust in air is an explosive. It used to be thought that colliery accidents were due entirely to the explosion of methane, a gas which is given off by the coal. But it has of recent years dawned upon people that it is the coal dust in the mine which really does the damage. The explosion of methane stirs up the dust, which then explodes. The former is comparatively harmless, but it acts as the trigger or detonator which lets loose the force pent up in the innocent-looking coal dust. Hence the greatest efforts in modern collieries are bent towards ridding the workings of dust, or else damping it, or in some other way preventing it from being stirred up into the dangerous state. So the essential feature of any explosive is oxygen and something which will burn with it. If it be a solid or liquid, the oxygen must be a part of the combination or mixture, for it cannot get air from the surrounding atmosphere quickly enough to explode. And moreover, it is generally necessary that explosives should work in a confined space, away from all contact with air. So oxygen, of necessity, must be an integral part of the stuff itself. But when oxygen combines with anything, it usually clings rather tenaciously to its place in the compound and is not easily disturbed quickly. That is where the nitrogen seems to find its part. It supplies the disturbing element in what would otherwise be a harmonious combination, so that the oxygen and the burnable substances readily split up and form a new combination with the nitrogen left out. Of all the harmless things in the world, one would think that the sweet, sticky fluid, glycerin, which most of us have used at one time or another to lubricate a sore throat, was the most harmless. As it stands in its bottle upon the domestic medicine shelf, who would suspect that it is the basis of such a thing as dynamite? Such is the case, however, for glycerin, on being brought into contact with a mixture of sulfuric and nitric acids, gives birth to nitroglycerin, an explosive of such sensitivity, of such a furious, violent nature, that it is never allowed to remain long in its primitive condition, but it is as quickly as possible changed into something less excitable. Glycerin is one of those organic compounds which is obtained from once living matter. Arising as a byproduct in the manufacture of soap, it consists, as do many of the organic substances, of carbon and hydrogen, the atoms of which are peculiarly arranged to form the glycerin molecule. To this the nitric acid adds oxygen and nitrogen, the sulfuric acid simply standing by, as it were, and removing the surplus water which arises during the process. So while glycerin is carbon and hydrogen, nitroglycerin is carbon, hydrogen, nitrogen, and oxygen. In this state they form a compact liquid which occupies little space. The least thing upsets them, however. The carbon combines with oxygen into carbon dioxide, commonly called carbonic acid gas. The hydrogen and some more oxygen form steam, while the nitrogen is left out in the cold, so to speak, and the total volume of the gases so produced is about 6,000 times that of the original liquid. It is easy to see that a substance which is liable suddenly to increase its volume by 6,000 times is an explosive of no mean order. But the fact that it is liable to make this change on a comparatively slight increase in temperature or after a concussion makes it too dangerous for practical use. It needs to be tamed down somewhat. Well, this was first done by the famous Nobel, who mixed it with a fine earth known as kieselguhr, whereby its sensitiveness was much decreased. This mixture is dynamite. It will be seen that the function of the earth is simply to act as an absorbent of the liquid nitroglycerin, and several other things can be used for the same purpose. Moreover, there are now many explosives of the dynamite nature, but differing from it in having an active instead of a passive absorbent, so that the decrease in sensitivity is accompanied by an increase in strength. For example, gelignite, which is being used for agricultural purposes in Great Britain, consists of nitroglycerin mixed with nitrocotton, wood meal, and saltpeter. The wood meal acts as the absorbent instead of the kieselguhr, while the nitrocotton is another kind of explosive, and the saltpeter, one of the ingredients in the old gunpowder, provides the necessary oxygen for burning up the wood meal. Nitrocotton is made in much the same way as nitroglycerin, except that cotton takes the place of the glycerin. Cotton is almost pure cellulose, another organic substance, like glycerin insomuch as it is composed of carbon and hydrogen, but unlike it, containing also oxygen. Treated with the nitric acid, it also forms a combination of carbon, hydrogen, oxygen, and nitrogen, which is called nitrocotton, nitrocellulose, or gun cotton. It may be asked, why, if these two substances are thus similar, need they be mixed? Well, the answer is that although alike to a certain degree, they are not exactly the same, and the modern manufacturer of explosives, in his strife after perfection, finds that for certain purposes one is the best, and for others another, while for others again a combination may excel any single one. For some work, another kind of explosive altogether is to be preferred. This is based upon chlorate of potash, a compound very rich in oxygen, which it is prepared to give up readily to burn any other suitable element which may be at hand. A well-known explosive of this class is that known as shedite, since it was first made at a factory at Shed in Savoy. For the sake of simplicity, however, I propose in the following descriptions to refer to all these explosives under the common term dynamite, since that will probably convey to the general public an idea of their nature better than any other term or terms which I could choose. So now we come to the great question: how can the modern farmer benefit by the use of high explosives such as these? The answer is in many ways. Let us take the most obvious one first. A farmer has been plowing his land and growing his crops upon it for years. Perchance his forefathers have been doing the same for generations. Every year for centuries possibly, a hard steel plowshare has gone over that ground, turning over and over the topsoil to a depth of 6 to 8 inches. Each season the plants, whatever they may be, grow mainly in that top layer. They take the goodness or nourishment out of it and eventually becomes more or less sterile. By properly rotating his crops, he mitigates this to a certain extent. In addition to which he restores to the land some of its old nitrogenous constituents by the addition of manure. Yet do what he will, this thin top layer is bound to become exhausted, and all the while a few inches lower down there is almost virgin soil, which has scarcely been disturbed since the creation of the world. Nay, more, that virgin soil, with all its plant food still in it, is not only doing little for its owner, it is positively doing him harm. For every time his plow goes over it, it tends to ram it down flat. Every time a man walks over it, the result is the same. Every horse that passes, everything that happens or has happened for centuries in that field, tends to make that soil just below the reach of the plowshare a hard, impervious mass, through which only the roots of the most strongly growing plants can find a way, and which tends to make the soil above it wet in wet weather and dry in dry weather. Thus roots have to spread sideways instead of downwards, or growing downwards with difficulty. Each plant has to expend vital energy in forcing its roots through the hard ground, which it might better employ in producing flowers or fruits. And there is no natural storage of water. A shower drenches the ground. In time it dries through evaporation into the air, and then when the drought comes, all is as arid as the Sahara. That hard subsoil is known by the term hardpan, and as we have seen, it is produced more or less by all that goes on in the field. Even worse is the case, a very frequent one too, wherein there is a natural stratum of clay or equally dense waterproof material lying a few feet down. Beyond the reach of any plow, this hard stratum can be broken up by the use of dynamite. The usual method is to drive holes in the ground about 15 to 20 feet apart and about 3 or 4 feet deep, right into the heart of the hard layer. At the bottom of each hole is placed a cartridge of dynamite with a fuse and a detonator. This latter is a small tube containing a small quantity of explosive which, unlike the dynamite, can be easily fired and initiates the detonation of the cartridge. When these miniature earthquakes have taken place all over a field, a very different state of things prevails. The hardpan has been broken. The explosive used for such purpose has a sudden shattering power, whereby it pulverizes the ground in its vicinity rather than making a great upheaval at the surface. The sudden shock makes cracks and fissures in all directions through which roots can easily make their way. Moreover, it permits air to find an entrance, thereby aerating the soil in such a way as to increase its fertility. The heat, or else the chemical products of the explosion, seem to destroy the fungus germs in the ground. And finally, a natural storage of water is set up. Heavy rain, instead of drenching the upper soil, simply moistens it nicely, while the surplus water descends into the newly disturbed layers, there to remain until the roots pump it up in time of drought. It is stated that an acre of hay pumps up out of the soil 500 tons of water per annum. and so it is easy to see what an important feature this natural water storage is. Farmers say that their crops have doubled in value after thus dynamiting the subsoil. This operation has been spoken of as a substitute for plowing, but that may be put down to journalistic license, for while it truly conveys the general idea, it is hardly correct. The ordinary plow turns over about 8 inches. The special subsoil plow reaches down to about 18 inches. But the dynamite method loosens the ground to a depth of 6 or 7 feet. Corn roots, if given a chance, will go downwards from 4 to 8 feet. Potatoes go down 3 feet. Hops 8 to 18 feet, and vines 20 feet. So it is easy to see how restricted the plants are when their natural rooting instincts are restrained by a hard layer at a depth of 18 inches or so. The holes are made by means of a bar or drill. A great deal depends, of course, upon the hardness of the soil. Sometimes a steel bar has to be driven in by a sledgehammer. At others, a pointed bar can be pushed down by hand. In some cases, it will be found that the best tool to employ is a dirt auger, a tool like a carpenter's auger, which on being turned round and round bores its way into the earth. However it may be done, 1 or more cartridges of dynamite are lowered into the finished hole, one of them being fitted with the necessary detonator and fuse. Then a little loose earth or sand is dropped into the hole until it is filled to a depth of 6 inches or so above the uppermost cartridge. Above that, it is quite safe to fill the hole with earth, ramming it in with a wooden rammer. This is called tamping, and it is necessary in order to prevent the force of the explosion being wasted in simply blowing up the hole. What is wanted is that the explosion shall take place within an enclosed chamber so that its effect may be felt equally in all directions. The holes are generally about 1.5 inches or 1.75 inches in diameter. There are 2 ways of firing the charges. One is by means of fuses. The detonator is fastened to one cartridge, and a length of fuse is attached to the detonator, which, passing up the hole, terminates above the ground. The fuse is a tube of cotton filled with gunpowder, and it burns at the rate of about 2 feet a minute. And thus if 3 feet of fuse be used, the man who lights it has 1.5 minutes in which to find a place of safety from falling stones. The other way is by electricity. In this case, an electric fuse is attached to the cartridge, and 2 wires are led up the hole. These are connected to an electrical machine, which causes a current to pass down into the fuse, where, by heating a fine platinum wire, it fires the detonating material with which it is packed. This detonating material, in turn, fires the dynamite. The advantage of the electrical method is that 20 or 30 holes being simultaneously connected to the same machine can all be fired at once. And now let us think of another kind of farming in which fruit trees are concerned. With a large tree, the need of plenty of underground space for its roots would seem to be more important even than that in the case of annual plants like wheat. And yet we know very well that the usual procedure is to dig a small hole just about big enough to accommodate the roots of the sapling when it is planted, while the ground all round is left undisturbed. The assumption is that the tree will in time be able to push its roots through anything which is not actually solid rock. So much is this the case that one authority has thought fit to warn tree growers in this picturesque fashion. "When planting a tree," he says, "forget what it is you're doing and think that you're about to bury the biggest horse you know." How many people, when planting any tree, dig a hole big enough to bury a horse? It is fairly safe to reply, only those who do it by dynamite. The method of working is to bore a hole nearly as deep as the hole you want to blast. At the bottom, place a powerful charge, far stronger than you would use for subsoiling, as just described. That will not only blow a hole big enough for you to put your tree in, but it will loosen the ground all around the hole for yards. The main debris from the hole will fall back into it, but that will not matter much, since being all loose, it is an easy matter to remove as much as is necessary to plant the young tree. The advantages are the same as those enumerated in the previous case, namely, the loosened ground gives more scope for the roots. Apple tree roots want 20 feet or so. The ground holds moisture better, and the explosion kills the fungus germs. In addition to these, there is the advantage that to blast a hole like this is cheaper than digging it. And that the advantages are not merely theoretical is shown by the fact that trees so planted actually do grow stronger, bigger, and quicker than precisely similar ones under the same conditions, but set in the ordinary way with a spade. And not only do new trees thus benefit, old trees can be helped by dynamite. Many an existing orchard has been improved by exploding dynamite at intervals between the rows of trees. Care has to be taken to see that the disturbance is not so violent or so close as to damage the trees. But that can be easily arranged, and then the result is that the soil all around the trees is loosened. The roots are given more freedom, and the water-storing properties of the ground are greatly improved. Again, how often a farmer is troubled with a pond or a patch of marshy ground right in the midst of his fields. It is of no use, and simply serves to make the field in which it occurs more difficult to plow and to cultivate, besides being so much good land wasted. Now, the reason for the existence of that pond or marsh is that underneath the surface there is an impervious layer in which, as in a basin, the water can collect. Make a hole in that, and it will no more hold water than a cracked jug will. And to make that hole with dynamite is the easiest thing in the world. If the pond be merely a collection of water which occurs in wet weather, but which dries up quickly, there simply needs to be drilled a deep hole and a fairly strong explosion caused at the bottom of it. How deep the hole must be depends upon the formation of the earth at that point, and how low down is the stratum which, being waterproof, causes the water to remain. It is that, of course, which must be broken through, and so the explosion must be caused at a point near the underside of that layer. With a little experience, the operator can judge the position by the feel of the tool with which he makes the hole. If the pond is permanent but shallow, men can wade to about the center, there to drill a hole and fire a shot. If it be permanent and deep, then the work must be done from a raft, which, however, can be easily constructed for the purpose. Once broken through, the water will quickly pass away below the impervious stratum, and useless land will become valuable once more. The same may be done on a larger scale by blasting ditches with dynamite. This is in many cases much cheaper than digging them. A row of holes is put down, or even 2 or 3 rows, according to the width of the proposed ditch. In depth they are made a little less than the depth of the ditch that is to be, and for a reason which will be apparent, they are put very close together, say 3 feet or so apart. Preparations may thus be made for blasting a ditch hundreds of feet long, and then all are fired together. The earth is thrown up by a mighty upheaval, a ditch being produced of remarkable regularity considering the means by which it is made. The sides, of course, takes a nice slope. The debris is thrown away on both sides and spread to a considerable distance, so that, given favorable conditions and a well-arranged explosion, there is constructed a finished ditch which hardly needs touching with spade or other tool. It not being feasible to fire a lot of holes electrically, the limit being about 30, the simultaneous explosion of perhaps hundreds has to be brought about in some other manner, and usually it is accomplished by the simple device of putting the holes fairly near together and firing one with a fuse. The commotion set up by this one causes the nearest ones to go off, they in turn detonating those farther on, with the result that explosion follows explosion all along the line so rapidly as to be almost instantaneous. A farmer who is troubled by a winding stream passing through his land, cutting it up into awkward shapes, can straighten it by blasting a ditch across a loop in the manner just described. In the case of low-lying land, however, ditches are obviously no use, since water would not flow away along them. In that case, the principle suggested just now for dealing with an inconvenient pond can sometimes be used. Or if the subsoil be blasted through at several points, it is very likely that water will find a way downwards by some means or other. And the list of possible uses is by no means exhausted yet. A man opening up virgin land often finds old tree stumps his greatest bother. He can dig round them and then pull them out with a team of horses, but by far the simpler way is with a few well-placed dynamite cartridges, for they not only throw up the stump for him, but they break it up, shake the earth from it, and leave it ready for him to cart away or to burn. Boulders, too, can be blown to pieces far more easily than one would think. The charges may be put underneath them, as with the tree stumps, but in many cases that is not necessary, all that is needed being some dynamite laid upon the top of the rock and covered with a heap of clay. So sudden is the action of the explosive that its shock will break up the stone underneath it. And yet another way, perhaps the most effective of all, is to drill a hole into the stone and fire a charge inside it. It behooves the onlooker then to keep away, for the fragments may be thrown 300 or 400 feet, a fair proof that the stone will be very thoroughly demolished. Even in the digging of wells, explosives may be useful. In that case the holes are made in a circle, and they slant downwards and inwards, so that their lower ends tend to meet. The result of simultaneously exploding the charges in these holes is to cut out a conical hole a little larger in size than the ring and a little deeper than the point at which the explosion took place. The bottom of that hole can be leveled a little and the operation repeated, and so stage by stage the well will proceed to grow downwards. The thought that naturally occurs to one is this: all the operations described may be very well, the cost may be very low, and the effects good. But are they sufficient to compensate for the risks necessarily dependent upon the use of explosives? The doubt implied is that question, natural though it be, is based upon prejudice, with which we are all more or less afflicted. The art of making these explosive substances has been brought to such a pitch that with reasonable care there is no risk whatever. The greatest possible care is used in the factory to see that all explosives sent out are what they are meant to be, and that they can therefore be relied upon to behave according to program and not to play any tricks. That is the first step, and what with competition between makers, government inspection, and searching inquiry into the slightest accident, and the desire of each maker to keep up the credit of his name, it is safe to say that modern explosives may be relied upon to do their duty faithfully. The second step in the process of securing safety is that the powerful explosive, the one that does the work, is made very insensitive, so that it is really quite hard to explode it. With reasonable care, then, it will never go off by accident. On the other hand, the sensitive material which is easy to let off is in very small quantities, so small that an accident with it would not, again with reasonable precautions, be a serious matter. Fuse, too, is very reliable nowadays. The man who lights the fuse may be absolutely sure that he will have that time to get to a place of safety, which corresponds to the length of fuse which he employs. With electrical firing, too, It is quite easy to arrange that the final electrical connection shall not be made until all are at a safe distance, so that a premature explosion is impossible. In many of the cases described, the shock takes place almost entirely within the earth, and there is very little debris thrown about. Indeed, the only danger which is to be feared with these operations is about on a par with that which every farmhand runs from the kick of a horse. Any careful, trustworthy man could be quite safely taught to do this work, and with the assistance of a laborer he could do all that is necessary. Given a fair amount of intelligence, too, he would take but little teaching. Altogether, there is no doubt that the use of explosives is going to have a marked effect upon farming operations in the near future. End of Chapter 1.
Section 2 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Measuring electricity. There are many people whose acquaintance with electricity consists mainly in paying the electric light bill. To such, the instruments whereby electricity is measured will make a specially interesting appeal. Current is sold in Great Britain at so much per Board of Trade unit. To state what that is needs a preliminary explanation of the other units employed in connection with electric currents. The public electricity supply in any district is announced to be so many volts. It may be 100, 200, or perhaps 230, but whatever it be, it is always so many volts. Then the electrician speaks lightly of numbers of amperes. He may even talk of the number of watts used by the lamps, while occasionally the word ohm will leak out. Among these terms, the general reader is apt to become completely fog-bound. But really they are quite simple if once understood, and, as we shall see in a moment, there are some very remarkable instruments for measuring them, some of which exhibit a delicacy truly astonishing. It is well at the outset to try and divest ourselves of the idea that there is anything mysterious or occult about electricity. It is quite true that there are many things about it very little understood even by the most learned, but for ordinary practical purposes it may be regarded as a fluid, which flows along a wire just as water flows along a pipe. The wire is, electrically speaking, a hole through the air, or other non-conducting substance with which it is surrounded, a water pipe being a hole through a bar of iron. So the copper core of an electrical wire is, so far as the current is concerned, but a hole through the center of a tube of silk, cotton, rubber, or whatever it be. Electricity can flow through certain solids just as water can flow through empty space. Water will not flow through a pipe unless a pressure be applied to it somewhere. In a pipe, the ends of which are at the same level, water will lie inert and motionless. Lower one end, however, and the pressure produced by gravity, in other words, the weight of the water, will cause it to move. In like manner, pressure produced by the action of a pump will make water flow. On the other hand, when it moves, it encounters resistance through the water rubbing against the walls of the pipe. Similarly, an electrical pressure is necessary before a current of electricity will flow, and every conductor offers more or less resistance to the flow of current, thus opposing the action of the pressure. Before current will flow through your domestic glow lamps and cause them to give light, there must be a pressure at work, and that pressure is described as so many volts. A battery is really a little automatic electrical pump for producing an electrical pressure. And the volt, which is a legal measure, just as much as a pound or a yard, is a certain fraction of the pressure produced by a certain battery known as Clark's cell. It is not necessary here to say exactly what that fraction is, but it will give a general idea to state that the ordinary Leclanche or dry cell, such as is used for electric bells, produces a pressure of about 1.5 volts. Thus, we see the volt is the electrical counterpart of the term pound per square inch, which is used in the case of water pressure. A flow of water is measured in gallons per minute. An electrical current is measured in coulombs per second. Thus, the coulomb is the electrical counterpart of the gallon. But in this particular, we differ slightly in our methods of talking of water and electricity. Gallons per minute or per hour is the invariable term in the former case, but in the latter, we do not speak of coulombs per second, although that is what we mean, for we have a special name for 1 coulomb per second, and that name is ampere. 1 ampere is 1 coulomb per second. 2 amperes are 2 coulombs per second, and so on. There is no recognized term to denote the resistance which a water pipe offers to the passage of water through it. But in the similar case with electricity, there is a term specially invented for the purpose, the ohm. Legally, it is the resistance of a column of mercury of a certain size and weight. A rough idea of it is given by the fact that a copper wire, 1/16 of an inch thick and 400 feet long, has a resistance of about 1 ohm. The 3 units, the volt, ampere, and ohm, are so related that a pressure of 1 volt acting upon a circuit with a resistance of 1 ohm will produce a current of 1 ampere. A current can do work. When it lights or heats your room or drives a tramcar, it is doing work. And the rate at which a current does work is found by multiplying together the number of volts and the number of amperes. The result is in still another unit, the watt, and 1,000 watts is a kilowatt. Finally, to crown the whole story, a kilowatt for 1 hour is a Board of Trade unit. So, for every unit which you pay for in the quarterly bill, you have had a current equal to 1,000 watts for an hour. To give a concrete example, if the pressure of your supply is 200 volts, and you take a current of 5 amperes for an hour, you will have consumed 1 BTU. Perhaps it will give added clearness to this explanation to tabulate the terms as follows. Volt equals the unit of pressure, analogous to pounds per square inch in the case of water. Coulomb equals the measure of quantity, analogous to the gallon. Ampere, the measure of the strength of a current, meaning 1 coulomb per second. Watt equals the unit denoting the power for work of any current. It is the result of multiplying together volts and amperes. Kilowatt is 1,000 watts, and a Board of Trade unit, a current of 1 kilowatt flowing for 1 hour. In practice, the measurements are generally made by means of the connection between electricity and magnetism. A current of electricity is a magnet. Whenever a current is flowing, it is surrounded by a region in which magnetism can be felt. This region is called the magnetic field, and the strength of the field varies with the strength, that is, the number of amperes in the current. If a wire carrying a current be wound up into a coil, it is evident that the magnetic field will be more intense than if the wire be straight, for it will be concentrated into a smaller area. Iron, with its peculiar magnetic properties, if placed in a magnetic field, seems to draw the magnetic forces towards itself, and consequently, if the wire be wound round a core of iron, the magnetism, due to the current, will be largely concentrated at the ends of the core. But the main principle remains. In any given magnet, the magnetic power exhibited will be in proportion to the current flowing. The switchboard at a generating station is always supplied with instruments called ammeters, an abbreviation for ampere meter, for the purpose of measuring the current passing out from the dynamos. Each of these consists of a coil of wire through which the current passes. In some, there is a piece of iron nearby, which is attracted more or less as the current varies, the iron being pulled back by a spring, and its movement against the tension of the spring being indicated by a pointer on a dial. In others, the coil itself is free to swing in the neighborhood of a powerful steel magnet. The interaction between the electromagnet or coil and the permanent magnet being such that they approach each other or recede from each other as the current varies. A pointer on a dial records the movements as before. In yet another kind, the permanent magnet gives way to a second coil, the current passing through both in succession, the result being very much the same, the two coils attracting each other more or less according to the current. Another kind of ammeter, known as a thermoammeter, works on quite a different principle. It consists of a piece of fine platinum wire which is arranged as a shunt, that is to say, a certain small but definite proportion of the current to be measured passes through it. Now, being fine, the current has considerable difficulty in forcing its way through this wire, and the energy so expended becomes turned into heat in the wire. It is indeed a mild form of what we see in the filament of an incandescent lamp, where the energy expended in forcing the current through makes the filament white hot. The same principle is at work when we rub out a pencil mark with India rubber, whereby the rubber becomes heated, as most of us have observed. The wire then is heated by the current passing through it and accordingly expands. The amount of expansion forming an indication of the current passing. The elongation of the wire is made to turn a pointer. A simple modification makes any of these instruments into a voltmeter. This instrument is intended to measure the force or pressure in the current as it leaves the dynamo. A short branch circuit is constructed, leading from the positive wire near the dynamo to the negative wire or to the earth, where the pressure is zero. In this circuit is placed the instrument, together with a coil made of a very long length of fine wire, so that it has a very great resistance. Very little current will flow through the branch circuit because of the high resistance of the coil, but what there is will be in exact proportion to the pressure. The voltmeter is therefore the same as the ammeter, except that its dial is marked for volts instead of for amperes, and it has to be provided with the resistance coil. Instruments of the ammeter type can also be used as ohmmeters. In this case, what is wanted is to test the resistance of a circuit, and it is done by applying a battery, the voltage of which is known, and seeing how much current flows. All the voltmeters and ohmmeters mentioned owe their method of working to what is known as Ohm's law. One of the greatest steps in the development of electrical science was taken when Dr. Ohm put forward the law which he had discovered, whereby pressure, current, and resistance are related. The reader will probably have noticed from what has already been said about the units of measurement, the volt, the ampere, and the ohm, that the current varies directly as the pressure and inversely as the resistance. That is the famous and important Ohm's law, and anyone who has once grasped that has gone a long way towards understanding many of the principal phenomena of electric currents. But the instruments so far referred to are of the big, clumsy type, suitable for measuring large currents and great pressures. They are like the great railway weighbridges, which weigh a whole truckload at a time, and are good enough if they are true to a quarter of a hundredweight. The instruments about to be described are more comparable with the delicate balance of the chemist, which can detect the added weight when a pencil mark is made upon a piece of paper. Indeed, beside them such a balance is quite crude and clumsy. They may be said to be the most delicate measuring instruments in existence. We will commence with the galvanometer. The simplest form of this is a needle like that of a mariner's compass, very delicately suspended by a thin fiber in the neighborhood of a coil of wire. The magnetic field produced by the current flowing in the wire tends to turn the needle, which movement is resisted by its natural tendency to point north and south. Thus the current only turns the needle a certain distance, which distance will be in proportion to its strength. The deflection of the needle, therefore, gives us a measure of the strength of the current. But such an instrument is not delicate enough for the most refined experiments, and the improved form generally used is due to that prince of inventors, the late Lord Kelvin. He originally devised it. It is interesting to note, not for laboratory experiments, but for practical use as a telegraph instrument in connection with the early Atlantic cables. Before describing it, it may sharpen the reader's interest to mention a wonderful experiment which was made by Varley, the famous electrician, on the first successful Atlantic cable. He formed a minute battery of a brass gun cap with a scrap of zinc and a single drop of acidulated water. This he connected up to the cable. Probably there is not one reader of this book but would have thought, if he had been present, that the man was mad. What conceivable good can come of connecting such a feeble source of electrical pressure to the 2,000 miles of wire spanning the great ocean? The very idea seems fantastic in the extreme. Yet that tiny battery was able to make its power felt even over that great distance, for the Thomson mirror galvanometer was there to detect it. 2,000 miles away, the galvanometer felt and was operated by the force generated in a battery about the size of one of the capital letters on this page. This wonderful instrument consisted of a magnet made of a small fragment of watch spring, suspended in a horizontal position by means of a thread of fine silk, close to the coil of fine wire. When current flowed through the coil, the magnetic field caused the watch spring magnet to swing around. But when the current ceased, the untwisting of the silk brought it back to its original position again. So far it seems to differ very little from the ordinary galvanometer previously mentioned, but the stroke of genius was in the method of reading it. With a small current, the movement of the magnet was too small to be observed by the unaided eye. So it was attached to a minute mirror made of one of those little circles of glass used for covering microscope slides, silvered on the back. The magnet was cemented to the back of this, yet both were so small that together their weight was supported by a single thread of cocoon silk. Light from a lamp was made to fall upon this mirror, thereby throwing a spot of light upon a distant screen. Thus the slightest movement of the magnet was magnified into a considerable movement of the spot of light. The beam of light from the mirror to the screen became, in fact, a long lever or pointer without weight and without friction. The task of watching the rocking to and fro of the spot of light was found to be too nerve-wracking for the telegraph operators, and so Lord Kelvin improved upon his galvanometer in two ways. He first of all managed to give it greater turning power, so that, activated by the same current, the new instrument would work much more strongly than the older one. Then he utilized this added power to move a pen, whereby the signals were recorded automatically on a piece of paper. The new instrument is known as the siphon recorder. The added power was obtained by turning the instrument inside out, as it were, making the coil the moving part and the permanent magnet the fixed part. This enabled him to employ a very powerful permanent magnet in place of the minute one made of watch spring. The interaction of the two magnets is the result of their combined strength, and that of the coil being limited by the strength of the minute current. The only way to increase the combined power of the two was to substitute a large powerful magnet for the small magnetized watch spring. This large magnet would of course have been too heavy to swing easily. Therefore, the positions had to be reversed. So now we have two types of galvanometer, both due originally to the invention of Lord Kelvin. For some purposes, the Thomson type, his name was Thomson before he became Lord Kelvin, are still used, but in a slightly elaborated form. Its sensitiveness is such that a current of a thousandth of a microampere will move the spot of light appreciably, and when one comes to consider that a microampere is a millionth part of an ampere, this is perfectly astounding. But there is a more wonderful story still to come of an instrument which can detect a millionth of a microampere, or 1/1,000,000th of a millionth of an ampere. It is not generally known that we are all possessors of an electric generator in the form of the human heart, but it is so, and Professor Einthoven of Leyden, wishing to investigate these currents from the heart, found himself in need of a galvanometer exceeding in sensitiveness anything then known. Even the tiny needles or coils with their minute mirrors have some weight, and so possess in an appreciable degree the property of inertia, in virtue of which they are loath to start movement, and having started are reluctant to stop. This inertia, it is easy to see, militates against the accurate recording of rapid variations in minute currents, so the energetic professor set about devising a new galvanometer which should answer his purpose. This is known as the string galvanometer. The main body of the instrument is a large, powerful electromagnet, in shape like a large pair of jaws nearly shut. Energized by a strong current, this magnet produces an exceedingly strong magnetic field in the small space between the teeth, as it were. In this space there is stretched a fine thread of quartz, which is almost perfectly elastic. It is a non-conductor, however, so it is covered with a fine coating of silver. Silver wire is sometimes used, but no way has yet been found of drawing any metallic wire so thin as the quartz fiber, which is sometimes as thin as 2/1000ths of a millimeter, or about a 12/1000th of an inch. 100 pages of this book make up a thickness of about an inch, so that one leaf is about a 50th of an inch. Consequently, the fiber in question could be multiplied 240 times before it became as stout as the paper on which these words are printed. The current to be measured is passed through the stretched fiber, and the interaction of the magnetic field by which the fiber is then surrounded with the magnetic field in which it is immersed causes it to be deflected to one side. Of course, the deflection is exceedingly small in amount, and as it is undesirable to hamper its movements by the weight of a mirror, no matter how small, Some other means of reading the instrument have to be devised. This is a microscope, which is fixed to one of the jaws, through a fine hole in which the movements of the fiber can be viewed. Or what is often better still, a picture of the wire can be projected through the microscope onto a screen, or onto a moving photographic plate or strip of photographic paper. In the latter case, a permanent record is made of the changes in the flowing current. An electric picture can thus be made of the working of a man's heart. He holds in his hands two metal handles, or is in some other way connected to the two ends of the fiber by wires, just as the handles of a shocking coil are connected to the ends of the coil. The faint currents caused by the beating of his heart are thus set down in the form of a wavy line. Such a diagram is called a cardiogram, and it seems that each of us has a particular form of a cardiogram peculiar to himself, so that a man could almost be recognized and distinguished from his fellows by the electrical action of his heart. The galvanometer has a near relative, the electrometer, the astounding delicacy of which renders it equally interesting. It is particularly valuable in certain important investigations as to the nature and construction of atoms. The galvanometer, it will be remembered, measures minute currents. The electrometer measures minute pressures, particularly those of small electrically charged bodies. Every conductor, and all things are conductors more or less, can be given a charge of electricity. Any insulated wire, for example, if connected to a battery, will become charged. Current will flow into it and there remain stationary. And there is what we mean by a charge as opposed to a current. Air compressed into a closed vessel is a charge. Air, however compressed, flowing along a pipe would be better described as a current. Imagine one of those cylinders used for the conveyance of gas under pressure, and suppose that we desire to find the pressure of the gas with which it is charged. We connect a pressure gauge to it and see what the finger of the gauge has to say. What happens is that gas from the cylinder flows into the little vessel which constitutes the gauge, and there records its own pressure. And just the same applies with electrometers. Precisely as the pressure gauge measures the pressure of air or gas in some vessel, so the electrometer measures the electrical pressure in a charged body. Further, some of the charged bodies with which the student of physics is much concerned are far smaller than can be seen with the most powerful microscope. How wonderfully minute and delicate, therefore, must be the instrument which can be influenced by the tiny charge which so small a body can carry. It will be interesting here to describe an experiment performed with an electrometer by Professor Rutherford, by which he determined how many molecules there are in a centimeter of gas, a number very important to know, but very difficult to ascertain, since molecules are too small to be seen. This number, by the way, is known to science as Avogadro's constant. Everyone has heard of radium, and knows that it is in a state which can best be described as a long, drawn-out explosion. It is always shooting off tiny particles. Night and day, year in and year out, it is firing off these exceedingly minute projectiles, of which there are two kinds, one of which appears to be an atom of helium. Some years ago, when radium was being much talked about, and the names of Monsieur and Madame Curie were in everyone's mouth, little toys were sold, the invention, I believe, of Sir William Crookes, called spinthariscopes. Each of these consisted of a short brass tube with a small lens in one end. Looking through the lens in a dark room, one could see little splashes of light on the walls of the tube. Those splashes were caused by a tiny speck of radium in the middle of the tube, the helium atoms from which, by bombarding the inner surface of the tube, produced the sparks. Now, if we can count those splashes, we can tell how many atoms of helium are being given off per minute. And if then we reckon how many minutes it takes to accumulate a cubic centimeter of helium, we can easily reckon how many atoms go to the cubic centimeter. But the difficulty is to count them. So the learned professor called in the aid of the electrometer. He could not count all the atoms shot off, so he put the piece of radium at one end of a tube and an electrometer at the other. Every now and then an atom shot right through the tube and out at the farther end. And since each of these atoms from radium is charged with electricity, each, as it emerged, operated the electrometer. By simply watching the twitching of the instrument, therefore, it was possible to count how many atoms shot through the tube. One atom, one twitch. And from the size and position of the tube, it was possible to reckon what portion of the whole number shot off would pass that way. The result of the experiment showed that there are in a cubic centimeter of helium a number of atoms represented by 256 followed by 17 noughts. And as helium is one of the few substances in which the molecule is formed of but one atom, that is also the number of molecules. And now consider this, please. A cubic centimeter is about the size of a boy's marble. That contains the vast number of molecules just mentioned. And the electrometer was able to detect the presence of those one at a time. Need one add another word as to the inconceivable delicacy of the instrument? In its simplest form, the electrometer is called the electroscope. Two strips of gold leaf are suspended by their ends under a glass or metal shade. As they hang normally, they are in close proximity. Their upper ends are, in fact, in contact and are attached to a small vertical conductor. A charge imparted to the small conductor will pass down into the leaves, and since it will charge them both, they will repel each other, so that their lower ends will swing apart. Such an instrument is very delicate, but because of the extreme thinness of the leaves, it is very difficult to read accurately the amount of their movement, and so to determine the charge which has been given to them. In a more recent improvement, therefore, only one strip of gold leaf is used, the place of the other being taken by a copper strip. The whole of the movement is thus in the single gold leaf, as the copper strip is comparatively stiff, and it is possible to arrange for the movement of this one piece of gold leaf to be measured by a microscope. The other principal kind of electrometer we owe, as we do the galvanometers, to the wonderful ingenuity of Lord Kelvin. In this, the moving part is a strip of thin aluminum, which is suspended in a horizontal position by means generally of a fine quartz fiber. Since it is necessary that this fiber should be a conductor, which quartz is not, it is electroplated with silver. Thus, a charge communicated to the upper end of the fiber, where it is attached to the case, passes down to the aluminum needle, as it is called. Now the needle is free to swing to and fro with a rotating motion between two metal plates carefully insulated. Each plate is cut into 4 quadrants, the opposite ones being electrically connected, while all are insulated from their nearest neighbors. One set of quadrants is charged positively, and one set negatively by a battery, but these charges have no effect upon the needle until it itself is charged. As soon as that occurs, however, they pull it round, and the amount of its movement indicates the amount of the charge upon the needle, and therefore the pressure existing upon the charged body to which it is connected. The direction of its movement shows, moreover, whether the charge be positive or negative. A little mirror is attached to the needle, so that its slightest motion is revealed by the movement of a spot of light, as in the case of the mirror galvanometers. Instruments such as these are called quadrant electrometers. My readers will remember, too, the string galvanometer already mentioned. The same idea has been adapted to this purpose. A fine fiber is stretched between two charged conductors, while the fiber is itself connected to the body whose charge is being measured. The charge which it derives from the body causes it to be deflected, which deflection is measured by a microscope. In all cases of transmission of electricity over long distances, for lighting or power purposes, the currents are alternating. They flow first one way and then the other, reversing perhaps 20 times a second, or it may be 200, or even more times in that short period. Some electric railways are worked with alternating current, and it is used for lighting quite as much as direct current and is equally satisfactory. In wireless telegraphy, it is essential. In that case, however, the reversals may take place millions of times per second. Consequently, to distinguish the comparatively slowly changing currents of a frequency or periodicity of a few hundredths per second from these much more rapid ones, the latter are more often spoken of as electrical oscillations. And these alternating and oscillating currents need to be measured just as the direct currents do. Yet in many cases the same instruments will not answer. There has therefore grown up a class of wonderful measuring instruments specially designed for this purpose, by which not only does the station engineer know what his alternating current dynamos are doing, but the wireless operator can tell what is happening in his apparatus. The investigator can probe the subtleties of the currents which he is working with, and apparatus for all purposes can be designed and worked with a system and reason which would be impossible but for the possibility of being able to measure the behavior of the subtle current under all conditions. One trouble in connection with measuring these alternating currents is that they are very reluctant to pass through a coil. One method by which this difficulty can be overcome has been mentioned incidentally already. I refer to the heating of a wire through which current is passing. This is just the same whether the current be alternating or direct. One of the simplest instruments of this class has been appropriated by the Germans, who have named it the Rice electrical thermometer, although it was really invented nearly a century ago by Sir William Snow Harris. It consists of a glass bulb on one end of a glass tube. The current is passed through a fine wire inside this bulb, and as the wire becomes heated, it expands the air inside the bulb. This expansion moves a little globule of mercury, which lies in the tube, and which forms the pointer or indicator by which the instrument is read. As the temperature of the wire rises, the mercury is forced away from the bulb. As the temperature falls, it returns. And as the temperature is varied by the passage of the current, so the movement of the mercury is a measure of the current. Another way is to employ a rectifier. This is a conductor which has the peculiar property of allowing current to pass one way but not the other. It thus eliminates every alternate current and changes the alternating current into a series of intermittent currents all in the same direction. Rectified current is thus hardly described by the term continuous, but still it is continuous current in the sense that the flow is always in the same direction, and so it can be measured by the ordinary continuous current instruments. The difficulty about it is that there is some doubt as to the relation between the quantity of rectified current which the galvanometer registers and the quantity of alternating current which, after all, is the quantity which is really to be measured. How the rectification is accomplished will be referred to again in the chapter of wireless telegraphy. But to return to these thermal galvanometers, as those are termed which ascertain the strength of a current by the heat which it produces, the simple little contrivance of Sir William Snow Harris has more elaborate successors, of which perhaps the most interesting are those associated with the name of Mr. W. Dudell, who has made the subject largely his own. Besides their interest as wonderfully delicate measuring instruments, these have an added interest since they introduce us to another strange phenomenon in electricity. We have just noted the fact that electricity causes heat. Now we shall see the exact opposite, in which heat produces electrical pressure and current. And the feature of Mr. Dudell's instruments is the way in which these two things are combined. By a roundabout but very effective way, he rectifies the current to be measured, for he first converts some of the alternating current into heat, and then converts that heat into continuous current. If two pieces of dissimilar metals be connected together by their ends, so as to form a circuit, and one of the joints be heated, an electrical pressure will be generated, which will cause a current to flow round the circuit. The direction in which it will flow will depend upon the metals employed. The amount of the pressure will also depend upon the metals used, combined with the temperature of the junctions. With any given pair of metals, however, the force, and therefore the volume of the current, will vary as the temperature. Really, it will be the difference in temperature between the hot junction and the cold junction. But if we so arrange things that the cold junction shall always remain about the same, the current which flows will vary as the temperature of the hot one. The volume of that current will therefore be a measure of the temperature. Such an arrangement is known as a thermocouple. It is becoming of great use in many manufacturing processes as a means of measuring temperatures. In the Dudell thermogalvanometers, therefore, the alternating current is first led to a heater consisting of fine platinized quartz fiber or thin metal wires. Just above the heater there hangs a thermocouple consisting of two little bars, one of bismuth and the other of antimony. These two are connected together at their lower end where they nearly touch the heater, but their upper ends are kept a little apart, being joined, however, by a loop formed of silver strip. This arrangement will be quite clear from the accompanying sketch, and it will be observed that the loop is so shaped that the whole thing can be easily suspended by a delicate fiber, which will permit it to swing easily, like the coil in a mirror galvanometer. It is indeed a swinging coil of a galvanometer, formed with a single turn instead of the many turns usual in the ordinary instruments, and it will be noticed from the sketch that there is a mirror fixed just above the top of the loop. This coil, then, with the thermocouple at its lower extremity, is hung between the ends of a powerful magnet, much as the fiber of the Eindhoven galvanometer is situated. The alternating current to be measured comes along through the heater. The heater rises in temperature. That warms the lower end of the thermocouple. Instantly, a steady continuous current begins to circulate round the silver strip, which forms the coil, and that, acting just as the current does in the ordinary galvanometer, causes the coil to swing round more or less, which movement is indicated by the spot of light from the mirror. A current as small as 20 microamperes, or 20 millionths of an ampere, can be measured in this way. Mr. Dudell has also perfected a wonderful instrument called an oscillograph, for the strange purpose of making actual pictures of the rise and fall in volume of current in alternating circuits. To realize the almost miraculous delicacy of these wonderful instruments, we need first of all to construct a mental picture of what takes place in a circuit through which alternating current is passing. The current begins to flow. It gradually increases in volume until it reaches its maximum. Then it begins to die away until it becomes nil. Then it begins to grow in the opposite direction, increases to its maximum, and dies away once more. That cycle of events occurs over and over again at the rate, it may be hundreds of times per second. Now, for the actual efficient operation of electrical machinery working on alternating current, it is very necessary to know exactly how those changes take place. Do they occur gradually, the current growing and increasing in volume regularly and steadily, or irregularly in a jumpy manner? Engineers have a great fancy for setting out such changes in the form of diagrams, in which case the alternations are represented by a wavy line, and it is of much importance to obtain an actual diagram showing not what the changes should be according to theory, but what they really are in practice. It is then possible to see whether the wave form of the current is what it ought to be. Once again, we must turn our thoughts back to the string galvanometer. In that case, it will be remembered there is a conducting fiber passing between the ends or poles of a powerful magnet, the result of which arrangement is that as the current passes through the fiber, it is bent by the action of the magnetic forces produced around it. If the current pass one way, downwards, let us say, the fiber will be bent one way, while if it passes upwards, it will be bent the opposite way. Suppose then that we have two fibers instead of one, and that we send the current up one and down the other. One will be bent inwards and the other outwards. Then suppose that we fix a little mirror to the center of the fibers, one side of it being attached to one fiber and the other to the other. As one fiber advances and the other recedes, the mirror will be turned more or less. Consequently, as the current flowing in the fibers increases or decreases or changes in direction, the mirror will be slewed around more or less in one direction or the other. The spot of light thrown by the mirror will then dance from side to side with every variation, and if it be made to fall upon a rapidly moving strip of photographic paper, a wavy line will be drawn upon the paper, which will faithfully represent the changes in the current. In its action, of course, it is not unlike an ordinary mirror galvanometer, but its special feature is in the mechanical arrangement of its parts which enable it to move with sufficient rapidity to follow the rapidly succeeding changes which need to be investigated. It is far less sensitive than, say, a Thomson galvanometer, but the latter could not respond quickly enough for this particular purpose. End of section 2.
Section 3 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. CORBIN. The Fuel of the Future. We now enter for a while the realm of organic chemistry, a branch of knowledge which is of supreme interest, since it covers the matters of which our own bodies are constructed, the foods which we eat, and the beverages which we drink, besides a host of other things of great value to us. Although the old division of chemistry into inorganic and organic is still kept up as a matter of convenience, the old boundaries between the two have become largely obliterated. The distinction arose from the fact that there used to be, and are still to a very great extent, a number of highly complex substances, the composition of which is known, for they can be analyzed or taken to pieces, but which the wit of man has failed to put together. Consequently, these substances could only be obtained from organic bodies. The living trees or animals could in some mysterious way bring these combinations about, but man could not. The molecules of these substances are much more complicated than those with which the inorganic chemist deals. The important ingredient in them all is carbon, which with hydrogen, nitrogen, and oxygen almost completes the list of the simple elements of which these marvelous substances are compounded. In some cases, there appear to be hundreds of atoms in the molecule. If one takes a glance at a textbook on organic chemistry, the pages are seen to be sprinkled all over with C's and O's, N's and H's, with but an occasional symbol for some other element. Another feature of this branch, which cannot fail to strike the casual observer, is the queer names which many of the substances possess. Trimethylanilene, triphenylmethane, and mononitrophenol are a few examples which happen to occur to the memory, and they are by no means the longest or queerest sounding. Another peculiarity about these organic substances is that a number of them, each quite different from the others, can be formed of the same atoms. Certain atoms of hydrogen, sulfur and oxygen form sulfuric acid, and under whatever conditions they combine, they never form anything else. On the other hand, there are 66 different substances, all formed of 8 of carbon, 12 of hydrogen, and 4 of oxygen. This can only mean that in such cases as the latter, the atoms have different groupings, and that when grouped in one way, they form one thing, in another way some other thing, and so on. This explains the extreme difficulty which the chemist finds in building up some of these organic substances. Every now and again, we are startled by some eminent man stating that the time will come when we shall be able to make living things, when the laboratory will turn out living cows and sheep, birds and insects, even man with a mind and soul of his own. Yet one cannot but feel that such men, no matter how great their authority, are simply pulling the public's leg, to use a colloquial expression, for they hopelessly fail to make many of the commonest things. In many cases, where they wish to produce an organic substance, they have to call in the aid of some living thing to do it for them, even if it be but a humble microbe. For the microbes perform wonderful feats in chemistry, far surpassing those of the most eminent men. Hence the latter very sensibly use the microbe, employ it to work for them, just set things in order, and then stand by while the microbe does the work. Thus most things can be analyzed, that's to say, taken to pieces, while many things can now be synthesized, that is to say, built up from their constituent atoms, but still a great many remain, and among them the most important, the synthesis of which completely baffles man. One of the most useful and widespread substances, for example, cellulose, is at present at least utterly beyond us. We do not even know how many atoms there are in the cellulose molecule. The molecules may, for all we know, contain thousands of atoms. Indeed, many of these organic matters have very large molecules. And even if the chemist were able to make all kinds of organic matter, he would still be as far off as ever from making living matter. Indigo used to be derived entirely from plants of that name. One of the great triumphs of the organic chemist was when he produced artificial or synthetic indigo. But he is as far off as ever from making the indigo plant. It's claimed that synthetic rubber is exactly the same as natural rubber, although some users say it's not quite the same. Still, if it be so, it's dead rubber, not the living part of the plant. The time, then, is infinitely far distant when the chemist will be able to make anything with the characteristics of life, namely, to grow by accretion from, within, and to reproduce its kind. The most wonderful product of the laboratory is dead. At most, it simply resembles something which once was alive. But that's somewhat of digression. This dissertation on organic chemistry was simply intended to lead up to the question of liquid fuels, all of which are organic. In the life of today, one of the most important things is petroleum. This is a kind of liquid coal. Just how it was formed down in the depth of the earth is not clear. One idea is that it's due to the decomposition of animal and vegetable matter. Another is that certain volcanic rocks, which are known to contain carbide of iron, might, under the influence of steam, have in bygone ages given off petroleum or paraffin, to use the other name for the same thing. In many parts of the world, these deposits of oil are obtained by sinking wells and pumping up the oil. In others, the liquid gushes out without the necessity of pumping at all. This is believed to be due to the fact that water pressure is at work. Artesian wells, from which the water rushes of its own accord, are quite familiar and are due to the fact that some underground reservoir tapped by the well is fed through natural pipes, really fissures in the rock, from some point higher than the mouth of the well. Now supposing that a reservoir of oil were also in communication with the upper world in the same way, the descending water would go to the bottom, underneath the lighter oil, and would thus lift it up so that on being tapped, the oil would rush out. Another source of mineral oil is shale, such as is to be found in vast deposits in the southeast of Scotland. This shale is mined much as coal is. It's then heated in retorts as coal is heated at the gas works, and the vapor which is given off, on being condensed, forms a liquid like crude petroleum. In all these cases, the original oil is a mixture of a great number of grades, differing from each other in various ways. They are all hydrocarbons, which means compounds of carbon and hydrogen, and they extend from cymogen, the molecules of which contain 4 atoms of carbon and 10 of hydrogen, to paraffin wax, which has somewhere about 32 of carbon to 66 of hydrogen. For practical purposes, their most important difference is the temperature at which they boil or turn quickly into vapor. This forms the means by which they are sorted out. In a huge still, like a steam boiler, the crude or mixed oil is gradually heated, and the gas given off is led to a cooling vessel, where it's chilled back into liquid. The lightest of all, cymogen, is given off even at the freezing point of water. That's led into one chamber and condensed there. Then, as the temperature rises to 18 degrees Celsius, rigolin is given off. That's collected and condensed in another vessel. Between 70 degrees and 120 degrees, petroleum ether and petroleum naphtha are produced, and they together constitute what is commonly called petrol. Between 120 degrees and 150 degrees, petroleum benzene rises. All the foregoing taken together constitute about 8 to 10% of the whole crude oil. Then, between 150 degrees and 300 degrees, there comes off the great bulk of the oil, nearly 80%, the kerosene or paraffin which we burn in lamps. Above 300 degrees, there is obtained another oil, which is used for lubrication, also the invaluable Vaseline, and finally, when the steel is allowed to cool, there remains a solid residuum known as paraffin wax. This process is known as fractional distillation, and it will be noticed that it consists essentially in collecting and liquefying separately those vapors which are giving off at different ranges of temperature. For our purpose in this chapter, we are mainly concerned with the petrol and the kerosene. Many efforts have been made in times gone by to use kerosene for firing the boilers of steam engines. In naval vessels, a great deal is so used at the present time, but the chief method of employing oil for generating power is to use it in an internal combustion engine. These machines have been dealt with at length in Engineering of Today and Mechanical Inventions of Today, and so must be simply mentioned here. They consist of two types. In one, which is exemplified by the ordinary car or bicycle motor, the oil is gasified in a vessel called a carburetor or vaporizer and then led into the cylinder of the engine together with the necessary air to enable it to burn. At the right moment, a spark ignites the mixture, which burns suddenly, causing a sudden expansion, in other words, an explosion. Thus the power of the engine is derived from a succession of explosions. If the fuel be petrol, it vaporizes at the ordinary temperature of the engine and needs no added heat. With kerosene, however, heat has to be employed in the vaporizer to make it turn readily into a gas. The other method is employed in engines of the new diesel type, in which the cylinder of the engine, being already filled with hot air, has a jet of oil sprayed into it. The heat of the air causes it to burst into flame, causing an expansion which drives the engine. An important feature in the latter type of engine is that the oil is very completely burned, so that very heavy oils can be used, oils which, if employed in an engine of the other kind, would choke up the cylinder with soot. In other words, the range of oils which can be used in this new kind of engine is much wider than is possible in the others. The latter may be likened to a fastidious man who is very particular about his food, while the former resembles the man of hearty appetite who can eat anything. And just as a man of the latter sort is more easily provided for by the domestic authorities, so the diesel engine makes the problem of the provision of liquid fuel much simpler. For it must never be forgotten that the provision of liquid fuel for the world is by no means a simple matter, since the supply is by no means adequate. The output runs into thousands of millions of gallons, and the whole world is being searched for new fields of oil, and yet it's all swallowed up as fast as it can be produced, while the coal mines do not feel the competition. A year or so ago, the United States and Russia, between them, and they are the greatest producers, obtained 5 billion gallons of oil, seemingly an enormous quantity. But on the other hand, Great Britain alone produces over 250 million tons of coal per annum. If therefore liquid fuel is to displace coal, as some people lightly think it's going to do, the supply will have to be multiplied many times. In the amount of heat which it is capable of giving, the coal of Great Britain alone beats the oil produced by the whole world. And another thing to be borne in mind is that as the coal miner goes down to the seam and sees for himself what's there, while the oil producer simply stays at the surface and draws it up with a pump, the coal man knows far more as to how much there is still left than the oil man does. We know that the coal deposits will last for many years to come, even if the production go on increasing, whereas the oil supply may fall off in the near future instead of increasing. And in both cases, we are using up capital. Coal is not being made on the earth now, at any rate in any appreciable quantity. The stage of the earth's history favorable to the formation of coal measures has long gone by, and the same probably applies to oil. It is interesting in this connection to note that coal itself is to a certain extent, or can be at all events, a source of oil. When coal is heated in order to make it give up its gas or to turn it into coke, vapors are given off, which on cooling become coal tar, at one time regarded only as a crude sort of paint. This is now the source from which many chemical substances are obtained, varying from photographic chemicals to saccharin, a substitute for sugar. So valuable are these products that there is a brisk demand for the tar in other directions than the manufacture of oils, but oils of various kinds are also obtained from it. The first step in the operations is fractional distillation, after the manner just described for petroleum. The first fraction is coal tar naphtha, then follows carbolic oil, after that heavy or creosote oil, anthracene oil, and finally there remains in the still, on cooling, a solid residue known as coal pitch. The naphtha, on being distilled again, gives among other things benzene, from which the famous aniline dyes are made and which is useful in many industries. Creosote is largely employed as a preservative for wood, being forced into the timber under high pressure so that it penetrates right into it and tends to prevent rotting, no matter how wet it may be. Railway sleepers are thus treated, small truckloads of them being run into a cast iron tunnel, which is then sealed at both ends, while the creosote is forced in by powerful pumps. After such treatment, they can lie nearly buried in the damp ballast for a long time without any deterioration. These coal tar substances are all very similar to petroleum and its products, hydrocarbons, compounds of hydrogen, and carbon in various proportions. Many of them could be used for fuel. But since they are based upon the supply of coal, which is itself limited, they cannot, however, they may be used, do more than stave off the evil day when the supply will be exhausted. Quite different is it with alcohol, which it seems likely may be the fuel of the future. Some people will be inclined to exclaim, "What a pity to burn it," since to many the word conveys ideas of another sort altogether. There are many nowadays, however, who, like the writer, have none but a scientific interest in it. To such whiskey, for example, is but impure alcohol, and it's without the impurities that it may become of vast use to the world, thereby possibly repaying man for some of the harm which in the past it has inflicted upon him. Alcohol again is a hydrocarbon. It's really more correct to speak of it in the plural as alcohols, since there is a large group of substances all of the same name. Two of these are of the greatest importance, methyl alcohol and ethyl alcohol. The former is obtained from wood, hence it's sometimes called wood spirit. Wood is strongly heated in an iron still, and the methyl alcohol is given off in the form of vapor, which, on being collected and cooled, condenses into a liquid. it's exceedingly unpleasant to the taste. If it were the only kind, there would be no consumption of alcohol as a drink. The second kind mentioned is obtained by the agency of germs or microbes, and the story of its production is so interesting as to demand a little space. We will commence with the maltster. He performs the first part of the operation, starting with ordinary barley. By the action of heat, aided by natural growth, he produces the raw material on which the brewer may work. Now barley, like all grain, is largely made up of starch, and although starch will not make alcohol, it can be turned into sugar, which will. So the task of the maltster is to commence the change of the starch in the grain into sugar. First of all, it's soaked in water and spread upon floors, and heated until it begins to sprout. There is a little part in each grain called the endosperm, which is the embryonic plant, and the starch is really the food provided by nature to nourish the growing endosperm until such time as it shall be strong enough to draw its nourishment from the soil. In order that it may not be washed away prematurely, the starch is locked up by nature in closely fastened cells, and moreover, it's insoluble so that water cannot carry it away. The endosperm, however, has at its disposal certain substances known as enzymes, and it increases its store of these as it grows, one of which is able to dissolve away the walls of the cells, to unlock the treasures, as it were, while the other turns the insoluble starch into soluble matter, in which state the growing organism is able to make use of it as food. So as the grain sprouts upon the maltster's floor, this process is going on. The cells are being opened and their contents converted from starch into soluble matters. Then, when the growth has gone far enough, the grain is transferred to a kiln where it's subjected to heat, by which the growth is stopped. The living part of the grain is in fact killed. That's mainly to stop the young plant from eating up the altered starch, which it would do if allowed time, but which the brewer wants to be kept for his own use. The maltster's task is now finished, and we come to the brewer's. The first thing he does with the malt is to crush it between rolls, thereby liberating thoroughly those substances which have been formed from the starch and which he intends to turn into sugar. Having crushed it, he places it in the mesh tun, a large tank of wood or iron, in which it's mixed with water and subjected to heat. While in this vessel, the enzymes become active again and turn the soluble starch or a part of it into a kind of sugar. The liquid drawn off from the mesh tun, containing of course the sugar, is subsequently boiled. Numerous flavoring matters, including hops, are added, and then it's cooled again, ready for the final process, fermentation. This takes place in a large vat or tun and is brought about by the agency of yeast, which is added to the liquid. Now yeast is a multitude of microscopic plants, round in shape and about 1/3000th of an inch in diameter. Though so small, this little organism is really quite complicated in its structure, and within its little body there are carried on complicated chemical changes which baffle entirely the most learned chemist to imitate. Further, he has yet to find out how the little yeast plant does it. He not only cannot imitate the process, he doesn't know what the process is. These little organisms multiply mainly by the process of budding. A new one grows out of the side of each old one, rapidly reaches maturity, breaks away, and commences an independent existence. No sooner it's free than it, in turn, gives birth to another. Indeed, so great is its hurry to propagate itself that sometimes the new cell begins to throw out a bud before it has itself separated from its parent. It's therefore easy to see that yeast increases in quantity by what some call leaps and bounds, but which the mathematically minded know as geometrical progression. The particular form of sugar with which we are concerned here is known as dextroglucose. This, the yeast, splits up into alcohol and carbonic acid gas. The latter bubbles up to the surface and escapes into the air, while the alcohol becomes dissolved in the watery liquid. It is believed that the yeast performs this operation not directly, but by the production of certain enzymes, which in their turn act upon the sugar. The liquid so formed is beer, but since it's alcohol with which we are concerned and not beer, many details connected with its manufacture have been omitted. Enough has been said, however, to show that by comparatively simple processes, grain of all sorts, in fact, anything which contains starch, and such things are to be found in worldwide profusion, can be turned into alcohol. All the really intricate chemical functions are performed readily and cheaply by living organisms. All man has to do is to set up the conditions under which the organisms can work. In the process just described, only a portion of the starch in the grain is converted into sugar. Hence the percentage of alcohol in beer is comparatively small. If all the starch be converted a liquid, much stronger in alcohol is produced, and if that be distilled, so as to separate the spirit from the water with which it's mixed, there results whiskey. Brandy likewise is the spirit distilled from wine, rum from molasses, and so on. In all these familiar beverages, the essential feature is this same alcohol, of the variety known as ethyl alcohol. It will be noticed that in the making of beer, the alcohol is actually formed in water. There is a sugary water which under the action of the yeast becomes an alcoholic water, and this indicates a very useful feature about the liquid when used for industrial purposes. A tank full of petrol is extremely dangerous, so much so that the storage of petrol is hedged about by all manner of precautions. The danger is that it gives off an inflammable vapor, and that if it once begin to burn, there is particularly no possibility of putting it out. Being lighter than water, it simply glows with a layer of fire any water which may be thrown onto it. The water in such circumstances simply serves to spread the naming petrol about, and so to make matters worse. Now alcohol, with its partiality for the companionship of water, behaves quite differently. True, it also may give off an inflammable vapor, but if a quantity of it catch fire, it can be extinguished in the usual way by a fire engine. The water and alcohol immediately combine. The alcohol becomes dissolved in the water, just as sugar may do, and as soon as the percentage of water in the mixture becomes considerable, the burning stops. It may be that some readers will have discovered this fact for themselves without knowing precisely what it was. It is a common dodge with amateur photographers if they want to dry a negative, quickly to immerse it in methylated spirit. The spirit seems to take the water out of the film, and itself, drying quickly, leaves the negative in a perfectly dry condition in a few minutes. Now, after using spirit in that way, it's useless to put it in a stove or lamp. It will not burn. Methylated spirit is alcohol, and the reason why it has such a quick drying action is that it and the water in the wet film quickly mix. After immersion, the film is wet, not with water merely, but with a mixture of a lot of spirit and a little water. Hence the speed with which it evaporates, and the non-inflammability of the mixture is due to the presence of the water. Methylated spirit only differs from the alcohol in alcoholic beverages in that something is added to make it undrinkable, owing to the craving for it, which is so widespread, and the doubtful effect which it has on certain citizens. Most states regard it as preeminently a subject for taxation, thereby on the one hand bringing in a good revenue, and on the other discouraging its too free use. But those considerations apply only to drinkable alcohol. That which is to be used for industrial purposes is not in any way a legitimate object for taxation. Hence the problem arises of making a form of alcohol which shall answer all the needs of the industries which use it, and at the same time be so repulsive to the senses that no one can possibly drink it. This result is achieved by adding some of the methyl alcohol derived from the vapor given off by wood when heated, commonly known as wood spirit. This is so unpleasant that it renders the mixture of no use for drinking, and so it can safely be freed from taxation. Unfortunately, this spirit has less heating value than petrol. That means that a given quantity of each liquid will produce more heat in the case of petrol than in the case of alcohol. Indeed, the difference is about 2 to 1. Hence an engine to give out a certain horsepower would need to have its cylinders twice as big if it were to use alcohol instead of the other fuel. There is a certain compensation, however, in the fact that alcohol is very easily compressible. In modern internal combustion engines, much of the efficiency is due to the explosive charge which is drawn into the cylinder being compressed into a small space before it's fired. It was the discovery of the value of compressing the gas which made the gas engine so formidable a rival to the steam engine, and the wonderful performances of the diesel engines are due very largely to the fact that the air is compressed in the cylinder to a very high pressure. The jet of oil burns in highly compressed air, and because of the facility with which alcohol can be compressed, it's said to be more effective as a source of motive power than would be expected from its comparatively feeble heat. Thus we may sum up the possibilities of the future. Coal, petroleum, and their derivatives exist in limited quantities in the world, and so far as we can see, the vast drafts which we are taken from them are not being replaced. Indeed, at this stage of the earth's development, cannot be replaced by any more. Sooner or later, we must come to an end of them. Is it not comforting, therefore, to know that there is another source of fuel at hand, inexhaustible, since it can be produced as needed? We have only to set the sun and the ground to work to produce grain, rice, potatoes, or any of the myriad substances which contains starch, and from that, by simple and well-known processes, we can obtain a cheap, safe, and reliable fuel. Indeed, there seems nothing but the ultimate laws of sunlight, countless millions of years hence, which can ever check the supply of this valuable commodity. What has doubtless in many cases been a curse in the past may turn out to be the great boon of the future. End of section 3.
Section 4 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Some Valuable Electrical Processes. Students of that branch of science known as physics are coming to the conclusion that electricity plays a much more important part in the universe than was supposed. They are led to believe that electrical attraction is the cement which binds together those exceedingly minute particles out of which everything is built up. Whether electricity binds them together or not, it is certain that electrical action can in some cases separate those particles, and this process of separation provides a means of carrying on some very remarkable and useful industrial processes. Let us imagine a vessel filled with water to which has been added a little sulfuric acid, while suspended in it are 2 strips of platinum. There is a space between the strips, so that when their upper ends are suitably connected to a source of electric current, that current flows from one strip to the other through the liquid. That is an example of the apparatus for carrying out this electrical separation in its simplest form, and it will facilitate the further description if the names of the various parts are enumerated. The process itself is electrolysis. The liquid is the electrolyte, while the strips are the electrodes. The individual electrodes, again, have special names, that by which the current enters being the anode, and that by which it leaves the cathode. It is not difficult to remember which is which if we bear in mind that the current traverses them in alphabetical order. Since, however, it may not be easy for the general reader to carry all these terms in his mind, we will, when it is necessary to differentiate between the 2 electrodes, call one the in electrode and the other the out electrode. Returning now to our imaginary apparatus, let us turn on the current. At first, nothing seems to be happening, although suitable instruments would show that current was flowing. Soon, however, little bubbles appear upon the electrodes, and these grow larger and larger until they detach themselves from the platinum to which they have been adhering, float up to the surface, and burst. The question which naturally arises is, what do these bubbles consist of? Are they air? If we take means to collect the gases which formed them, we get an unmistakable answer. The bubbles which arise from the in electrode are oxygen, those from the other, hydrogen. If we allow our apparatus to work for some time and collect all the gas which arises, we shall find that there is twice as much hydrogen as oxygen. We shall also find, as the process goes on, that the quantity of water diminishes. Perhaps I may be allowed at this point to remind my readers that water is a collection of minute, ultramicroscopic particles called molecules, each of which is formed of 3 smaller particles still, called atoms. Of the 3 atoms, 2 are hydrogen and 1 oxygen. Water, therefore, consists of hydrogen and oxygen, there being twice as much of the former as there is of the latter. We see, therefore, that electrolysis gives us hydrogen and oxygen in exactly those proportions in which they occur in water, and since we also see that as these gases appear the water itself disappears, we are led to conclude that the current is splitting up the water into the gases of which it is formed. But the strange thing is that this will not work with pure water. We have to add something to it. In the case of our imaginary experiment, it was sulfuric acid. What part does that play? This is not fully understood, but we may be able to form a mental picture of what is believed to happen as follows. The in electrode is surrounded by a vast assemblage of these tiny molecules, most of those of water, but a few of those of acid. The latter are more complex in their structure than the former, but they too contain hydrogen. Current flows into the electrode and instantly hydrogen atoms from the acid molecules crowd round it, like boatmen at the seaside anxious to secure a passenger. Each takes on board a quantity of electricity and with it darts across the intervening space to the other electrode. Arrived there, it gives up its load and, its work done, remains lying upon the electrode until enough others like unto itself have gathered there to form a bubble and so escape. These hydrogen atoms are thought to be the craft which carry the current through the liquid and enable it to pose, as it were, as a conductor of electricity, which in reality it is not. But where does the oxygen come from? To find the answer to that, we must add a second chapter to our story. When the hydrogen boats took on board their load of electricity, they left their former associates, and these forthwith set upon neighboring water molecules, and with the audacity of highwaymen stole from them enough hydrogen atoms to take the place of those they had lost. Thus the acid molecules became complete once more, while the scene of the conflict near the in-electrode was strewn with the remains of the water molecules from which the hydrogen atoms had been stolen. These remains, of course, would be oxygen, and they, collecting together on the electrode, would eventually be in numbers sufficient to form bubbles and so escape. Thus it may be the acid which really does the work, yet because of its subsequent raid upon the water, it is the latter which disappears, and it is the materials of the latter which are brought to the surface in the bubbles. And there we see the mechanism whereby, so it is believed, electric current can pass through otherwise non-conducting liquids. And the important part, as far as practical utility is concerned, is that the passage of the current is accompanied by a splitting up of something or other, either the water or something in it, the materials of which are deposited, one on one electrode and the other on the other. And now we can proceed to those useful applications of electrolysis, the commonest of which, perhaps, is electroplating. We have seen how electrolysis causes hydrogen, probably out of the acid, to be deposited upon one electrode. Suppose that, instead of an acid, we put in the water one of those substances known to chemists as a salt, the commonest example of which is ordinary table salt. This well-known condiment is caused by the interaction of hydrochloric acid and the metal sodium, and will serve to illustrate what all salts are. All acids are compounds of hydrogen and something else, and their biting action is due to the readiness which the something else evicts the hydrogen and takes in a metal in its place. Thus, hydrochloric acid, given the opportunity, gets rid of its hydrogen and takes in sodium, thereby forming chloride of soda or a common salt. Another example is the gold chloride familiar to photographers. This is the result of the action of certain acids upon gold, wherein the acids throw out their hydrogen and take in gold instead. To sum up, then, a salt is just the same sort of thing as an acid, like the sulfuric acid which we used in our experiment, except that some metal has taken the place of the hydrogen. It is not surprising, then, to find that if we put a salt in the electrolyte instead of an acid, we get a similar result. In one case, hydrogen is deposited upon the out electrode, in the other, the metal. In the former case, since hydrogen is a gas, it forms bubbles and floats away, but in the latter the solid metal remains a thin, even coating upon the electrode. This is the principle of electroplating. The electrolyte consists of a suitable solution containing a salt of the metal to be deposited, and it is placed in an insulating vessel or vat. The articles to be plated form the out electrode, so that they have to be suspended in some convenient way from a metal conductor by conducting wires. Of course, they are entirely immersed in the liquid. The in electrode is sometimes a plate of platinum, the reason for that expensive metal being used being that it is unaffected by the chemicals, or else a plate of the metal being deposited. In the former case, the solution becomes weaker as the work proceeds, and more salt has to be added. In the latter, however, the strength of the solution remains unchanged, for by an interesting interchange the in electrode adds to it just what it loses by deposition upon the other one. The effect is therefore just as if the current tore off particles from the one and placed them upon the other. This is believed to be due to the agency of the oxygen, which in the case of the electrolysis of water becomes free, but which in this case forms with the metal electrode a layer of oxide upon its surface, this oxide being then dissolved away by the liquid. Thus, as fast as the metal is deposited upon the out electrode, its place is taken by more metal from the in electrode. In some processes, it is desired to deposit metal upon a non-conducting surface, and it is evident that such cannot be used as an electrode. Nor is it any use to attempt to deposit upon anything except an electrode. The only thing to do, then, is to make the object a conductor by some other means. Models in clay, wax, and plaster, once living objects like small animals, fruit, flowers, or insects, can, however, have a perfect replica made of them by electrical deposition, by the simple method of coating the surface to be plated with a thin layer of plumbago. This skin, although extremely thin, is a sufficiently good conductor to make the process possible. Process blocks for printing are copied in this way, so that a particularly delicate example of the blockmaker's art need not be worn down by much pressing, copies or electrodes being made off it for actual use in the press. The original block is a plate of copper on which the picture is represented by minute depressions and prominences. On this a layer of soft wax is pressed, so as to obtain a perfect but reversed copy. Having been coated with plumbago, this is then put into a vat containing a solution of copper salts and is used as the out electrode, the other being a plate of copper. When the current is turned on, the copper is thus deposited on the wax until a thin sheet of copper is formed which is an exact but reversed copy of the wax, a direct copy, that is, of the original block. The back of this thin sheet is then covered with molten lead or type metal to fill up any depressions and to give it sufficient strength. Anyone who has seen one of these half-face blocks covered with minute depressions so slight they can scarcely be seen, yet so perfect that a beautiful print can be obtained from them, will realize the wonderful power of this electrolytic process, and the marvelous accuracy with which the original is copied, and the unerring way in which the electrical current carries the particles of copper into every one of the myriad recesses in the wax. Another specimen of the marvelous work of this system is the wax cylinder of the phonograph. The sound is produced by a needle traveling along a groove of varying depth cut in the surface of the cylinder. This groove forms a spiral, passing round and round like the thread of a screw, and it encircles the cylinder 100 times in every inch of its length. Consequently, at any point one may take, there is but 1/100th of an inch from the center of one turn to the center of the turn on either side of it, and at its deepest, the groove is less than 1/1000th of an inch deep. The phonograph itself cuts the first master record, as it is termed, and the problem is to take a number of casts off this model of such delicacy and accuracy that every variation in that exceedingly fine groove shall be faithfully reproduced. Such a task might well be given up as hopeless, but with the help of electrolysis it is accomplished easily and cheaply. To attempt to press anything upon the surface of the master would but smooth out the soft wax and obliterate the groove altogether. To apply anything softened by heating would be to melt it. But electrolysis, without tending in any way to distort or damage the delicately cut surface, deposits upon it a surface of metal from which thousands of casts can be made. The gentle fingers of the electricity overlay the soft wax with the hard, strong metal with a minute perfection almost beyond belief. To commence with, the master record is placed upon a sort of turntable in a vacuum, and turned round in the neighborhood of 2 strips of gold leaf strongly electrified. By this means the gold is vaporized, and a perfect coating of gold is laid upon the wax. This is far too thin to be of any use except to render the cylinder a conductor, for the coating is so fragile that it is no stronger than the wax itself. It enables the cylinder, however, to be electroplated with copper until it is surrounded by a strong metallic shell 1/16th of an inch thick. It takes about 4 days to deposit this thickness. The copper shell is then turned smooth in a lathe and fitted tightly into a brass jacket. A little cooling causes the wax record to shrink sufficiently to free it from the copper shell and allow it to be lifted out. A copper mold is thus formed in which any number of additional records can be cast. The molten wax is simply introduced into the inside and allowed to set. The inside is bored out in a lathe, and then with a little cooling it shrinks and can be withdrawn. a completely finished record, every tiny depression or swelling in the original master being reproduced with an accuracy almost incredible. Another valuable use to which this process is put is the purification of metals. The electrochemical action works with unerring precision. It never mistakes an atom of iron for an atom of copper, for example. Passing through a solution of copper salt, the current deposits only copper. For modern electrical machinery and apparatus, copper is required of the utmost possible purity, for every impurity adds to its electrical resistance. In other words, diminishes its value as a conductor. Consequently, thousands of tons of electrolytic copper, as it is termed, are produced every year. The electrodes used are plates of ordinary copper. A coating of pure metal is deposited by electrolysis upon the out electrode from the other one. When the deposit is thick enough, the out electrode is taken out and the deposit torn off it, the union between the two being sufficiently imperfect for this to be done without difficulty. The metal of which the in electrode is made has already been purified by other processes, until it contains but 1% of foreign matter, and by this means even that small percentage is entirely got rid of. The impurities fall to the bottom of the vessel in the form of slime, which is periodically removed. And not only is electrolysis thus unerring in picking out certain atoms from among a mixture, but there is an exact relation between the work being done and the quantity of current used. Consequently, it forms a very exact method of measuring currents. The method of measuring current by the strength of the magnetic field which it produces has been mentioned already, and such measurements can be checked by electrolysis. Thus, the practical definition of the ampere is that current which, when passed through a solution of silver nitrate in water, will deposit silver at the rate of 0.001118 gram per second. The electric accumulator, or secondary battery, one of the most useful appliances, is the result of electrolysis reversed. Many large electric lighting plants have, in addition to their generating machinery, a large battery of secondary cells which, being kept charged, are able to help the machinery in times of heavy demand, or even to supply the whole current needed for, say, half an hour, so that the whole of machinery could, in the event of an accident, be shut down for that time and the supply maintained from the batteries. This would be sufficient in many cases for fresh machinery to be brought into action or emergency arrangements to be made. It may be that this book is being read by someone seated serenely in his armchair, while engineers and workmen at the generating station are working in frantic haste to set right some sudden breakdown before the batteries are run down. The batteries may have saved the town half an hour's darkness. Large telegraph offices are fitted with secondary batteries. Many motorists owe the ignition which keeps their engines at work to secondary batteries. It is secondary batteries which keep the wireless apparatus at work on a wrecked vessel after the engines have stopped. Indeed, secondary batteries are one of the most beneficent inventions, and if only they could be made in a lighter form than is possible at present, their value would be infinitely increased. We have seen how the passage of current through acidulated water produces hydrogen and oxygen. If those gases be collected in closed vessels over the water, so that they remain in contact with the water, as soon as the current is stopped, a reverse action sets in. The gases tend to recombine with the electrolyte, and in doing so give back a current equal to that which formed them. Figure 4 shows the construction of what is called a voltometer, in which the gases arising from the electrodes are collected in little gas vials placed just above them. Such an apparatus enables us to see easily how the accumulator works. The picture shows the battery which is effecting the separation of oxygen and hydrogen. If that be disconnected and the wires joined, as shown by the dotted line, a current will flow back until the oxygen and hydrogen have returned into the solution again. The apparatus will, in fact, work like an ordinary battery, except that instead of a plate or rod of zinc, a mass of hydrogen will form the essential part. An appliance such as a voltometer is not of much use for the practical purpose of storing large quantities of electrical energy because the surfaces of the electrodes are so small, and the surfaces where the liquid and gases are in contact are small too. It is clear that the larger the electrodes are, the wider will be the passage for the current, just as a wide road can accommodate more traffic than a narrow path. We may regard the electrodes as like gateways through which the current passes. By making them large, therefore, we enable a large current to pass, and consequently permit electrolysis to take place with greater comparative rapidity. The plates, as the electrodes in a secondary battery are termed, are generally large metal plates. Experiment has shown that lead is the best for this purpose. It has also been found that it can be improved by making it porous, since the inner surfaces of the pores are so much added surface through which current can pass into the electrolyte. There are various ways of producing this porosity, which need not trouble us here, however. It will suffice for our purpose to understand that an ordinary secondary cell consists of 2 lead plates, with the largest possible surface, immersed in a liquid, generally a dilute solution of sulfuric acid in water. To charge the battery, current is sent to one plate, through the liquid to the other plate, and so away. A thin film of hydrogen is thus formed upon the outgoing plate, while oxygen is formed at the incoming one. Since the hydrogen is spread over such a large area, it does not accumulate sufficiently for it to rise to the surface. Most of it remains adhering to the plate. The oxygen combines with the lead of its plate, and so is safely stored up there in the form of oxide of lead. This storage of hydrogen upon the one plate and oxygen on the other cannot go on indefinitely, and so as soon as the limit is reached, the cell is fully charged. Passage of further current is then simply a waste. The dynamo, or primary batteries which are used for charging having been disconnected, the 2 plates can be connected together through lamps, motors, or in any other desired way, and the current will flow out again, the opposite way to that in which it entered, just as a stone thrown up in the air returns the opposite way. The current which comes out is, in fact, a sort of reflex action arising from that which went in, the mechanism by which is produced being the reabsorption of the oxygen and hydrogen into the electrolyte. Whether a cell is fully charged or not is ascertained by weighing the electrolyte, an operation which at first sight seems to have nothing whatever to do with the matter. It arises from the difference in weight between water and sulfuric acid, the latter being the heavier. We have seen that while a little acid must be added to the water before it can be electrolyzed, it is the water which is ultimately resolved into its constituent gases. Hence, the result of electrolysis is to increase not the amount, but the proportion of acid. Therefore, it increases the weight of the electrolyte. This weight is ascertained by means of a hydrometer, a glass tube stopped and loaded with some small shot at its lower end. On the upper part is engraved a graduated scale, so that the exact depth to which it sinks can be easily read. This depth will, of course, vary with the specific gravity of the liquid, and so the depth recorded by the scale will be an indication of the proportion of acid, and that in turn will show how far the process of charging has progressed. Accumulators are, or have been hitherto at any rate, very troublesome things. They are apt to lose their power. If not properly charged, they are easily damaged. Too rapid charging, or too rapid discharging, standing for a while only partially charged, all these things have a bad effect, in extreme cases even destroying them altogether. Because of the use of lead, they are terribly heavy too, so much so that for traction purposes they are of very little use, for a large amount of the energy stored in the accumulators is then used up in hauling them about. Yet what a field there is for the successful accumulator! Take the one instance of the electrification of a railway. If good light and efficient accumulators were to be had, no alteration at all would be necessary to the permanent way. The engines or motor carriages would need to go periodically to a depot to be recharged, but that could be easily arranged. Such things as conductor rails, overhead conductors, and so on would be needless. The world has therefore been interested for years in the rumor that T.A. Edison was engaged upon this problem, and at last he has produced his accumulator, by which he has removed many of the difficulties, if not all. Instead of a case of glass or celluloid, as is usual with the older cells, his cells are enclosed in strong boxes of nickel steel. The positive plate consists of nickel tubes filled with alternate layers of nickel hydroxide, while the negative plate is formed of prepared oxide of iron in a nickel framework. The electrolyte is a solution of potassium hydroxide. The chemical action and the electrical reaction is, of course, on the same principle precisely as in the older cells, but it is claimed that the Edison cells are foolproof. That is to say, they cannot be damaged by careless handling, and they appear to be a little lighter. Thus, the problem is partly solved, and with that as a fresh starting point, someone may sooner or later give us a secondary battery which is light as well as strong. If any would-be scientific inventor reads these words, there is a suggestion for a promising line of investigation. End of Section 4. Section 5 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Machine-made cold. One of the most remarkable adaptations of scientific knowledge is the manufacture of cold. At first, that phrase seems strange, but it is really quite legitimate. There are machines at work at this moment which are turning out cold as if it were any other manufactured article. It is not that they manufacture cold water or cold air, it is the cold itself which they produce. Of course, cold has no real existence, since it is simply a negative quantity, an absence of heat, yet its effects are so real that we are in the habit of talking of it as if it were a reality, and in that sense we can regard it as a product of manufacture. Moreover, we see in this a conspicuous instance of the interdependence of invention and science, for scientific principles were first adapted to produce cold, and then artificial cold was employed in scientific inventions, whereby the rare gases of the atmosphere have been discovered, as we shall see presently. In mechanical inventions of today, I have dealt with the uses which can be made of heat as a motive power. Here we have in some sense a reversal of the process. In the heat engine, the expenditure of heat produces motion. In the refrigerating machine, motion produces heat. On the face of it, a strange way of producing cold. Yet it is by the production of heat in the first instance that we are ultimately able to obtain the cold. One way to make a thing cold is to place it in contact with ice, but that process suffers from severe limitations. In the first place, we may not be able to produce ice when we want it, and in the second place, we may want to produce a temperature much lower than that of ice. Now, a machine can produce any degree of coldness, almost down to the absolute zero, the point at which a body is absolutely devoid of any heat whatever, the condition in which its molecules are absolutely still. That point is 274 degrees Celsius below freezing point. Freezing point on that scale is 0, and so this absolute zero is minus 274 degrees. Or, to put it another way, freezing point is 274 degrees absolute temperature. The absolute zero has never been reached, and there is reason to believe that it never can be quite reached, but by methods about to be described, a temperature within a few degrees of it has been attained, and all of this can be done without any cooling agent colder than water at an ordinary temperature. There are several systems, but the one which illustrates the principle most simply is that in which carbonic acid gas is the working fluid. This is a very compressible gas, and so is well fitted for the purpose. First of all, a pump or compressor compresses it. That has the effect of heating it. Such we might expect from the fact that heat is molecular activity. When by compressing the gas we force the molecules closer to each other, they naturally hit each other and the sides of the container vessel harder than they did before, and the increased activity is manifested as increased heat. So the first effect, as was remarked just now, is to produce, apparently, increased heat. But then the hot compressed gas, by being passed through a coil of pipes surrounded by cold water, can be robbed of that heat. According to the speed at which it traverses the coil, it will be more or less cooled. By causing it to travel slowly, it can be brought down almost to the temperature of the water. So we start with the gas at atmospheric pressure and at somewhere about atmospheric temperature too. This we convert into compressed gas at high temperature. After cooling it, we have compressed gas at a moderate temperature. Then, to complete the process, we let the gas expand again. Now, just as compressing a gas heats it, letting it expand cools it. If we compressed it and then expanded it again, we should be just as we were to commence with. But since, in between the two operations, we extracted a quantity of heat by means of the cooling water, we get at the very end a much lower temperature than that with which we started. We cannot cool the gas without compressing it. because heat will only flow from one body into another when the second is cooler than the first. But, by making the gas hot temporarily by compression, we enable the water to draw some heat from it, and then, allowing it to sink back to its original state, we get practically the old temperature, less what the water has extracted. The principle is really absurdly simple when one once gets to understand it. The application is not so simple as far as the designer of the machine is concerned, for he has to adjust the various parts to exactly the right shape and dimensions so that they may work well with one another and produce the desired result with the minimum expenditure of power. To the observer, however, and to the user too, the finished machine is wonderful in its simplicity. The principle is illustrated diagrammatically in Figure 5. In the center is the compressor. Its action forces the gas along the pipe to the right and down into the condenser. As it flows downward through the coil, there cold water enters at the bottom of the tank, flows upward past the coil, and escapes again at the top. Thus the coil is kept in contact with cold water. Passing then through the bottom of the tank, the gas travels from right to left through the regulating valve and into an arrangement almost exactly similar to the condenser, but called the evaporator. Here the gas expands and suffers a great fall in temperature. This cold is communicated to liquid circulating in the tank which forms part of the evaporator, and this liquid can be circulated through pipes into any rooms to be cooled, or around vessels of water which it is desired to freeze. This liquid, which acts as the carrier of the cold, is called brine, and is water to which is added calcium chloride to keep it from freezing. Now the observant reader may have noticed that there is no apparent reason for the name of the left-hand vessel. It will be quite clear, however, when I explain that although I have spoken of the working fluid all along as a gas, I have only done so to avoid bringing in too many explanations at once. It is actually liquid for a good part of its journey. Carbonic acid gas liquefies at a very moderate temperature and pressure, and so, while it leaves the compressor as a gas, it becomes liquid in the condenser and remains so until it has passed the regulating valve. Then it begins to expand into gas once more, and in that state it passes back to the compressor. There is a pressure gauge on the pipe leaving the compressor and another on the one entering it. A comparison of the readings of these two tells how the apparatus is working. The difference between them indicates how much compression is being given to the gas. Assuming that the compressor is working at a constant speed, this compression can be regulated to a nicety by the valve. Close it a little and the compression will increase. Open it a little and the compression will decrease. By this means the degree of cold produced can be varied at will. This is the way in which many ships are enabled to carry cargoes of frozen meat. The chambers in which the meat is stowed are insulated, that is to say, their walls are made as impervious as possible to heat. Then the brine is carried into the chamber in pipes, cooling them much as the hot water pipes heat an ordinary public building. Or another method is to carry the pipe which constitutes the evaporator into the chamber to be cooled. A third way is to dispense with the brine and to blow air through the coils of the evaporator, whereby the air is made to carry away the cold to wherever it is needed. Ice can be made easily in molds of metal or wood around which brine circulates. If made of ordinary water, the ice is likely to be cloudy and opaque, which is quite good enough for many purposes. In cases where it is desired that it should be clear, the water is agitated during freezing, or else distilled water is used. To enable the blocks to be got out of the molds, it is sometimes arranged to circulate warm brine for a few moments. Ice skating rinks are formed by making first an insulating layer of sawdust, slag wool, or something of the sort, those, by the way, being the materials generally used for insulating cold chambers, underneath the floor. The floor, too, is made waterproof, and then upon it is laid as closely as possible a series of iron pipes. Water is flooded onto the floor until the pipes are covered to a depth of several inches, and then brine is pumped through the pipes. In time, the water freezes, and so long as the brine circulates, it remains so. But although the CO2 process, described above, is the simplest illustration of the principle, there are other systems. In one very popular form, ammonia gas is the working fluid. This is liquefied by pressure and cooling with water, being subsequently expanded just as described above. Another much-used system is the ammonia absorption process. in which the ammonia is not liquefied, but when under pressure is absorbed by water, returning to gas again when the pressure is released. But the degree of cold attained in these commercial machines is as nothing to the extremely intense cold generated on the same principles in the liquid air machine, which is found in every well-equipped physical laboratory. Briefly, this consists of a coil of many turns of small tube enclosed in a small double vessel, the space between the inner and outer skins of which is packed with insulating material. A compressor pumps air in the top of the coil at a pressure from 150 to 200 atmospheres. An atmosphere, it may be remarked, is a unit often used in scientific matters, meaning the normal pressure of the atmosphere, which is, roughly speaking, 15 pounds per square inch. Hence, 200 atmospheres is about 3,000 pounds per square inch. Of course, air so highly compressed as that is hot, but after it has passed down the coil and has escaped from the valve which liberates it at the bottom, it is much cooler. But that is only the beginning of the operation. The expanded, and therefore cooled, air finds its way upward through the turns of the coil down which the following air is coming. That, expanding in its turn, is colder still, because of the cooling action of the first air, and so the process goes on. This is perhaps easier to understand if we imagine that the air comes through the coil in gusts, and we notice what happens to each succeeding gust. The first comes down, expands, cools, and ascends, thereby cooling the second gust as it comes down. The second, then, after expansion, will be cooler than the first was. That, in its turn, will cool the third, and so the third after expansion will be cooler than the second. And that will go on, each succeeding gust being cooler than the one before, and although the flow of air is continuous, and not in gusts, the result is just the same. It goes on getting cooler and cooler until at last the air comes out in its liquid form. This liquid collects in a little chamber formed at the bottom of the vessel which contains the coil, and can be drawn off when desired. Air in its liquid state looks very much like water. In fact, it is difficult to get chance observers to believe that it is not water. It boils at a temperature far below the freezing point of water, so that liquid air, if placed in a cup made of ice, will boil furiously. Ice is so much the hotter that it behaves towards liquid air as a very hot fire does to water. The feature of the above machine, it will be noticed, is that no cooling water is required, as in the refrigerating machine, although the principle of the two is the same. The coil is the condenser, and the vessel in which it is enclosed is the evaporator, and so the cold air produced by the process in the evaporator cools the coil of the condenser. Thus it is self-intensive, as the makers call it. Hydrogen can be liquefied in a similar machine, except that it needs a little preliminary cooling with liquid air. Liquid hydrogen is the coolest thing known, approaching the region of absolute zero. And now we can turn to the wonderful discoveries which have followed upon the manufacture of liquid air. To make the story complete, we need to go back to the time of Priestley and Cavendish, early in the last century. They investigated the atmosphere and showed that it consisted of oxygen and nitrogen in certain invariable proportions, with, under certain conditions, a small portion of carbonic acid. These facts were so well authenticated, and they seemed to explain everything so satisfactorily, that it was quite thought almost up to the end of the 19th century that there was nothing more to learn about the atmosphere. Nevertheless, there was an idea in the minds of some scientists that there must be another group of elements somewhere, the existence of which was then undiscovered, but it was never dreamed that these were in the air. Soon after the weights of the atoms had been found, a medical student named Prout, in an anonymous essay, called attention to the fact that there were curious numerical relationships between them. Speculation on the subject went on for many years, until in 1865 the great Russian chemist Mendeleev published his conclusions. He had arranged the elements in the form of a table in the order of their atomic weights. The table consisted of 12 rows of names forming 8 vertical columns, and the remarkable thing was that all those elements which fell into any particular column, although their atomic weights were very widely different, had similar properties. This enabled him to predict the discovery of certain new elements, for the table contained a number of blank spaces. 3 elements have been found since, and their atomic weights and properties are just such as to fill 3 of the blank spaces. One blank space, it is thought, may be filled someday by the gas coronium, which like helium has been discovered in the Sun, but unlike it has not yet been detected here. When it is, there is the place in the table which it may fill. The table then commenced with what is called Group 1, but for reasons too complicated to explain here, it appeared as if there must be a group before that, a group the chief characteristic of which would be the inactivity of the elements included in it. These were expected to be of various atomic weights, but these weights, it was anticipated, would so occur in the intervals between the others so that they would all fall into a new column to the left of Group 1. In the year 1892, Lord Rayleigh was investigating the question of the density of a number of different gases, including, so it happened, nitrogen. Now there are several ways of procuring nitrogen. One is to get it from the atmosphere by ridding it of the oxygen with which it is normally mixed. Another way is to split up some compound, such as ammonia, of which it forms a part, in such way as to catch the nitrogen and leave the other elements with which it was combined elsewhere. Lord Rayleigh tried both ways, and he found that the nitrogen from the atmosphere was denser than that derived from ammonia. Sir William Ramsay then carried the matter a step further. He heated atmospheric nitrogen in the presence of magnesium, under which conditions some of the nitrogen combines with the latter element to form nitride of magnesium. That, it was found, made the remaining nitrogen denser still. The explanation seemed obvious. Suppose we imagine a mixture of sawdust and iron filings. It will be heavier than an equal quantity of pure sawdust. And if we contrive to take away some of the sawdust from the mixture, we shall find that what is left is heavier still when compared with an equal bulk of pure sawdust. For it is clear that as we take away sawdust, we thereby increase the proportion of the heavier iron filings, and so we make the mixture heavier. Applying a similar process of reasoning to these discoveries, the conviction grew that the nitrogen of the air was not pure, but that it had mixed with a small proportion of some other gas of greater density. They soon succeeded in isolating this denser gas, to which they gave the name of argon. Its atomic weight was found, and, wonderful to relate, it was such that argon fell into a new column to the left of Group 1, as had been anticipated. The discovery of argon was announced in 1894. The next year, Sir William Ramsay, investigating a gas which had been discovered locked up in the interstices of a mineral called clevite, was able to state that it was helium, the element which had been previously noticed by the spectroscope in the Sun. Like argon, it was found to be extremely inactive, and its atomic weight turned out to be such that it, too, fell into the zero group. In 1898, Professors Ramsay and Travers found 2 more gases in the air, krypton and neon, and a little later still there was found mixed with the krypton a further new gas, xenon. All of these had their atomic weights found and fell into that new column in the periodic table. But what has all this got to do with liquid air? The 2 subjects are closely related, for it is by liquid air machines that these rare gases are now obtained, and it was from liquid air that the last 3 were first discovered. For air, as we well know, is a mixture of gases, and when extreme cold and pressure are applied, these gases liquefy, each behaving according to its own nature. They do not all liquefy at the same time, nor, on being relieved from pressure and heated, do all evaporate again at the same temperature. Although they emerge from the liquid air machine in the form of a single liquid, it is really a mixture of liquids, each with its own boiling point. In an earlier chapter, we saw how petroleum can be separated into its various constituents, such as petrol, by fractional distillation, advantage being taken of the difference in the boiling point of the various fractions. The boiling point of a liquid is, of course, the temperature at which it turns freely into vapor, and just as petroleum, when heated, first gives off cymogene, next rhylogene, then petrol, benzene, kerosene, and so on in the order named, so liquid air, when it is evaporate, gives off its different constituents in order. Nitrogen, oxygen, argon, helium, krypton, neon, and xenon can all be separated each from the others in this way, by fractional distillation. The heat from the surrounding objects is allowed to get at the liquid, and the gases are then given off in the order of their boiling points. and thus we see how the mechanical production of cold has assisted in the pursuit of pure science. The newly found gases are not of any great use at present. They are so inactive that possibly they never will be, with one exception, and that is neon. If an electric discharge be made to pass through a tube filled with this gas, a beautiful glow is the result, and it is just possible that neon tubes may become the electric light of the future. That is only a prediction, however, and a hesitating one at that. The inactive elements may become of value in explosives. We have seen how important nitrogen is in these dangerous substances, the chief feature of which is their instability, their readiness, that is, to change into something else, which instability is due to the reluctance with which nitrogen enters into them. Now nitrogen, though inactive, is much less so than these others, and if a way should ever be found of inducing them to enter into a compound, that compound will probably be an extremely powerful explosive. End of section 5.
Section 6 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arvindh Sundar from arvindsundar.com. Marvels of Scientific Invention by Thomas W. Corbin. Scientific Inventions at Sea. The safety of our fellow creatures has always been a strong stimulus to our inventive faculties. The occurrence of a bad railway accident, and roughly its nature, can be inferred from the files of the Patent Office, for such an event brings men's thoughts to devising ways and means of preventing a recurrence, and an avalanche of such inventions descends upon the Patent Department in consequence. In like manner, a particularly distressing accident to a lifeboat some years ago brought out many inventions for the improvement of those romantic craft. Many of the inventions which arise under these conditions are, of course, utterly worthless, but some of them come to stay. It is not surprising, therefore, when we think of the almost innumerable wrecks which happen, even with modern shipping, that human ingenuity has been extremely busy in devising ways for bringing more of safety and less of risk into the lives of those who go down to the sea in ships. Of these, perhaps none is more fascinating than the modern lighthouse, with its tall tower, its brightly flashing light, standing undisturbed in the wildest storm, quietly and persistently sending forth its guiding rays, no matter how the elements may be buffeting it. There is something specially attractive in this perfect embodiment of quiet strength and devotion to duty. Of course, its origin is very ancient. One of the earliest inventions, no doubt, was the bright thought of a very primitive man who lit a fire on a hill to serve as a guide to some belated friends out in their fishing canoes. From some such beginning, the modern lighthouse, a magnificent product of the science of civil engineering and the science of optics, has arisen. Of the difficulties encountered in the construction of lighthouse towers on outlying rocks, much has been written. The historic Eddystone, for example, has quite a voluminous literature of its own. Of the light itself, however, much less is known. It will be interesting first to note the different purposes for which a light may be required, and then see how the apparatus of the lighthouse is made to serve these purposes. There is the making light, perched, if possible, upon some high eminence, deriving its name from the fact that the sailor sights it as he is making the land. Vessels approaching England from the southwest by night first see the light at the Lizard. The transatlantic vessels know they are approaching land by catching sight of the Fastnet Rock light off the coast of Ireland. Cape Race light serves in the same way for those about to enter the St. Lawrence, and Navesink for the entrance to New York Harbor. All such as these have to be of the greatest power practicable, so that they may be visible not only at the longest possible distance, but also under unfavorable conditions, such as haze and slight fog. No light, of course, can penetrate thick fog, but in light fog and haze a powerful light can be seen at considerable distances. For the same reason, these lights must be high up, or the curvature of the ocean surface will limit their range. A light elevated 100 feet above the sea level will be visible nearly 16 miles away, but if only 50 feet up, it will be invisible at 13 miles. To be seen 40 miles away, it must be as high as 1,000 feet. But then again, height is in some cases a disadvantage, for sometimes fog hovers a little distance above the sea, while below it the air is clear, and the higher a light may be, the more likely is it to have its lantern immersed in a floating cloud of fog. Many readers familiar with the south coast of Britain will remember that the light which used to show on the summit of Beachy Head is there no more, but has been replaced by a tower at the foot of the cliffs, the reason being that it may be below the clouds of fog which are prevalent at that point. But the mention of Beachy Head introduces us to another class of lights, known as coasting lights, since they are intended to lead the mariner on from point to point along a coast. It will be seen at once that in many cases they do not need to be visible at such great distances as the making lights. When the mariner has sighted the lizard, for example, he knows where he is. In order that he may learn that important fact as soon as possible, it is desirable that the light should have the greatest possible range. But having thus located himself, when he begins to feel his way along the English Channel, he is guided by the coasting lights, and so long as they are of such range that he will never be out of sight of one or two of them, that will be sufficient. Thus, the Beachy Head light, in its present low position, has a sufficient range for its purpose, with the added advantage of more freedom from obscuration by fog. Thus, we see how the local conditions and the purpose of each particular light have to be taken into consideration in determining its position and power. The Eddystone, again, is an example of a further class. It simply serves to denote the position of a group of dangerous rocks. Its function is not so much guidance, although no doubt it often serves for that, but for warning. The lizard light beckons the oncoming ship to the safety of the English Channel. The Eddystone warns it away from danger. The latter, therefore, and similar lights are warning lights. Right at the entrance of the English Channel, that greatest of all highways for shipping, there lie the Scilly Isles. This group comprises some few islands of fair size from which we draw those plentiful supplies of beautiful spring flowers. But it also includes a large number of rocky islets which have sent many a strong ship to its doom. On one of these islets, therefore, the Bishop's Rock, there now stands a very powerful light which exemplifies many whose purpose is the double one of welcoming the mariner as he approaches our shores and at the same time warning him of a local danger. Such are both making and warning lights. Of no less importance, though less impressive, are the guiding lights, which guide the ships into and out of harbors and through narrow channels. These are generally arranged in pairs, one of the pair being a little way behind and above the other. Thus, when the sailor sees them both, one exactly over the other, he knows he is on the right course. Sometimes, lighthouses have subsidiary lights as well as the main light, to mark a passage between two dangers, or to give warning of some danger. The subsidiary lights are often colored, and they are generally sectors, showing not all around a complete circle, or even a considerable portion of one, but just in one certain direction. They are generally shown from a window in the tower lower down below the main light. Finally, it is important to remember that every light must be distinguishable from its neighbors. Hence, every one in any given locality has a different character from all the others. This character is given to it by means of flashes. Instead of showing, as the primitive lights did, a steady light, the modern lighthouse exhibits a series of flashes, the duration of which, together with the intervals between, give it its distinctive character. This flashing arrangement has a further advantage over the steady light. Each flash can be made more powerful than a steady light could be, but more of that later. The actual source of light varies with circumstances. The electric arc is, as we all know, a very powerful light. In fact, it can be made the most powerful of all, but its light is decidedly bluish. Now the time when a light is most of all needed is when the weather is thick. Fogs varying from a slight haze to a thick pall of darkness are very common occurrence, and the lighthouse must be able as far as possible to penetrate them. As a matter of fact, clean fog, such as one gets at sea, is not by any means opaque. The black fogs of the great cities are another matter, but they are not the sort which afflict the mariner. On a foggy day in the open country or by the sea, it is often particularly light. Indeed, the light is of a peculiarly diffuse nature, which gives a nice even illumination to everything. Thus, we see the fog is really transparent, but it diffuses the light. It does not stop the light rays, but simply bends them about and scatters them in all directions. Thus, we can see nothing through the fog, yet a flood of light reaches us through it. In its effect, it is like that crinkled glass which is often used for partitions between rooms, which lets the light through, but which cannot be seen through. We see, then, that the effect which a fog produces is mainly to refract the light rays. Each little drop of water, for it must be remembered that fog is myriads of tiny drops of liquid, it is not vapor, acts like a minute lens, and bends the rays which pass through it. And the more blue a ray is, the more it is bent. On the contrary, the more red it is, the less is it bent. When a beam of light is analyzed in the spectroscope, the red rays are bent least and the blue rays most, so that the red rays fall at one end of the spectrum and the blue at the other. Now we only see a thing when light rays proceeding from every part of it fall straight, or nearly so, upon our eyes. Consequently, since red rays are bent and scattered by the fog less than the blue rays are, a red light will be more easily seen through a fog than a blue one. It might seem from this that a red glass put in front of a light would make it better for this purpose, but that is not the case, for the simple reason that filtering the light through red glass does not really make it any redder than it was before. It simply makes it look redder by extracting from the original light all except the red. But a source of light which is naturally reddish is so because it is more plentifully endowed with red rays, while a bluish light, like the electric arc, is naturally deficient in red rays. Consequently, we should be inclined to expect from theory that the electric arc would not be a good light for a lighthouse, since it would lack penetrating power in foggy weather. Some readers may have noticed themselves, in towns where electric lights and gas lamps are in use near each other, that the latter, though relatively feebler under normal conditions, seem to give more light in fog, and experiments show that this is really the case. So although there are some lighthouses with electric arc lights, that which is now believed to be the best is an oil lamp of special design, using a mantle of the Welsbach type. The oil is stored in strong steel reservoirs into which air is pumped by means of a pump not unlike those used to inflate bicycle tires. By this means, the pressure is maintained upon the oil of about 65 pounds per square inch. This forces the oil up a pipe and drives it in a jet into a vaporizer, a tube heated from the outside so that in it the oil is turned into gas. This gas then rises to the burner and heats the mantle, just as the gas does in the ordinary incandescent gaslight. Indeed, in the case of lights on the mainland near a town, the gas from the town main is often utilized. But this simple arrangement for using vaporized oil, as will readily be seen, can be employed anywhere. A little of the gas produced is led through a branch pipe and burned to heat the vaporizer. To start the apparatus, the vaporizer is heated with a little methylated spirit. Thus everything is quite self-contained and so simple that there is little to get out of order. The largest size of lamp will give 2400 candle power, with an expenditure of 2 1/4 pints of oil per hour, just common oil too, of the kind used with ordinary wick lamps. Having got a source of powerful light, the next thing is to collect that light and throw it in the direction required. For the light proceeds from the lamp in all directions, practically, and much of it would be entirely wasted could it not be collected and guided in the required direction. The earliest attempt at this was to use a reflector of bright polished metal. In the most improved form, these were made to the peculiar curve known as a parabola. This is a curve obtained by cutting a cone in a certain way, wherefore it is one of the conic sections, and its particular appropriateness for this work resides in the fact that if a light be placed at a certain point known as the focus, all the diverging rays which fall upon the reflector will be reflected in the same direction, parallel to each other. An ordinary spherical mirror would reflect them either back to the lamp or in diverging directions. At any distance, the beam from the parabolic reflector will be more intense than that from the spherical one, since the rays will be closer together. But even with the parabolic one, there is some diffusion, for the simple reason that whereas the focus is a mathematical point, position without magnitude, the most concentrated form of light known has a considerable magnitude. Hence, the rays proceeding from the center of the mantle are reflected as per the theory, but those from the outlying parts of it are somewhat diffused. This difficulty cannot possibly be overcome, and hence even in the finest examples of lighthouse architecture, the flashes are not quite sharp and clear-cut. There is a central moment, so to speak, wherein the flash is almost blinding in its intensity, but it is preceded by a period of growing brightness and succeeded by one of decreasing light. In the modern apparatus, however, metallic mirrors are entirely dispensed with, their place being taken by reflecting prisms of glass. The metallic ones had to be continually rubbed to keep them clean, and this soon dulled their brightness, while the glass prisms need only to be wiped carefully, which operation has little effect upon their surface. It may come as a surprise to some that reflecting prisms are possible. The idea of refraction through a prism is quite familiar. Such forms the essential principle of the spectroscope. Refraction is explained to every schoolchild in order to account for the rainbow. But reflection by a piece of the clearest glass seems a contradiction in terms, almost. Yet, it is only a question of shape. In some prisms, the light is simply bent as it passes through. In others, it is bent twice, so that it leaves the prism just as if it had been reflected off a mirror. Both devices are used in the lighthouse. Let us see how they are combined so as to perform the work to be done. Take first of all the case of a light upon an isolated rock where the warning is needed equally all around. All that is necessary here is to pick up those rays which, if left to themselves, would fall upon the water near the foot of the tower, and those which would waste themselves skywards, and then to gather all the rays into several bundles or beams. We will suppose a simple case in which the light is supposed to give flashes at regular intervals. We are in the topmost room of the lighthouse, the lantern as it is called. In the center there stands the murette or pedestal. In this, several columns support a circular platform on the top of which there moves what we might call a turntable, which in turn bears a frame of gunmetal into which are fitted a maze of glass bars, triangular in section and curved to form concentric circles. The whole structure, possibly, is of great size. From the floor to the platform is as high as an ordinary man. Indeed, around the turntable there is a gallery which forms a roof over our heads, so that it is only after mounting some iron steps into this gallery that we are able to examine the glass part. As we ascend, we notice that the walls of the chamber as far up as the gallery are formed of iron plates, while above that there is a metal framework filled in with glass panes, and above all a dome-shaped roof. Having reached the platform, we proceed to examine the glass, and we find that the metal framework forms a cage with 4 sides, each approximately flat, but really slightly spherical. Each of these sides is called a panel. In the center of each is the lens. Peeping through the interstices between the prisms, we perceive that the lamp is inside the structure, exactly in the center, so that its light shines directly through the central lens or bull's-eye. Around this bull's-eye forming refracting prisms. Around this again are more bars in the form of segments, which together form circles, some being refracting prisms and others reflecting prisms. All the light rays from the lamp which fall on any one prism are deflected, so that they proceed approximately in the same direction. Those prisms in the upper part lay hold of the rays which would otherwise go up into the sky. Those at the bottom collect those which would fall near the foot of the tower, so scarcely any are lost. But for the fact that the lamp itself is comparatively large and not a theoretical point, as already explained, the beam from this panel would be perfectly straight, parallel, and of uniform density everywhere. As it is, it widens slightly as it proceeds, but, practically speaking, we might call it a solid beam of light. Each of the panels sends forth such a beam so that they strike out in 4 directions from the central lamp, much as 4 spokes from the hub of a wheel. Then, descending once more to the floor from which we started, we see that among the columns there is a large clockwork arrangement, the purpose of which is to drive round the turntable and all that it carries. In the language of the lighthouse engineer, the optical apparatus, or more briefly, the apparatus. And as this turns, the radiating beams of light sweep out round the horizon and in succession strike into the eyes of any mariner who may be within range. Each time a beam strikes him, he sees a flash. If the apparatus revolves once a minute, he will see 4 flashes every minute, 1 from each panel. Let us consider, then, the advantages of this wonderful mechanism with its cunning arrangement of prisms. It is these latter, of course, which are the important thing. The rest, the mechanical portion, is simply for the purpose of holding them and turning them at the proper speed. In the first place, the contrivance gives us flashes instead of a steady light. It gives the lighthouse its character. Then again, it enhances the brightness of the light. Instead of shining all around, the light is concentrated in 4 special directions, and the light which would be wasted upwards or downwards is saved and brought into use. But suppose that the lighthouse we are considering be near the shore, so that there is no need for it to throw any light in the landward direction. Then we should see inside the revolving framework with its prisms a fixed frame with reflecting prisms which would catch any rays going from the lamp in the direction of the land and simply hurl them, as it were, back into the flame. Thus, the intensity of the flame becomes increased by those rays thrown back which would else have been wasted. Or suppose that the character of the light is such that the flashes have to be at irregular intervals. Then the framework, instead of being symmetrically 4-sided, would be of an irregular shape. And that brings us to a beautiful feature of the mechanism of the apparatus. We have been discussing a 4-panel arrangement. Suppose that we were to reduce it to 3, then since all the light would be concentrated into 3 beams instead of 4, each beam would be more intense. We should thereby have the increased range of our apparatus without any increase in the cost of oil, for nothing, as it were. But to get the same number of flashes per minute, we should have to drive it around so much faster. But increased speed means increased burden on the keepers who have to wind up the heavy weights which operate the clockwork. So there is a limit to the speed which can be attained. But if friction can be almost eliminated, the apparatus can revolve at a high speed without throwing undue burden upon the men. But how can friction thus be got rid of? Messrs. Chance Brothers, the great lighthouse constructors of Birmingham, have done it almost entirely by floating the apparatus on mercury. The turntable has on its underside a large ring which nearly fits a cast iron trough on the top of the pedestal. In this trough there is mercury, so that upon the liquid metal the apparatus floats as if upon a circular raft. The table with its lenses, prisms, and other fittings may weigh 6 or 7 tons, yet it can be pushed around by one finger. The various sizes of optical apparatus are known as orders. One of the first order has a focal distance of 920 millimeters. This means that there is that distance between the center of the lamp and the bullseye. They descend by successive stages down to the 6th order, with a focal distance of 150 millimeters, while the most important lights are of an order superior even to the so-called first, termed the hyperradial, the focal distance of which is 1330 millimeters. A recent example of a hyperradial light is at the well-known Cape Race in Newfoundland. It revolves once every 30 seconds, giving a flash of 3 seconds every 7.5 seconds. The optical apparatus weighs 7 tons. Most lighthouses are fitted with fog signals of some kind, which have a distinctive character the same as the lights. Some are horns blown at intervals by compressed air, often obtained from a special air pump driven by an oil engine. Another thing is to let off detonators at stated intervals. But perhaps the most interesting of all is the submarine telephone. The trouble with audible signals is that they are apt to vary as the conditions of the atmosphere change. For, strange though it may appear, the air, which is the natural medium by which sounds are carried to our ears, is really a very bad substance for the purpose. Water is much superior. A swimmer who cares to try the experiment of lying upon the water with his ears immersed, while a friend beats a gong under the water some distance off, will be astounded at the result. So many modern ships are fitted with underwater ears, waterproof telephone receivers really. One is fixed each side of the vessel, the wires from them being led to the telephone receivers near the bridge. Many lighthouses and lightships in like manner are fitted with underwater bells which can be rung at intervals. The sounds so conveyed through the water are always the same. Atmospheric or similar changes have no effect upon them, and, moreover, the officer can tell which side of his ship the bell is. If it be on his port side, it sounds louder in his port telephone and vice versa. By turning his ship until he hears them equally, he knows that he is pointing directly to or from the bell. Thus, if the bell belong to a warning light, he can steer confidently right away from the danger even in the thickest fog. But science has not only provided the mariner with lights of marvelous power and of strange distinctive characters, and reliable sound signals for foggy weather, it has also found him a reliable compass, but that is worthy of a chapter to itself. End of section 6. Recording by Arvindh Sundar from arvindsundar.com.
Section 7 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. CORBIN. The Gyro-Compass. The magnetic compass has been for ages the mariner's guide over the trackless waters. In cloudy weather, it has been his only means of knowing the direction in which his craft was heading. Indeed, it is not too much to say that the maritime compass of the world was based upon the behavior of that little piece of magnetized steel. It has always, however, been subject to certain faults. To commence with, it points not to the geographical north, but to the magnetic pole. It points some distance from the geographical pole, and one moreover which is not quite permanent. The fact that the magnetic pole varies its position is impressively shown by the fact that a special department at Greenwich Observatory is continually employed by the aid of delicate self-recording instruments, watching and setting down its fluctuations. And the premier observatory of the world, it should be remembered, exists primarily not in the interests of pure science, but as the department of the British Admiralty in order to study matters of interest to navigation. Thus we have testimony to the importance of these little vagaries on the part of the magnetic compass. But in addition to these inherent faults, there is a new source of error in the magnetic compass which man has introduced himself by making his ships of iron instead of wood. Every ship of the present day is a huge magnet. A piece of iron left in the same position for a length of time becomes polarized, which is to say that it acquires the properties of a magnet, and two magnets always exert an influence upon each other. Consequently, the ship, after lying for perhaps a year in one position during the period of building, becomes itself magnetic and interferes with its own compass. Then again, our methods of ship construction aggravate this trouble. It is believed that every molecule of iron is itself a minute magnet with the north and south pole of its own. These, lying in confusion in the mass of unmagnetized iron, neutralize each other, so that the mass taken as a whole does not exhibit any magnetic power. But if by some means the whole of the millions of molecules can be set the same way, with all their north poles in one direction and their south poles in the opposite direction, then they will all act together. Instead of neutralizing each other, they will then help each other, and under those conditions, the mass of iron will possess that peculiar power which is distinctive of a magnet. So long as a piece of iron is left in the same position, the magnetism of the earth is thus acting upon the molecules. Just as it tends to place the compass needle north and south, so it does with every molecule in the iron mass. And if, while lying still, the iron be hammered, the shaking of the molecules due to the hammering loosens them, as it were, and assists the earth's power in pulling them into position. One has only then to watch the riveting up of a ship, and to see the vigorous way in which the riveters wield their hammers, to realize when the thousands or even millions of rivets have all been finished, the material of that ship will have had the very best possible chance of becoming magnetic. To make matters worse still, ships are often loaded with great weights of iron among their cargo. That too may affect the compass. On warships, there are the heavy guns, each weighing with its turret hundreds of tons, and they move so that their effect upon the compass is not always the same, but may vary from time to time. And finally, one may mention the electrical machinery in a modern ship consisting largely of powerful magnets. Altogether then, it is not surprising that the old magnetic compass is somewhat unreliable. It has to be coaxed into doing its duty. Pieces of iron and magnets have to be disposed about it to counteract these disturbing influences with which it is surrounded. Before a voyage, experts have to come on board to adjust the compasses, and even then there is reason to believe that the instrument sometimes plays the ship false. It is not to be wondered at, then, that the naval authorities in particular throughout the world have welcomed the advent of a new compass, which appears to possess none of these drawbacks. It points to the geographical north, to the actual pivot, if one may so speak, upon which the Earth turns. It is non-magnetic, so that the presence of iron or magnets even in its immediate neighbourhood has little or no effect upon it. On the other hand, it has to be driven by a current of electricity, and it seems just possible that in some great crisis it might fail. Although every provision is made for alternative sources of supply in case of one failing, and there is always the possibility of falling back upon the old magnetic compass should the new one go wrong. In principle, the improved compass is like its older brother, simplicity itself. The latter is but a small piece of iron magnetized. The former is nothing more than a spinning top. It is rather strange that although the spinning object has been a familiar toy for years, and that moreover its behavior has been the subject of investigation by some very eminent scientific men, it is only of recent years that its principles have been put to practical use. Everyone is familiar with the fact that a round block of wood will support itself upon a comparatively tall peg so long as it is rapidly rotating. And that is but one of the curious things which a rotating body will do. For example, imagine a wheel mounted upon an axle, the ends of which are supported inside a ring, while the ring again is supported on pivots between the two prongs of a fork, the fork being free to swivel round in a socket. The wheel is then free to move in any direction. Technically, it is said to have 3 degrees of freedom. It can spin round, its axle can turn over and over, with the pivoted ring inside which it is fixed, while it can also swing round and round as the fork turns in its socket. Assuming that the joints are all perfectly free, that the pivots move in their sockets with perfect freedom, which of course they do not, then a wheel so mounted could move in any direction under the influence of any force that might act upon it. Now, a wheel so mounted, if left alone, remains in precisely the same position so long as it goes on rotating. If it be turning sufficiently quickly, its tendency to remain will be strong enough to overcome the friction of any ordinarily well-made instrument. Consequently, a wheel of that description has been used to demonstrate the rotation of the Earth, it remaining still, except of course for its rotating movement, while the Earth has moved under it. Could we entirely eliminate the effects of friction that might be used as a compass, for it could be set, say with its axle pointing north and south, at the commencement of the voyage, and it would remain so despite all the evolutions through which the ship might go. But there is a better scheme even than that, based upon the peculiar behavior of a revolving wheel when it has only 2 degrees of freedom. Suppose that we dispense with the ring, employed in the previous arrangement, pivoting the ends of the axle between the prongs of the fork. The wheel is then free to rotate, and its axle can slew round through a complete circle by the turning of the fork in its socket, but there can be no tilting of the axle. Being thus deprived of one of its movements, the gyroscope with 3 degrees becomes a gyroscope with 2 degrees of freedom, and in that form it supplies the need for an efficient and reliable compass. The secret of the whole thing is the curious fact that a gyroscope with 2 degrees of freedom exhibits a keen desire to place its axis parallel with the axis of the Earth. Owing to the shape of the Earth, a device such as has been described, with its fork standing up vertically, cannot possibly have its axis really parallel with that of the Earth, except on the equator. Still, it gets as nearly parallel as possible. To be scientifically accurate, we ought to say that it places its own axis in the same plane as that of the Earth. To understand this, we need to realize that all movement is relative. In ordinary language, when we say a thing is still, we mean that it is still in relation to the surface of the Earth, But since the Earth is moving, the stillest thing, apparently, is really travelling at enormous speed. St. Paul's Cathedral in London, or a tall skyscraper in New York, would usually be regarded as supreme instances of immobility. It would be hard to find better examples of stationariness as we ordinarily look at things. Each stands firm and strong upon a horizontal base, yet each is really turning a somersault every 24 hours. The plateau upon which St. Paul's stands, though it seems still and motionless beneath our feet, is continually tilting. Its eastern edge is continually going downwards, and its western edge upwards as the Earth performs its daily spin. It is only a north and south line which does not share in some degree this continual tilting action. Every plane, large or small, so long as it remains horizontal, is being tilted thus, down at the eastern edge and up at the western. And the plane in which the axle of a gyroscope with 2 degrees is free to move is a horizontal plane. Owing to its being held between the prongs of the fork, while it can swing round to point north, south, east or west, or towards any point between them, it cannot deviate from the horizontal plane. Therefore, such axle is always being tilted by the motion of the Earth, except when it happens to be lying exactly north and south. Now, for a reason which is too complex to go into here, a gyroscope strongly objects to having its axle tilted in this manner. If it be compelled by superior force to submit to tilting, it tries to wrench itself round sideways. Anyone who has a gyroscope top and cares to try the experiment will feel this action quite easily. Hold the spinning top in your hand and turn it over so as to tilt the axle, when it will, if you are not careful, twist itself out of your grasp. So a gyroscope of the kind we are considering, when the motion of the Earth tilts its axis, turns itself round in its socket until at last it reaches the north and south position, when the tilting and therefore the twisting ceases. Hence the axle of the gyroscope, if left to itself, the rotation of the wheel being maintained the while, will place itself in a north and south direction, and moreover it will keep in that direction. It will take some force to slew it round into any other, and if moved into any other by some extraneous means, it will restore itself to the old position again. Hence, a wheel thus arranged has all the attributes which we need for a mariner's compass. But unfortunately, there are mechanical difficulties in the way of using such a simple contrivance for that purpose. Chief of all these is the fact that it is not what engineers call dead beat. That means that it will not go to the proper position and then remain there quite still. Instead, it will first slightly overshoot the mark, which being followed by the reverse action, it will come back and overshoot it just as far in the opposite direction. Instead, therefore, of a steady pointing, always in the same direction precisely, it will oscillate more or less, the exact north and south line being the mean or average position, the center of the oscillations. It would of course be possible to damp this, to apply a brake as it were, if the apparatus were to remain stationary. For example, if the whole concern were immersed in water, the resistance of the liquid would restrain any quick movement of the axle, yet it would not prevent it from slowly finding its true position. Thus, the oscillations would be reduced to such a small range as to be, for practical purposes, negligible. But the drawback to a device of that kind, applied to a gyroscope on board ship, would be that the axle would be carried round to some extent every time the ship turned. As she changed direction, it would more or less carry round the water with it. That in turn would carry the gyroscope, and so the direction of the latter would be for a time untrue. It would in course of time regain its accuracy, but in the meantime it would be leading the ship astray. Consequently, the application of this in itself wonderfully simple idea to this extremely important purpose was accompanied with a difficulty which was for a long time insuperable. But all was overcome at last by the genius of Dr. Anschutz of Hamburg, whose firm were the first to turn out the practicable article. Taking advantage of another movement of the gyroscope, when arranged as has been described, and using the revolving wheel itself as a centrifugal fan, he was able to make the wheel blow air against itself, as it were, when in any position other than north and south. Thus, if it deviates towards the east, this jet of air tends to blow it back. If it turns westwards, the jet again comes into operation, tending to bring the airing gyro back to its proper place. and so the tendency to oscillate is checked. The finished instrument, as it is installed on the latest warships, is of course quite different in detail from the simple contrivance which we have been considering so far, although it is the same precisely in principle. The essential part is a heavy metal wheel, combined with which is an electric motor, which keeps it rotating at a speed of 20,000 or so times per minute. The bearings of the wheel are supported upon a metal ring, which floats upon the surface of a trough of mercury. Thus, friction is brought down almost to the irreducible minimum. The only place where the wheel and its support touch anything solid is at one delicately made pivot, which serves to keep the floating mechanism in the center of the mercury basin, and to prevent it from rubbing against the side of it. The current which drives the motor reaches it through this pivot and leaves through the mercury. Thus arranged, although the floating part is of considerable weight, a very slight force indeed is enough to move it. While looking at it the other way, we can see that the ship might turn rapidly, to right or to left, carrying round the mercury bowl with it, without turning the floating part at all. Thus, the gyroscopic action is very free indeed, to exercise its function of keeping the contrivance pointing always in the one way. The float has mounted upon it a compass card, much like that of the ordinary magnetic instrument, and the sailor reads it in precisely the same way. To outward appearance, there is little essential difference. In one case, there is a magnet under the card to keep it still, in the other, there is the float with the revolving wheel mounted upon it. It is customary to have one master compass of this kind on a ship with an electrical repeater in each of the steering positions. As the master turns in its casing, it sends a rapid series of currents to all the others, causing them to turn in unison with it. The master is fitted in some safe part of the ship where it is least likely to be the victim of any accidental damage. End of section 7.
Chapter 8 of Marvels of Scientific Invention by Thomas W. Corbin. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by garyleosmith. Marvels of Scientific Invention by Thomas W. Corbin. Chapter 8, Torpedoes and Submarine Mines. It is sad to think how much scientific skill and learning has, during the Great War, been devoted to killing people. It used to be thought that one day a great scientific invention would arise of such deadly power that forever afterwards war would be unthinkable. Its horrors would be such that all nations would shrink from it. That prophecy, however, has not been fulfilled, nor are there any signs of it. On the contrary, each scientific achievement in the realm of warfare is quickly countered by another, so much so that with all our science in the manufacture of weapons and our skill in using them, warfare in the 20th century is, if anything, less deadly in proportion to the numbers engaged than it used to be. There are, however, two weapons which in this war have reached a deadly efficiency, which they did not seem to possess before, and to which satisfactory antidotes have not yet appeared. These two are the submarine mine and the torpedo. The latter particularly had been a dismal failure previously, but as the weapon of the submarine it has now established itself. It is, however, only in connection with the submarine that it has achieved any measure of success, and as there are strong indications that very soon the submarine itself will be robbed of its terrors, it is quite likely that the reign of the torpedo will be brief. Although it has only just made itself felt seriously in warfare, the torpedo is a fairly old idea. In fact, we can trace the general idea of it back to very ancient times. The modern weapon, however, dates from the year 1864, when an Austrian inventor approached an English engineer named Whitehead with a request to take up his idea. Mr. Whitehead had at the time a works at Ufume on the Adriatic, and it was really his genius that developed the crude idea into a practicable invention. Thus there came into existence the Whitehead torpedo, now used in a great many navies, and also the Schwarzkopf, which may be regarded as the German variety of the same thing. Speaking generally, it may be described as a small automatic submarine boat. Externally, it naturally follows somewhat the lines of a fish, deriving its name from that curious fish which is able to give electric shocks from its snout. It likewise carries on its nose that appliance whereby it gives a shock, not electric, it's true, but equally deadly to anything which it may touch. Since no man-made mechanism can approach the marvelous action of a fish's fins and tail, the propulsion is achieved by a propeller like that of a steamboat, but of course on a very small scale. A single propeller, however, would tend to turn the torpedo over and over in the water, and so it has two, one behind the other, driven in opposite ways, so that the turning tendency of one is neutralized by that of the other. The blades of the propeller are, however, set in opposite ways, so that although rotating in different directions, they both push the torpedo along. Behind the propellers, again, there are rudders for steering. One steers to the right or left, as does that of an ordinary ship, while two others are so placed that they can steer upwards or downwards. So there we have the general picture of the outside, a smooth, fish-like body with a sting in its nose, propellers at the rear to drive it along, and rudders to guide it. Inside are various chambers. One contains the explosive which blows up when the nose strikes something. This head, as it is termed, is detachable, so that it can be left off until it is really required for war. The peace head, which is of the same size, shape, and weight as the warhead, is what the torpedo carries during its earlier career. With this, it can be tried and tested in safety, the warhead being substituted when the real business of the torpedo begins. Another chamber contains the compressed air which furnishes the motive power. This also serves to give buoyancy. Another chamber again contains the engines, beautiful little things of the finest workmanship, almost exactly like the finest steam engine, but of course very small in comparison. In the early stages, the range of the torpedo was limited by the amount of compressed air which it could carry. At first sight, there seems no reason why any limit should be placed upon this, but in practice there are often limitations in engineering matters which are not apparent on the surface. For example, to increase the air chamber would mean enlarging the whole torpedo, calling for more propulsive power and larger engines, and these larger engines would call for more air, thus defeating the object in view. Forcing more air in by using a higher pressure in a similar way would necessitate a thicker chamber to resist the higher pressure. This would add weight, calling for more buoyancy. Thus, there seemed to be a practical limit beyond which it was impossible to go. The difficulty was overcome, however, in a very cunning way. When the engines have used some of the air and the store is somewhat exhausted, chemicals come into action which generate heat, which is imparted to the air which is left. This heat expands the air, producing in effect a larger supply of it, and enabling the torpedo to make a longer journey. Steering in a horizontal direction, that is to say, to left or right, is done by a gyroscope. The action of a rotating wheel is discussed in the last chapter, and it is not necessary here to say more than this. A rotating wheel always tries to keep its axle pointed in the same direction. Just at the moment of starting such a wheel is set going inside a torpedo, its arrangement is such that, should the torpedo swerve to the left, the gyroscope operates the rudder and steers it back. In the same way, if it tends to turn to the right, the ever-watchful gyroscope brings it to its true course once more. The effect of the gyroscope, therefore, acting upon the rudder, is to keep the torpedo faithfully to the direction upon which it is started. The up and down rudders are likewise controlled quite automatically, but in a different way. Their function clearly is to keep the thing at a certain uniform level. Without such control, a torpedo would be equally likely to jump out of the water altogether, or to go downwards vertically and bury its nose in the mud. The depth at which it is to move is determined beforehand. Certain necessary adjustments are made, and the torpedo then pursues its even way, neither coming to the surface nor driving beneath its target. For this purpose there is first of all a hydrostatic valve. This little appliance, which is open to the action of the water, responds to changes in pressure. The pressure at any point underwater is exactly proportional to the depth. At 10 feet, for example, it is precisely 10 times what it is at 1 foot. So the hydrostatic valve is adjusted to set the rudder straight when the water pressure upon it is a certain amount. If then it dives downwards, the pressure increases and the valve operates the rudders so as to bring it upwards, while if it rises too high, the decrease of pressure causes it to be guided downwards. This action, however, is too sudden and violent, so that with it alone the torpedo would proceed by leaps and bounds. After being low, it would come up too suddenly, overshoot the mark, only to be steered downwards again equally suddenly. The valve, therefore, is combined with a pendulum, whose actions tends to restrain these too sudden changes, with the result that under the influence of the two things combined, the torpedo keeps fairly well to an even course, only varying upwards or downwards to an extent which is negligible. Finally, there is an interesting little feature about the firing mechanism which merits a description. The actual firing is caused by the driving in of a little pin which projects at the nose of the torpedo. Suppose that in the process of pointing the torpedo and launching it upon its course, that pin were to be knocked accidentally. An awful disaster would result. It must be provided against, therefore, and the method adopted is beautiful in its certainty and simplicity. Normally, the firing pin is fixed by a screw so securely that no accidental firing is possible. There is, however, a little propeller-like object associated with it, which is driven round by the water as the torpedo is pushed through it, and this unscrews and thereby releases the pin. The little fan has to rotate a certain number of times before the pin is released, and it is quite impossible for this number to be accomplished before the torpedo has proceeded to a safe distance from the ship which fires it. On board the ship, therefore, and so long as it is near the ship, it is quite safe, but by the time it reaches its target, it is ready to explode. As far as is known, the foregoing description gives a true general description of the torpedoes now in use. Those of different powers may vary in detail, but broadly they are as just described. There are others, however. The Brennan, for instance, was once adopted and largely used by the British for harbor defense. This was controlled from the shore by wires. It was driven, so to speak, with wire reins, and thus guided it could fairly hunt down its prey, turning to right and to left as required. Of greater scientific interest, perhaps, still, is the Armour 1 wireless-controlled torpedo. This is the invention of two gentlemen, Messrs. Armstrong and Orling, whose first syllables combine to form the title of the torpedo. Of this, two very interesting features may be mentioned. Firstly, the wireless control. In the chapter on wireless telegraphy, there is described the coherer, a simple little apparatus which we might describe as a door which is opened by the waves which travel through the ether from the sending apparatus. Whenever the key of the sending apparatus is depressed, these waves travel forth, and when they fall upon the coherer, it opens. Normally the coherer is shut, but when acted upon by the incoming waves, it opens and lets through the current from a battery, which current can be caused to perform any duty which we may wish. Thus, ignoring the intermediate steps, we get this. Whenever the sending key is depressed, current flows through the coherer and performs whatever duty is set before it. And now picture to yourself a tooth wheel with 4 teeth. A catch normally holds one of the teeth, but when the catch is lifted for a moment, it lets that tooth slip and the next one is caught. At every lifting of the catch, the wheel turns a quarter of a turn. Then imagine that catch is operated by an electromagnet energized by the current which passes through the coherer. We see then that every time the sending key is depressed, the wheel turns a quarter turn. Attached to the wheel is a little crank which turns with it, and the pin of this crank fits in a slot in the end of a bar like the tiller of a boat. Suppose that, to commence with, the tiller is straight, so as to steer the boat straight. Depress the key, the wheel turns a quarter turn, and the tiller is set so as to steer to one side, say the left. Another pressure upon the key and a second quarter turn brings the tiller straight again. Yet another pressure, another quarter turn, and the tiller is steering to the right. Thus, by simply depressing the key the correct number of times, the torpedo can be made to travel in any desired direction. The second ingenious feature of this weapon is the means by which it is made visible to the man who is controlling it from the shore or ship. Probably the reason why these torpedoes are not used more is that the man who guides them is of necessity himself visible. He has to be posted somewhere where he can follow its course, or he has no idea how to steer it. Consequently, he would be an object for attack by the enemy. Such a torpedo would be useless in a submarine, for the submarine would need to come to the surface in order that the observer might get a sufficiently good view to be able to steer the torpedo, and we all know that when upon the surface a submarine is a very vulnerable craft. But that is by the way. The point is how to make the torpedo very clearly visible while it is still underwater. A short mast might be used, but that would be liable to be shot away. The inventor had a happy inspiration when he made it blow up a jet of water like a whale does. This jet is quite easy to see, yet no shot can destroy it. Compressed air blows up this telltale jet which the observer can see, and by its means he can guide the torpedo at will. A submarine mine may be regarded as a stationary torpedo. It consists of a metal case filled with a powerful charge of explosive, which floats harmlessly in the water until some unfortunate vessel strikes against it, when it blows up with sufficient force to make a hole in the stoutest ship. There are two classes of mine, one which is laid in peacetime to protect harbors and channels, and the other which is laid during actual warfare. The former are anchored in a more or less permanent way. The services of divers are used to place them in position. In some cases, they float well down in the water, out of the way of passing ships, but come up nearer the surface when needed. This result is achieved by having an anchor chain of such length that when fully extended, the mine floats a little way under the surface, just high enough to be struck by a passing ship, together with what is called an explosive link. The link is used to loop together two parts of the chain, and so in effect to reduce its length. Wires pass from the link to the shore, and when an electric current is sent along these wires, the link bursts asunder, liberates the chain, and the mine floats up to the full length of its chain. Another plan is to let the mines float high up always, but to fire them not by the touch of the ship, but by electricity from the shore. In this way, a safe channel is kept for friendly vessels, while an enemy can be destroyed. Necessarily, those mines which are hurriedly laid in wartime are very different from these. To be of much use, a mine must be concealed below the surface. If it floats upon the water, it will be visible and can be avoided, or, at all events, easily picked up. It is practically impossible to set a floating object at a certain depth in the water, except by anchoring it to another, heavier object, which will lie at the bottom. Therefore, mines have to be anchored in some way. But the sea varies in depth, so that the length of the anchor chain must be varied, or else some of the mines will be on the surface, thereby advertising the presence of a minefield, while others will be below the depth of even the biggest ship. In warfare, however, mines need to be laid quickly. There is no time to sound for the depth and then to adjust the length of the cable accordingly. Hence, the mine must be so made as to set itself correctly at a predetermined depth. Possibly some readers may think that such things might be made to float of themselves at the right depth. It is a fact, however, that a thing either floats upon the surface of the water or falls to the bottom. Water is practically incompressible, so that the water at the bottom of the sea is no heavier than that near the surface. The conditions which prevail in air and allow a balloon to float at any desired height do not apply. The only thing in this case is to have an anchor chain or rope of the right length. So let us picture a mine-laying ship steaming along, probably in the dead of night, surreptitiously laying mines in the hope that the enemy will run into them on the morrow. Along the deck of the ship are small railway lines, and on these lines stand what appear to be trains of small trucks, each truck having small wheels to run on, and each bearing a large round metal ball. As the ship travels along, the crew, handling these deadly things quite freely, as if they were innocent of any danger, propel them along to the stern, and at regular intervals push one overboard. That is all. The freedom with which the men handle them is not folly, for they are then quite harmless, nor need they trouble about the length of rope, for that adjusts itself. Just tumble the things overboard, and in due time they anchor themselves at the right depth and set themselves to the right condition for blowing up any ship which may get amongst them. The truck-like object upon wheels is not the mine itself. It is the sinker which lies at the bottom of the sea. The round ball which it bears is the mine, and the two are connected together by a wire rope. To commence with, this rope is coiled upon a drum in the sinker, which drum is either held tightly or is free to revolve according to the position of the catch. That catch is held open so that the drum is free by a weight at the end of a short rope. Let us assume that that rope is 10 feet long. Then, when the whole thing is tumbled into the water, the weight sinks first 10 feet below the sinker, which, being more bulky in proportion to its weight, follows downward more slowly. While sinking, the weight is pulled upon its rope and holding open that catch, so that the drum pays out its rope and the mine lies serenely upon the surface. As soon as the weight touches bottom, however, the pull on the short rope ceases. The catch grips the drum, no more rope is paid out, and the sinker, in settling down its last 10 feet, has to drag the mine down too. Thus, quite automatically, by what is really a beautifully simple arrangement, the mine becomes automatically anchored at a depth below the surface equal to the length of the short rope. By making that rope the desired length, the depth of the mine under the water can be fixed. There are various methods of firing these mines, all of which work perforce by the concussion of the ship itself. In some cases, the sudden tilting over causes an electric contact to be made and permits a battery in the mine to cause the explosion. Another way is to furnish the mine with projecting horns of soft metal, inside which are glass vessels containing chemicals. The ship, striking a horn, bends it, breaks the glass, and liberates the chemicals which cause the explosion. In the type of mine largely used by the British Navy, there is a projecting arm pivoted on the top of the mine and projecting from it horizontally. The mine itself rolls along the side of the passing ship, but the arm simply trails and scrapes along. Thus the mine turns in relation to the arm, and a trigger is thereby released which fires the mine. In this, to be noted, the ship only pulls the trigger, so to speak, and releases a hammer which does the work, just as the trigger of a gun releases the hammer. The motive force, which makes the hammer do its work when the trigger is pulled, is the pull on the anchor rope. That arrangement has a virtue which is not apparent at first sight. Since it is the pull on the anchor rope which actually fires the mine, it follows that if such a mine break away from its moorings, it instantly becomes harmless. Safety for the men who lay the mines is secured in several ways. One is by the use of a hydrostatic valve. The firing mechanism is locked until the pressure of water releases it, and that pressure does not exist until the mine is several feet under water. Another way is to seal up the firing mechanism with a soluble seal made of some substance such as sal ammoniac. The mine cannot then explode until it has been under water long enough for the seal to be melted. It now remains to relate how these mines are swept up and removed, yet there is very little really to tell, for the process is so exceedingly simple. So far as is generally known, no method has been found that is superior to the primitive plan of dragging a rope along between two ships so as to catch the anchor ropes. The vessels employed are usually of very light draft, so that they stand a good chance of passing over the mines themselves, and the rope used is as long as possible, so that a mine, if exploded by being caught in the loop of the rope, explodes so far away as to do no harm. When dragged to the surface, the mines are exploded from a distance by shots from a small gun, or even from a rifle. In the case of those mines which have horns, a blow from a bullet is enough to break the glass and cause explosion, and in all cases, mines seem sooner or later to succumb to a sharp blow. Thus they are destroyed by their own action at a safe distance from the sweepers. Accidents happen, however, and mine sweeping is no job for anyone but the bravest. It has been somewhat difficult to crowd a description of torpedoes and mines into the small space of one chapter, and so many details have had to be omitted. But the above descriptions give the broad general principles underlying practically all forms of these terrible weapons. This is the end of Chapter 8, recorded by garyleosmith, Dublin, Ohio.
Section 9 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Marie Neilson, Vancouver, BC. Marvels of Scientific Invention by Thomas W. Corbin. Gold Recovery. There has always been something very fascinating about gold. Even in ancient times it was prized above all other things, and apparently it was comparatively plentiful. It is estimated, for example, that King Solomon possessed over 4,000,000 pounds worth of it, while the little gift which the Queen of Sheba bought him was of the handsome value of 600,000 pounds, so that she too must have been plentifully supplied with it. Probably it was more easily come by in those days, owing to the richness of the primitive deposits, the best of which, perchance, have been worked out. In one respect gold differs from all other metals, with the single exception of platinum, which is scarcer still, in that it appears naturally as gold, not as ore. The little pieces of gold lie in the mine ready to be picked out, and so if the deposit in which it occurs be near the surface, and the particles be of any considerable size, they are sure to be found. A savage may be, and often is, very anxious to secure weapons and tools of iron, little knowing that the very ground which he stands is possibly of iron ore. He covets the single article of iron, and in some cases is willing to give much gold for it, or ivory, or some such treasure, while thousands or millions of tons of ore lie at his feet. Only he does not recognize it, nor would he know how to utilize it if he did. For iron, like all other metals except the two just referred to, is found naturally in combination with something else, generally oxygen, and the combination bears no resemblance at all to the metal. The red rust so familiar to us on iron is a combination of iron and oxygen, and is fairly typical of the kind of state in which iron is found in the earth. Nor would anyone recognize copper ore, lead ore, tin ore, or any of the ores any better than iron ore. All are difficult to recognize. It is said that the highest compliment that a Cornish miner, the finest metalliferous miners in the world, come from Cornwall, or are the product of Cornish influence. The highest compliment that such a man can pay to another is to say that he knows tin, meaning that he can tell tin ore when he sees it. Contrasted with these other metals, gold is easy to find. It does, it is true, under certain conditions, form chemical compounds with other things, as, for instance, in gold chloride, which is present in sea water, but it does not oxidize as the others do, and so when it is in the earth, it is in the bright yellow grains such as, if they be large enough, can easily be recognized at sight. And it is often found in beds of loose gravel, alluvial deposits, as they are termed. In such cases the gold is to be had simply for the picking up. Sometimes a lucky find occurs in the form of a big nugget, but more often the metal lies in tiny grains at long distances apart, so that a ton of gravel has to be sorted over to find a paltry ounce or so of gold. Yet so desired is it that gold will always fetch its price, and an ounce to the ton, even less, is sometimes worth getting. But in the early history of the world there were possibly particularly generous deposits with plenty of gold in good-sized pieces, and such would be quickly discovered and worked by primitive man. No doubt the chieftains of those days took much, if not all, of the gold that their people found, and more powerful chiefs and kings would, in turn, either by force or in trade, take it from the weaker, so that it is not surprising to learn that some of the mighty kings and potentates of long ago were well supplied with gold. Yet there are few things more useless. Its value in the first instance was probably entirely due to its beautiful color, and the fact that it does not easily tarnish. For this reason, coupled with the fact that it was by no means plentiful, men liked to deck themselves with it, not only adding to their beauty by doing so, but advertising to their fellows the fact that they were men of wealth, men who possessed what few others had, or at all events possessed it more abundantly. These three basic facts about gold, its beauty, its freedom from deterioration, and its comparative scarcity, give it its peculiar status among the commodities of commerce, in that for it, and for it alone, there is a continuous and universal demand. No gold mining company ever shut down its properties because of the falling off in the demand for gold. No one ever had to hawk gold about to find a purchaser. It is always saleable. And hence its value to humanity as the great medium of exchange. When a tailor wants bread, as has been pointed out by a great political economist, he does not go searching for a baker who happens to need a coat. If he did, he might starve before he found one. Instead, he gives his coat to anyone who needs one, no matter what his trade may be, taking gold in exchange. Then he goes with confidence to the baker, knowing full well that he, in turn, will be perfectly ready to give bread in exchange for gold. That is the principle upon which gold, and in a few cases silver, has become the foundation of trade. We use it for toning photographs and a few other things, but practically speaking, it is useless stuff, yet certain special circumstances have given it a special function in civilized society, and so governments now make it up into little flat discs, putting their own special stamp upon them as guarantee of size and quality, and it is by handing those little discs about that we carry on our trade. Or even where we use no actual disc, we pretend that we do, and use a piece of paper the value of which we say is so many discs, but that value depends entirely upon the fact that someone has guaranteed, on demand, to give so many discs for it. And the strange thing about it is that although this usefulness of gold depends upon its rarity, we lose no opportunity of looking for new sources of supply, and so diminishing that rarity. As has been said, gold is present in seawater, although no one knows how to get it out, except at a cost which makes it not worthwhile. But suppose that some genius found a way, and gold thus became twice as plentiful as it is now, the world would be no better off. Everything would cost twice as much as it does now, that is all. A pound is merely so much gold. If gold be twice as plentiful, people would want twice as much of it in exchange for what they have to sell. Yet all the same, the man who could solve that problem of getting gold from seawater, or from anywhere else, in fact, would be hailed as a benefactor, and for a time at least he would reap a generous harvest. Even as it is, science has done much for the production of gold. Not, as in other metals, in finding ways for extracting it from its ores, for, strictly speaking, it has none, but in finding ways of catching the tiny particles of metal from the gangue, as it's called, the rock or earth in which they are embedded. The trouble is that they are so small, so infinitesimally small, almost. There are two great types of place where gold is found. In the alluvial deposits, the beds of old rivers, the gold is quite loose. The convulsions of ages ago have, in many cases, elevated these beds, until now they are on the sides of mountains. In such cases the loose, gravelly stuff of which they are composed is washed down by a powerful stream of water from a huge hose-pipe terminating in a nozzle called a monitor. This process, called hydrolusing, brings down everything into a pond formed at the foot of a hill, and in some cases a boat or raft is floated upon the pond with machinery on board for dredging up the material. Often a powerful centrifugal pump sucks up the water through a pipe reaching to the bottom of the pond, bringing gravel and gold with it. Arrived in this way upon the raft, it all goes on to separating tables, by which the gold, being heavier, is divided from the gravel, which is lighter. These tables will be referred to again later. In non-alluvial workings the gold is embedded in rock of some kind, such as that called quartz. This is hard, somewhat of the nature of granite, and before the gold can be liberated it has to be crushed to the likeness of fine sand, so that the tiny grains of gold can be captured. The quartz is found in veins or lodes, fissures evidently in the original crust of the earth, produced probably as the earth cooled. These have been gradually filled up by the hot volcanic streams of water, which carried not only the gold in solution, but also the materials of which the quartz is formed. It used to be thought that the veins were the result of hot liquids forced up from below by the volcanic action, the rock and metal being themselves in the liquid state through intense heat. It is now more generally held that the water was the vehicle by which the materials were brought in and the vein formed. The gold in the alluvial deposits, too, is now thought to have come there in solution in water, and not by the erosion and washing down of rocks higher up the original river. However that may be, and it is the subject of discussion among geologists and metallurgists, there the gold is to-day, firmly fixed in the hard rock, and the problem which confronts the metallurgist is to get it out with the least expense. The old historic way of breaking up the quartz rock is with what are called stamps, pestles, and mortars on a huge scale. There are a number of vertical beams of wood, each shod with iron, fixed in a wooden frame so that they are free to slide up and down. Running along behind the stamps is a horizontal shaft with projections upon it called cams. There is one cam for each stamp, and as the shaft turns slowly round this projection catches under a projection of the stamp, and after lifting it up a short distance, drops it suddenly. Thus, as the machine works, the stamps are lifted and dropped in rapid succession. The rock is fed into a box into which the feet of the stamps fall, and thus it is pounded until it is quite small. Meanwhile, a stream of water flows through the box and carries away the finely broken particles through a kind of sieve which forms the front of the box, and which allows the fine, small pieces to escape, while holding back the larger ones and keeping them until they too have been crushed. An average stamp will weigh 600 to 700 pounds, and the repeated blows of such a hammer are enough to pulverize the hardest rock. Machines such as these have been employed since the 16th century, at all events, and the improvements of modern times are only as regards details. It may well be wondered, then, why such an old device is still in use, and how it comes about that it has not been displaced by something newer and better. The answer, which is an instructive one, well worth bearing in mind by many inexperienced inventors, is that it is so simple. It can be shipped in comparatively small parts, and so taken cheaply to any outlandish place. A good deal of it can be made roughly of wood, so that if native timber is available it can be made partly at the mine, and carriage costs saved. Finally, it is so easy to work and to understand that the most inexperienced workman can handle it, and there is so little that can go wrong that the most careless attendant cannot damage it. In the bottom of the boxes there is placed some mercury, for which gold has a curious affinity. If a particle of gold once gets in contact with the surface of the mercury, it will not get away again easily. Thus the mercury catches and holds many of the gold particles, which are liberated when the rock is broken up. As it reaches the required fineness, then the crushed rock escapes from the stamp machine and flows away in the stream of water, and although much gold is caught by the mercury, it is by no means all. The stream is therefore directed over tables formed of copper sheets, coated with mercury, so that additional opportunities are given to mercury to catch the grains of gold. Moreover, the table, which, by the way, is placed at a slight incline, is broken at intervals by little troughs of mercury called riffles, which assist in the depositing and catching of the metal particles. But even then all the gold is not captured. The crushed rock is now like sand, and some of the grains still contain gold, which has not been detached by the crushing. The gold, however, makes such grains slightly heavier than the others, and because of that they can be separated. The old way is to use a blanket table, a table, that is, covered with coarse flannel or baize, the hairs of which catch these heavier particles as the water stream carries them along, the lighter particles escaping. The grains so caught form what are known as concentrates, since in them the gold is concentrated. The concentrates are subsequently treated, as we shall see later. Now we can see how modern scientific methods have supplemented the old ways. Take first the case of the stamp mill or stamp battery. In spite of that prime virtue of simplicity which has kept it at work almost unchanged for centuries, it has its weaknesses, and no doubt for some purposes crushing mills are better. Of these there are a great variety, several of which depend for their action upon centrifugal force, or, as it is more correctly termed, centrifugal tendency. In these crushing mills there is a ring, generally of steel, inside which are suspended one or more heavy iron rollers. The shafts which carry these rollers are attached by their upper ends to the driving mechanisms on the top of the mill, and when that is set in motion the rolls are carried round and round inside the ring. Because of the centrifugal tendency, they swing outwards, pressing heavily against the inner surface of the ring. The rock is fed in such a way that the rollers, as they roll around the inside of the ring, repeatedly travel over it and crush it. In another type of mill, called the ball mill, the principle is different. There you have a cylinder of steel which turns upon a horizontal axis. This cylinder is partly filled with steel balls of various sizes, and as the mill turns, the rock, being mixed with these balls, is pounded and broken up. As the mill turns over and over, the balls fall upon the pieces of rock, thus producing a fine powder. Other mills, again, are but refined editions of the common mortar mill, and so often seen where building operations are going on, in which heavy iron rollers travel over the material to be crushed as it lies in a round pan. The blanket table, too, gives place at the modern mine to the vanner, of which there are several varieties. Essentially they are much the same, and a description of two will serve to give an idea of them all. Let us take the record vanner. Imagine a large table formed of wood, the upper surface covered with linoleum. It is fixed on sides so that it can move to and fro endwise. It is given a slight slope in the direction at right angles to its length. That is to say, one edge is a little lower than the other. The material is fed on at one end, at the higher edge, and naturally tends to run down and off at the lower edge. It is restrained somewhat from doing this by the presence of rows of riffles or ridges running lengthwise. Nevertheless, it does in a short time finds its way off the table at the lower end. By all the time that it is at work, the table is being slidden backwards and forwards on the slides. By a simple but curious mechanism it is arranged so that it moves quickly in one direction and slowly in the other, with the result that the heavier particles of sand, those which contain gold, are carried to the farther end of the table. Thus, as has been said, all the stuff is fed on to the higher edge and carried down by the water until it falls off at the lower edge. But during the journey from edge to edge, the peculiar motion of the table causes the different kinds of sand to separate themselves, so that the concentrates fall off near one end and the rest near the other end. Another interesting example of ingenuity is the well-known frowned vanner. In this the table is a broad, endless band of India rubber, extended upon two rollers, one of which is slightly higher than the other. The stream of water and crushed ore flows on at the upper end, and runs down to the lower, the lighter particles being carried down and dropped off at the lower end, while the heavier rest upon the band. Meanwhile the turning of the rollers carries the band slowly along, so that the heavier particles gradually ascend and are carried over at the upper end. To assist in the separation, the whole concern is given a side to side while it is at work. We have seen so far how the ore is crushed, and the coarser grains of gold got out of it by the aid of mercury. The mixture of mercury and gold is termed amalgam, and the process of extracting gold by mercury is called amalgamation. The gold is actually dissolved in the mercury, and so when the amalgam has been, as it is periodically, collected from the plant, it has to be filtered and then evaporated in a retort. The mercury vapor is caught and condensed back into a liquid, while the gold is left in the retort. In fact, the amalgam is distilled in order to separate the gold and mercury. But when all that is done, we still have the concentrates from the vanners, or whatever be used, to deal with. Mercury is useless with them, for the gold is covered probably with a coating of the other substances, whatever they might be, with which it has been associated, or else there is mixed with the gold some substances which make amalgamation impossible, or at least difficult. Often roasting is necessary before anything more can be done. If arsenic or sulphur be present, for example, they interfere with the recovery of the gold, and roasting will disperse them. So the concentrates are passed through great furnaces in which they are heated in contact with air until these objectionable matters have been oxidized or burnt. Then finally we come to some process by which the remaining gold is dissolved out from its admixtures in some solvent liquid from which it can be subsequently precipitated. This is rather interesting because it means that man has adopted, to recover this gold from the ore, the very method which it is believed nature employed to put it there. As already said, the latest idea is that the gold was carried into and deposited in the lodes where it is now to be found by water, that the gold was actually dissolved in water at the time. But of course gold in its metallic state will not dissolve in water. Salts of gold, however, the meaning of the term salt as applied to a metal has been explained earlier, will dissolve in water, as every photographer who makes up his own toning solution knows from experience. Gold will not dissolve in water, but chloride of gold will, and so the gold must have been carried to its resting place as salt, and converted into the metallic form after arrival. In the same way, to recover these finest particles of all, it has to be converted back into a salt. Then that salt must be dissolved and drained away from the other stuff, and finally the gold must be thrown out of solution again in some way. The great example of this operation is the familiar cyanide process. The word familiar is appropriate to this matter in only one way. However, holders of shares in mining companies, for example, may hear about it repeatedly at shareholders' meetings and prospectuses, but very few have any clear idea as to what it is. So I cannot be accused of telling an oft-told tale if I devote a short space to its consideration. The combination of one atom of carbon and one atom of nitrogen is called cyanogen. If cyanogen be given the chance, it will take unto itself an atom of hydrogen, producing the deadly hydrocyanic or prussic acid. Alternatively, if potassium be brought into combination with it, there results potassium cyanide, which, with the assistance of water and oxygen, can dissolve gold. In applying this scientific fact to the purpose of recovering gold from the concentrates, the latter are placed in vats with a weak solution of the cyanide in water. This time during which they are allowed to remain depends upon the size of the gold particles. If they be comparatively large, it stands to reason that it must be longer than if they be small, for they will take longer to dissolve. After the proper time, which is found by experiment, the liquid is drawn off, and in some cases the concentrates are given a second dose to ensure that the gold shall be thoroughly removed and none left undissolved. If the material being operated upon be very fine, as it often is, forming what the mining people call slimes, then mechanical stirrers have to be used in the vats to keep the stuff moving, as otherwise the cyanide would not get to all the particles and some would not be acted upon. The liquid, having been the appropriate time in the vat, is drawn off, placed in wooden tanks or boxes, and fine shreds of zinc are added to it. Discs of sheet zinc are also put into a lathe and a fine shaving taken of them, and it is these fine shavings which are used. Now zinc, as we know from the fact that it is the essential part in electric batteries, has very pronounced electrical properties, and it is believed that these come into play here. At all events, the gold becomes deposited upon the zinc, while the zinc itself is to a certain extent eaten away by the solution. The result is a solution weaker than it was before, b. the remains of the shavings, and c. at the bottom of the box in which this process takes place, a dark mud. That black mud, on being heated, produces the bright metallic gold, and the object of the whole operation is achieved. The solution is then led to another tank, brought up to its proper strength again, and is ready to be used once more, while the remains of the shavings are used for the next batch of material to be treated. In some cases, the crushed ore straight from the crushing mill is cyanided. In others, it is simply the remains left over from the previous amalgamating process which is thus treated. All depends upon the nature of the material in question. There are other chemical methods besides the cyaniding, but it is the chief. It has been found specially useful with the Johannesburg ores, and to it the South African goldfields owe a great deal of their success. There is a modern form of it, although the whole process is quite novel, having been introduced only in the 90s of the last century. This development, it is almost wearing to repeat, is electrical. Instead of the zinc shavings being used to precipitate the gold out of the solution, the process is electrolytic. A lead anode is used while the process is carried on in a box, the bottom of which is covered with mercury, which forms the cathode. The precipitated gold is thus amalgamated, the amalgam being removed at intervals, retorted, and the gold recovered. The idea of recovering gold from the waters of the sea is certainly a most attractive one. To some, it is true, the suggestion may bring thoughts the reverse of pleasant, for there have been several partially successful attempts to delude the public with specious promises of vast dividends to be gathered in the form of pure gold from the inexhaustible sea. Still, there is something in it, and some day the dreams may be realized. The quantity of gold dissolved in sea water is so small, in 200 cubic centimeters, it is impossible to detect it, even by the most delicate tests known. The quantity needs to be multiplied threefold before the quantity of gold becomes even detectable, to say nothing of being recoverable. A writer in Cassier's magazine, a few years ago, related how he had actually obtained gold from the water of Long Island Sound. But whereas he got $2 worth, it cost him over $4,000 to do it. No company will ever be floated on results such as that. From the mud of a creek near New York, however, he did a little better, for there $10 worth of gold only cost $379. A company promoter would still look askance at even that comparatively successful undertaking. As usual, the authorities differ, but there is a consensus of opinion that in every ton of seawater there is from 1/2 to 1 grain of gold, besides silver and iodine. It seems as if the water were able to dissolve that amount and no more. If, as has been suggested earlier in this chapter, all the gold which is now found in mines and in gravel beds was carried there in water, it is probable that the sea obtains its gold from the same original sources, and that, just as the hot ocean of ages ago carried its burden of gold in solution, so the colder water of to-day has its share. the cold water naturally carrying less than the hot did. It is quite likely, then, that, could we find out how to rob the sea of its precious metal, it could replenish its store from the secret hoard of its own. But even if it could not, it would make little difference to us, since what it holds is far more than we could ever use. Put it at half a grain per ton. There are 4,205 million tons in every cubic mile of ocean, and 300 million cubic miles of water in the ocean. If all the gold that man has ever handled were to be dissolved in the sea, no chemist would be able to discover that fact. On the other hand, if that half grain per ton, which we believe to be in the ocean now, were to be recovered, we should have about 40,000 million tons of gold, a prospect which is enough to make the political economist turn pale with apprehension. What is required is some substance which, on being added to seawater, will combine with the gold and then be precipitated, that is to say, fall to the bottom. The precipitate, that which falls to the bottom, would need to be heavy, so that it would fall quickly and not necessitate the water being left standing for long periods. It would need to be cheap, too, or easily recoverable, so that it could be used over and over again. And finally, it would need to be such that the gold, having been captured by it, could easily be obtained from it. Given such a precipitant, the process of recovering the gold would be simple and cheap. Tanks would be formed in sheltered bays and in inlets. At every tide these would be filled, and when full, the precipitant would be added. The tide falling, the water would run out again and leave the precipitate on the floor of the tanks, whence it could be removed by scraping. Simple treatment would release the gold from its partner, which would then be returned to the tanks to act as a precipitant once more. Thus, by simple means, the tide itself assisting, the gold could be obtained from the sea. And there is nothing inherently impossible about this suggestion. The necessary precipitant may exist, awaiting discovery. A large works operating in this manner would produce, it is estimated, about 13 tons of gold per annum. It looks as if it would be a bad day for the Rand when that discovery is made. And there is yet another possibility, though less alluring than what has just been described. The American writer mentioned a little while back got a better return from the mud of a creek than from the water itself. In all probability this is due to the action of organic matter carried down by streams, or in some other way introduced into the waters of the creek, whence the mud was obtained. This organic matter would probably have an effect as a precipitant upon the dissolved gold, causing it to be thrown out of solution and deposited in the mud. Thus the mud around our shores, and particularly in the creeks and estuaries, may be potential gold mines, whence in time to come we may draw supplies of the precious metal. The cyanide or some similar process may be needed in order that we may extract the metal from its enclosing mud. But the time may not be so very far distant when dredging for gold may be a regular occupation at, for example, the mouths of the Thames and the Hudson. End of section 9. Recording by Lynda Marie Neilson, Vancouver, BC.
Section 10 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Phil Kasper. www.philcasper.net. Marvels of Scientific Invention by Thomas W. Corbin. Chapter 10. Intense Heat. Many of the useful and interesting manufacturing processes of today are based upon the intense heat which science has taught the manufacturer how to produce. Tasks which our forefathers dreamed of but were unable to accomplish are easy today because of the facility with which great heat can be generated. The burning fiery furnace 7 times heated is as nothing to some of the temperatures which are now obtained in the ordinary course of things. The greatest heat of all is that of the electric arc. 2 conductors, generally rods of carbon, are placed with their ends touching, and the current is turned on so that it passes from one to the other. Then they are gradually drawn apart. As the gap widens, the current experiences more and more difficulty in passing over this non-conducting gap, and great electrical energy has to be employed to keep it going. Now, that wonderful law of conservation of energy decrees that no energy can ever be lost. It can only be changed from one form into another. Therefore, the energy expended upon the arc is not lost, but is converted into heat. It is that heat acting upon the small particles of carbon, which are torn off the ends of the rods, which gives us the arc light. As a matter of fact, nearly all artificial light, and natural light too for that matter, is due to heat. Footnote, the glowworm is an example of the few exceptions. End footnote. The heat sets the molecules in violent agitation, which, acting upon the corpuscles in the atoms, sets them in violent motion too, so that light is often the companion of heat. Some substances give light more readily than others under the influence of heat, and we may reasonably believe that they are those whose corpuscular arrangements are such that they can be readily accelerated by the molecular action. To take a familiar instance, coal gas is mainly methane, one of the many combinations of carbon and hydrogen, and when it is burnt in the air, the hydrogen and oxygen combine, liberating heat, which causes the carbon liberated at the same time to glow. As each methane molecule breaks up, the carbon atoms are thrown out, forming solid particles of carbon, and it is they really which give the light. It is therefore the combustible gas heating the solid particles of carbon which forms a luminous part of the gas flame. The non-luminous part of the flame near the burner, I'm now speaking of the old-fashioned burner, is the burning gas before the carbon particles have had time to heat up. And the old gas flame, as we know, is now being rapidly displaced by the incandescent mantle. The reason being simply that von Welsbach discovered how certain rare minerals gave a more brilliant light when heated than particles of carbon do. In other words, it is easier to accelerate the motion of the corpuscles in ceria, thoria, and the other ingredients of the mantle than it is those of carbon. Consequently, they sooner reach that degree of agitation which will send forth electromagnetic waves of the high frequency necessary to produce the sensation of light. For this reason, the mantle heated by gas gives as bright a light as the carbon particles in the electric arc, although the latter are subjected to a much more intense heat. But the arc can be, and often is, used as a source of heat, apart altogether from the light which it gives. In Sweden, for example, where coal is rare, but water power plentiful, the power of the waterfalls is made to smelt iron. Hence, the waterfalls are sometimes termed the white coal of that country. Needless to say, it is the ubiquitous electricity which performs the change from the force of falling water into heat. The furnaces are in the shape much like those in which iron is smelted with coal, namely, tall chimney-like structures at the bottom of which is the fire. In the arc furnaces, there are, passing in through the side, near the bottom, a number of electrodes, and between these a series of arcs are formed. Coke and ironstone are thrown in from the top into this region of intense heat, and there the iron is liberated from the oxygen with which it is combined in the ore. Liberated, it flows out through a spout at the other side of the furnace. But the question will arise in the reader's mind, why is coke needed in an electric furnace? It is for metallurgical reasons. The heat of the arc loosens the bonds between the iron and oxygen, but it needs the presence of some carbon to tempt the oxygen atoms away. Therefore, coke, as the most convenient form of carbon, has to be there. It is there, however, in much smaller quantity than it would be in an ordinary furnace. It is not there as fuel, but but simply as the counter-attraction to draw the oxygen atoms away from their old love. The arc is also used for welding pieces of iron together, for which purpose it is eminently suitable, since what is wanted is intense heat at a particular point. But perhaps the reader will be wondering by this time what the heat of the arc is. It has been repeatedly referred to as intense, but something more definite may be demanded. In theory, it is unlimited. Apply more pressure, more volts that is, thereby driving more current across, and the temperature will rise. It is only a question of making dynamos large enough and driving them fast enough, and any temperature is possible. But there are practical difficulties which limit the degree of heat. One is the melting point of the furnace itself. Fire clay melts at about 1700 degrees to 1800 degrees Celsius. So in a furnace which has to be lined with fire clay, that is about the limit. In welding two pieces of iron together, the iron, of course, defines what the limit shall be. It needs to be heated to welding heat and no more, that is, a little short of melting, so that the parts to be joined are soft, and with a little hammering will join thoroughly together. If too much heat were to be applied, the parts would melt away. But the heat of the arc can be controlled by simply varying the current, and so the right heat can be applied at the right place, than which little more is wanted. One very simple way of doing this is for the workman to hold one of the electrodes, a rod of carbon suitably insulated, in his hand. The current is led to it through a flexible wire. The iron itself is made the other electrode by being gripped in a vise which is itself insulated but connected to the source of the current. Thus, on bringing the point of his rod near to the part to be heated, the man causes an arc to be created there. By moving the rod, he can move the arc about, heating one part more than another, distributing this heat if he wants to do so over a larger area, or keeping it to a small one just as he wills. On reaching the right heat, the rod is withdrawn, the arc destroyed, and the iron can be hammered just as if it had been heated in a fire. Yet another way is still known as resistance welding. In it, an enormous current at an extremely low voltage is used. The fundamental principle is the same, since the heat is formed by forcing current past a point over which it is reluctant to pass. That point of poor conductivity is the ends of the two bars to be joined. They are placed just touching, but since an imperfect contact like that always offers considerable resistance to the flow of a current, the passing current needs only to be made large enough for great heat to be generated. This is exceedingly pretty to watch. We will suppose that the article to be operated on is the tire of a wheel. The bar of iron has already been bent by rollers into the correct curve, and the two ends are touching. Brought to the machine, it is gripped, each side of the junction, in the jaws of an insulated vise, and the current is turned on. In a few seconds, the place where the two ends are just touching begins to glow. Rapidly, it increases in brightness until, in about half a minute, it is at welding heat. Then one vise, which is movable, is forced along a little by a screw so that the ends are pressed firmly together, a little judicious hammering meanwhile helping to complete the job. Then the current is switched off and the complete tire taken out of the machine. The current used has a force comparable with that which operates domestic electric bells, but in volume it is thousands of amperes. Alternating current is used, and it is obtained from a transformer or induction coil. In such a case, the primary part of the coil is made of many turns of fine wire, so that little current passes through it, while the secondary part is but 1 or 2 turns of thick bar. Thus, the voltage generated in the secondary is very little, but since the secondary has an almost negligible resistance, the current caused by that small voltage is enormous. Such an arrangement is, in industrial realms, generally called a transformer. The term induction coil being employed more for those things of a similar nature intended for the laboratory. The one just described is, moreover, a step-down transformer, since it lowers the voltage to distinguish it from step-up transformers which raise the voltage. And the resistance principle is also applied in another way to large furnaces, such as those for refining iron. In these, the resistance of the iron itself is utilized to generate the heat. Of course, it should be well understood, heat is always generated in everything through which current flows. There is no perfect conductor, and so every conductor is more or less heated by the passage of current through it. Some energy needs to be expended to drive current, even along large copper wires, and that energy must be turned into heat in the wires. If the same volume of current be forced along iron wires of the same size, the heat will be greater, since iron is but a poor conductor compared with copper, the relation being about as 1:6. And if the iron be hot, the resistance will be still more. For it stands to reason that when heated, the molecules, being farther apart, will be the less easily able to exchange corpuscles. We have the best reasons for believing, as has been suggested already, that a current of electricity is but a flow of corpuscles, and so we are not surprised to hear that, as a general rule, the hotter a thing is, the less does it conduct electricity. So imagine a circular trough of fire clay or other heat-resisting material filled with fragments of iron, or it may be with iron barely above melting point, which has come from another furnace, where it underwent the previous process. Circling inside or outside this trough is an enormous coil of wire through which currents of electricity are alternating. That is the primary of a transformer. And the secondary is the iron itself in the trough. If it be, as it often is, in the form of scrap or broken pieces, the heat will begin to show itself where the pieces touch each other. The currents generated in the trough by the coil outside will, of course, pass from piece to piece, and the points of contact, since they offer the greatest resistance, will show signs of heat. This will increase until the pieces begin to melt. As the separate fragments merge into the molten mass, the resistance will in one way decrease, for the imperfect contacts between the pieces will give place to the perfect contact throughout the mass of liquid metal. But for another reason, namely the increase in heat, the resistance will increase. And all the while, the alternations in the primary coil will be pumping currents, as it were, round and round the ring of molten iron. Whether the resistance increases or decreases, the current will do the opposite, so that heat will be generated whatever happens. For as resistance decreases, current increases, and vice versa. And the slightest variation in the strength of the primary current will have its effect upon the secondary, and therefore on the heat generated. So by simply regulating the primary current, the temperature of the metal can be controlled to a nicety. And such furnaces have the immense advantage that there is no possibility of deleterious substances in the fuel getting into and spoiling the metal, a thing which may very easily happen during the manufacturing of high-class steels, alloys of iron, in which the exact quantities, purity, and proportions of the ingredients are of the utmost importance. Hence these induction furnaces, as they are called, are frequently used quite apart from any question of utilizing water power. And they will probably be used still more as time goes on. For one thing, they may become valuable adjuncts to the older form of iron and steel furnaces, from which they will obtain their power-free gratis and for nothing. In districts such as Middlesbrough, they could generate more electricity than they have any use for. The ordinary iron furnaces belch forth flames, which are really good useful gas, carbon monoxide, burning to waste. Many of the furnaces are covered in at the top, and this gas is led away to heat boilers for the steam engines or to drive large gas engines, but in a large works there is more of this waste gas than they know what to do with. Now that could, and probably will ere long, be turned into electricity by means of gas engines and the current used for making steel in induction furnaces. It will probably surprise many to know that these enormous currents, which can thus heat great masses of metal until they melt, are no danger at all to the men who work with them. A man might dip an iron rod into the trough of metal, and he would scarcely feel the shock. And the same is true of the welding machine, which can be touched in any part without fear. The reason, of course, is that, broadly speaking, it is volume of current which does harm, and the resistance of the human body is so great that with the small voltages used, the volume which can pass is negligible. It should be mentioned, however, that the volume of current in lightning is also small, but we know that it is capable of inflicting terrible injury. Lightning, however, is in a class by itself. Our terrestrial voltages are baffled by an air gap of a few inches, but lightning springs across a gap miles wide. Its voltage must, therefore, amount to millions, and the ordinary rules relating to earthly currents do not apply. But other sources of heat besides electricity are at the disposal of our manufacturers nowadays. Preeminently, there is the flame of some gas burning with pure oxygen. The oxyhydrogen jet has been known for many years as the best means of producing light for a magic lantern. Such a jet, impinging upon a pencil of lime, causes the latter to glow with a dazzling white light. But the oxyhydrogen jet is now employed in many factories for the welding of metals. This is known as fusion welding, since the two parts are actually reduced to liquid. The usual way to go about this work is to bevel off the ends or edges to be joined. Suppose, for instance, that we wanted to weld two pieces of brass pipe together. We should first file or otherwise trim the edges to be joined until, when put together, they form a groove practically as deep as the metal is thick. Then, with a stick of brass wire in the left hand and an oxyhydrogen blowpipe in the right, we should direct the flame from the pipe onto the metal until, at one point, the sides of the groove were beginning to melt. Then, inserting the point of the wire into the groove, we should melt a little off it. Thus, we should work all round the joint, melting the sides of the groove and filling in with melted metal from the wire, until the whole groove had been filled up and the metal added had been thoroughly amalgamated with that on either side. As a matter of fact, if it were brass which we were working on, we should probably use the cheaper though less pure form of hydrogen, coal gas, so that it would really be oxy-coal gas that we should use and not oxyhydrogen. The latter is used, however, notably for the fusion welding of lead, or lead burning, as it is termed. The blowpipe is a brass tube about a foot or 18 inches long, with two passages in it, one for the oxygen and the other for the other gas. The gases are brought to one end of it through rubber pipes, while at the other end there is a nozzle in which the gases mingle and from which they emerge in a fine jet. The oxyhydrogen flame has a temperature of about 2000 degrees Celsius, hot enough to melt fire clay. That does not matter in the case of welding, however, since the molten metal is very small in quantity at any given moment and is allowed to cool before it can run away. It would be an awkward temperature to deal with, nevertheless, in a furnace. It seems strange that it does not burn the nozzle of the blowpipe, but the fact that it does not is, it is believed, explained by the fact that the expansion of the gas, as soon as it emerges from the hole out of which it shoots, causes a comparatively cool space just there, shielding it from the intense heat farther on. An exceedingly interesting use of the oxyhydrogen flame is in the manufacture of artificial rubies. These stones are made in Paris by a very simple means. The necessary chemicals are prepared and ground into an exceedingly fine powder. This is then allowed to fall through an oxyhydrogen flame. Thus, there is no need for a crucible capable of withstanding this high temperature, since the melting takes place as the particles are in the act of falling. When they reach the support prepared to catch them, they have cooled somewhat. Stones so called are real rubies, artificial but not shams. They possess every property of the ruby from the mine. Another product of the oxyhydrogen flame is the quartz fibers, which are used for suspending the needles in the finest galvanometers. The quartz is melted, in this case a crucible being employed. An arrow is then dipped in the liquid quartz and immediately fired into the air. The thick treacly liquid is thus drawn out into a thread of such fineness that a microscope is necessary to find it with. Hotter even than oxyhydrogen is the oxyacetylene flame, which at its hottest point reaches nearly 3,500 degrees Celsius. The gas, which is another of the combinations of carbon and hydrogen, its molecules containing 2 atoms of each, is easily made by allowing water to come into contact with calcium carbide. The latter, which is CaC2, is made by heating coke and lime together in the intense heat of an electric furnace. This accounts largely for the great heating power of acetylene, for since great heat is necessary to cause the elements to combine, great heat is given out by them when they ultimately separate. Here again is the conservation of energy. The heat energy of the electric furnace is largely expended in forcing these two elements into partnership. They are, as it were, given a large amount of capital in the form of heat. It ceases to be sensible heat, becoming latent in the compound, but still it is there. So a lump of calcium carbide, with which many readers are familiar, has vast stores of heat locked up within it. When water comes into contact with the carbide, the partnership is broken, but the heat is not liberated then, since another partnership is formed, which still retains the old heat capital. The calcium in the carbide is displaced by the hydrogen from the water, and so C2H2 comes into being, while the rejected calcium consoles itself by entering into combination with the equally forsaken oxygen from the water, forming CaO, which is but another name for lime. Then the acetylene, C2H2, is mixed with oxygen in the blowpipe and burnt, under which conditions the pent-up heat, borrowed originally from the electric furnace, is brought into play. With this flame, the harder metals can be fused and welded. Wrought iron, cast iron, steel in all its forms can be melted by the oxyacetylene flame almost as easily as snow by a hot iron. The fusion welding of these metals is then carried on just as already described for brass. By means of a special blowpipe, wherein an excess of oxygen is introduced at the hot point, hard steel plates can be cut into pieces almost as easily as a grocer cuts cheese. Even thick, hard armor plate can thus be cut, almost the only way, indeed, in which it can be cut. And for purposes such as welding and cutting, this flame has an interesting and peculiar advantage over all other kinds of heat. When a metal is heated in the air, there is usually trouble from oxidation. The domestic poker, for example, after it has been left to get red hot in the fire, is seen to be coated, in the part which has been heated, with scales which will flake off if the thing be struck. Those scales are oxide of iron, caused by the union of iron and oxygen when the poker was hot. But if the heat be applied by the oxyacetylene flame, that will not happen. The oxygen and the carbon from the acetylene will burn, and if the supply of the former be properly regulated, it will be entirely used up in the process. The hydrogen from the acetylene is, strange to say, unable to unite with oxygen at such a high temperature as that of the oxygen and carbon, so that it passes on beyond the oxygen-carbon flame and ultimately burns on its own account, with the oxygen from the atmosphere in a second flame surrounding the first. Thus there is a double flame. Inside, a little pointed cone of white flame, that is the oxygen and carbon, and outside that a bluish flame, the hydrogen and the atmospheric oxygen. The latter flame forms a kind of jacket entirely enveloping the former. And so when one melts metal by means of the white cone, the hydrogen jacket shields the molten metal from oxygen and prevents the oxidation. Only one who knows the bother caused by oxidation whenever metals are heated can realize the wonderful advantage of this. And now we can turn to even another source, also quite modern, of high temperature. If the oft-quoted man in the street were asked the two commonest things on Earth, he might possibly name oxygen as one, and so far he would be right. But the chances are much against his naming aluminium as the second. If he did not, however, he would be wrong. Aluminium and oxygen form alumina, of which are constituted the sapphire, the ruby, and other precious stones, but alumina is most commonly found in combination with silica or silicone and oxygen. This compound is called silicate of aluminium, and of it are formed clay and many rocks. The reason why the metal aluminium was until recently rare and expensive was because of the great difficulty of disentangling the metal from this rather complex combination. And these two commonest elements have, under certain conditions, a rare affinity for each other. They join forces with such energy that great heat is given out in the process. This, again, we may regard as an example of the conservation of energy. Heat had to be used up, apparently, in separating the aluminium and oxygen as they were found together in the natural state, and that heat reappears when they combine together again. This is the most powerful principle, for if heat has disappeared anywhere in the course of some operation, we know that in all probability, if we go about it the right way, we can get that heat back again, perhaps in a more convenient form. That is so in this case at all events. Now, aluminium will not readily combine with atmospheric oxygen, but it will readily do so with oxygen from the oxide of a metal. So if we put into a vessel some oxide of iron and some finely powdered aluminum and give it some heat at one point just to set the process going, the whole mass will burn with intense heat. And when the burning is finished, the crucible will be found to contain 1. Some molten iron, the oxide of iron with the oxygen gone, and 2, some oxide of aluminium or alumina, in the form which we call corundum, a very hard substance which in a powdered form is used for grinding hard metals. We start, you will notice, with a pure metal and an oxide. We finish with a pure metal and an oxide, only the oxygen has changed its quarters, having passed from the iron to the aluminium. And in the course of the change, a vast amount of pent-up heat has been liberated. Aluminium is thus a fuel, strange though it may seem to say so, just as coal is. Coal, however, is willing to pair off with oxygen from the air, while aluminium, more fastidious, will only accept it as partner when it can steal it from another combination. But the practical result is eminently satisfactory, for the action of the aluminium and the iron oxide is to leave us with a crucible full of molten iron at a very high temperature, and this can be used in various ways. Tramway rails, for example, can be joined together by it. A mold is formed around the ends of 2 rails, where they butt together, and into this mold a quantity of the melted iron can be poured. So hot is it that it partially melts the ends of the rails, and then, amalgamating with them, it forms a perfectly homogeneous connection between them. The same method can be applied to the repair of iron structures of all kinds. The propeller shaft of a ship, for example, sometimes breaks on a voyage. Such a catastrophe is fraught with the most serious consequences unless it can be quickly repaired. Thermite, as the process is called, is perhaps the only means whereby, under certain conditions, this can be accomplished. The extraordinary heat of the metal produced in this way is demonstrated by the fact that if it be poured onto an iron plate an inch thick, it goes clean through it. It melts its way through instantly. But although such high temperatures are at the command of the modern manufacturer, there are some things, indeed many things, which still baffle him. The diamond, for example. It is true that diamonds of small size have been made, but larger ones have so far defied all efforts. One very interesting fact about this may be mentioned in concluding this chapter. Sir Andrew Noble, a member of the great firm of Armstrong, Whitworth and Company of Elswick, tried the experiment of exploding some cordite, a high explosive, inside a steel vessel of enormous strength. He thus produced what is believed to be the highest temperature ever produced on Earth. It is reckoned to have been 5,200 degrees Celsius, and the pressure at the same time was, it is calculated, 50 tons per square inch. His intention was not to make diamonds, but Sir William Crookes predicted that diamonds would be the result, for the cordite consisted mainly of carbon, which, as is well known, is the material of which the diamond is formed, and the combination of high temperature and high pressure is just what is needed, so it is believed, to bring the carbon into this particular form. And true enough, on the iron being examined after the explosion, there were seen tiny diamonds. For larger ones, even higher temperatures and greater pressures are, no doubt, necessary, and as the diamond, like gold, has a peculiar fascination for mankind, so the efforts to manufacture it will continue. In years to come, the means may be found of creating these extreme conditions of temperature and pressure, and so another of the problems of the ages will be solved. End of section number 10. Recording by Phil Kasper. www.philkasper.net.
Section 11 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arvindh Sundar from Bangalore, India. Marvels of Scientific Invention by Thomas W. CORBIN. An artificial coal mine. Those countries which are blessed with a plentiful supply of coal are periodically shocked and saddened by a terrible calamity, an explosion in one of the mines, in which often scores of poor fellows lose their lives, and hundreds of widows and orphans find themselves without a breadwinner. One has to only recall that heart-rending calamity of the couriers' mines in France, where over 1,000 lives were lost, to realize how important is the question of the cause and the cure of the colliery explosion. It used to be thought a settled matter that these were due to the accidental ignition of a gas called, scientifically, methane, but by the miners, fire damp. This undoubtedly does collect in many mines, and since it is much the same as the domestic coal gas, indeed methane forms the bulk of coal gas, it is not surprising that the explosions were attributed to it. At times, shots were fired to blast down the coal, and although the greatest precautions are taken to prevent any accident resulting, it seems certain that explosions have occasionally followed the firing of shots. But still more dangerous is the adventurous miner who, for some reason, opens his safety lamp. It is lit for him before he enters the workings and locked up so that, theoretically, he cannot tamper with it, but it has to be a cleverly devised lock that cannot be picked in some way. And with the carelessness born of long immunity from accident, these are got open sometimes, with, it may be, disastrous results. Even a spark struck from a miner's pick may ignite the gas, or a spark from some electrical machine used in the mine. That is one of the reasons why electrical apparatus is suspect in colliery matters and machines worked by the less convenient and more costly means of compressed air are preferred. In some such manner the fire damp is ignited, and then there follows the fiery blast, which, sweeping through the narrow galleries and passages which constitute the workings, simply licks up the life of the men whom it encounters. Others, in byways and sheltered corners, escaping the burning cloud of flame, are poisoned by the deadly fumes of carbon monoxide which it leaves when its force is spent. While others, perchance the most unfortunate of all, are saved for a time, but, being imprisoned by falls from the roof and walls, die a lingering death of hunger and slow suffocation. A colliery explosion is one of the ghastliest events imaginable, the only relief from which is the noble heroism with which the survivors, from the mine managers to the humblest workmen, crowd round the pit mouth, eager to risk their own lives for the faint chance of saving some below. Not infrequently, these brave volunteers only share the fate of the men they would rescue. Now all that, as I have said, used to be put down to the effect of the fire damp. But it dawned upon men's minds some years ago that the damage seemed to be out of proportion to the power of the gas. Modern mines are well ventilated by large fans which impel great volumes of the air through all the workings. The air currents are cunningly guided by partitions, or brattices, so that every nook and corner shall be scoured out by the plentiful draught of pure, fresh air. Consequently, the amount of explosive gas which can collect in any one place is but small. How, then, can so small a volume of gas do so large an amount of damage? Coupled with this was the fact that explosions take place in flour mills, where there is no gas, and experimenters had found in their laboratories that almost any burnable substance, if ground up finely enough and blown into a cloud, would explode. Coal dust would naturally do this. Indeed, anyone throwing the dust from the bottom of the coal shovel upon a fire will see for himself how quickly such dust will burn, and, as has been pointed out in an earlier chapter, an explosion is but rapid burning. So the blame was largely transferred from the shoulders of the fire damp to those of the clouds of coal dust which collect throughout the workings of a mine. But then a difficulty arose from the fact that there is dust in all mines, yet some districts are quite free from explosions, and such districts are those where there is little or no fire damp. These two facts seem to be explainable in one way, and in one way only. It must be that gas first of all explodes feebly, and so, stirring up the dust lying along the roads and passages, prepares the way for the powerful, deadly explosion of coal dust which follows. But that was only a guess, and the matter was of such importance that it needed something more certain than mere assumption. So the Mining Association of Great Britain decided to have a series of experiments which should settle once and for all what part the coal dust played in these catastrophes and how best they could be prevented. It was at first thought that an old mine might be utilized for the experiments, but there was the difficulty that such always became wet after work has ceased in them, and so the dust would not behave normally. Moreover, the work would be extremely dangerous and the results difficult to observe. Then a culvert was suggested built of concrete, partially buried in the ground, but that too was dismissed. Finally, it was decided to make an imitation mine of steel, using old boiler shells with the ends taken out. The sum of £10,000 was subscribed for the purpose by the coal owners of Great Britain, and the great work was carried out at Altofts in Yorkshire, close to a colliery where a terrible disaster occurred in 1886. Here, the great tube or gallery was built, roughly the shape of a letter L. One leg is over 1,000 feet long, while the other is 295 feet. The longer leg is 7.5 feet in diameter and the shorter 6 feet. At the end of the shorter part, a large fan is installed which can force 50,000 to 80,000 cubic feet of air per minute through the structure, so producing the conditions of a well-ventilated mine. The shorter length has several sharp turns in it for the purpose of breaking the force of the explosion along that part, and so shielding the fan from damage, while a tall chimney is provided there so that, the door being shut to cut off the fan, the gases from the explosion can find a harmless way out. Inside the tube, shelves are fixed along the sides so as to reproduce the effect of the timbering in a real mine, upon the beams of which the dust finds lodgment. Props were put up too, just as they would be in the real mine. Everything, in fact, was done to make the place as perfect a replica as possible of actual underground workings. And then, added to this huge and costly structure, was an outfit of scientific instruments worthy of the important investigations which were to be carried on. To grasp the purpose and working of these, we need to remind ourselves of the aims and intentions of the experiments. First of all, it was desired to find out how various quantities and qualities of coal dust behaved. The dust was laid along the floor of the tube and along the shelves. A small gun fired at some point in the tube raised a cloud of this dust, just as the gas explosion in the real mine would do. Then, another gun was fired to explode the dust cloud. So far, all is quite simple and easy. But to do that would be of no value without the means of finding out exactly what resulted from the explosion. And that is the function of the instrument. To commence with, there is the great wave or tide of force or pressure which surges along the gallery immediately the cloud bursts into flame. How fast does that wave travel? How long is it after the explosion before the shattering effects of it are felt 100 yards away? To solve that problem, electrical contact breakers are fixed at intervals of 50 yards along the gallery. Each of these consists of a cylinder with a piston inside it, something like, shall we say, a cycle pump. The piston, held down normally by a spring, is blown upwards by the force of the explosion. The spring is adjustable, and so it can be arranged that the feeble force of the gun cannot lift the piston, but the more powerful coal dust explosion which follows can. Thus, when the explosion takes place, these contact breakers are operated in succession. The one nearest the seat of the disturbance is operated first, next the one 50 yards farther away, then the one 100 yards away, and so on. The moments when they work will tell the speed at which the blast travels along the gallery. But it travels with great speed, and so to measure and record the exact moment when each contact breaker is moved is a matter of no little difficulty. Electricity, however, makes this, like so many other things, comparatively easy. There is an apparatus used in astronomical observatories called a chronograph, which registers, within a small fraction of a second, the moment when a star seems to pass across a wire in the transit circle, the telescope by which the positions of stars are determined, and the exact time kept. The observer sits with his eye to the telescope, watching the apparent movement of the star. In his hand he holds a small push pressure on which by his fingers operates a minute pricker, which acts upon moving strip of paper. The paper travels along with the utmost steadiness and regularity, while a clock drives a sharply pointed pricker onto it every 2 seconds. Thus, the clock marks out the paper into lengths, each of which represents 2 seconds. But the other pricker, worked electrically by the observer's hand, also makes its mark upon the paper. And so, while the regular marks indicate intervals of 2 seconds, each irregular one marks the time of a transit or passing of a star across the wire. An examination of the strip subsequently enables the times of a transit to be seen with great accuracy, from the position of the corresponding mark between two of the regular marks. And the same principle was applied to the circuit breakers of this artificial mine. Normally, current flows through the circuit breaker, but the lifting of the piston breaks the circuit, whence the name of the contrivance, and that breaking of the circuit and consequent cessation of the current operates the chronograph. By a cleverly constructed device, the details of which are too complicated to set out here, each circuit breaker in turn makes its mark on the same strip, so that the distances apart of these marks show the time taken by the force of the explosion to travel 50 yards. Meanwhile, the clock goes on making its regular marks, in this case every half second, so that they form a scale by which the other intervals can be measured very exactly. The chronograph used here is more accurate than that in use at Greenwich Observatory, the reason being that in this case the recording currents are sent mechanically by the contact breakers operated by the explosion itself, while in the case of the astronomer the human element comes in. To watch a moving speck of light and to tell exactly when it crosses a fine line is by no means easy, and so to tell the time within a tenth of a second is about the limit of possible accuracy. The instrument we have been referring to, however, can register the time which a gaseous wave moving 3,000 feet per second takes to travel 50 feet. In other words, the circuit breakers can be operated so fast that when only a 60th of a second intervenes between the action of one and that of the next chronograph can duly record the fact. The records of the chronograph can be made in two ways. One by a pen on a piece of paper tape, and the other by a scratch on a piece of smoked paper. So, by that means, the progress of the force of the explosion can be measured. It is necessary also to time the movement of the heat of the explosion, for the two may not travel together, and the difference between them may let in some light as to the nature and the behavior of the explosion. So for this second purpose, a second set of circuit breakers are used. Each of these consists of a strip of thin tinfoil stretched across the gallery. Being placed edgeways to the moving current of gas, the force of the explosion has no effect upon it, but the heat instantly melts it. Normally, current flows through the strip, and so the melting is signalized by the cessation of the current, which event is recorded by the chronograph. Thus, the speeds at which the force and the heat of the explosion travel are ascertained. Another important fact which needs to be found is the amount of the force or the pressure at different points. For this purpose, pressure gauges can be connected to the gallery at the desired spots by means of flexible tubes. This flexible tube is necessary in order that the vibration of the steel shell, due to the explosion, shall not be communicated to the instrument. The pressure, finding its way along the flexible pipe, raises a piston against the force of a spring, and the distance to which it is raised forms, of course, a measure of the pressure inside the gallery at the point to which the tube is connected. The pressure is recorded by the action of the piston in moving a style which just touches against the surface of a moving paper. There are 3 styles in all marking this paper. The first is the one just mentioned. The second is held down onto the paper by an electromagnet energized by current flowing through a fine wire stretched across the gallery just where the explosion originates. this fine wire is broken at the moment of the explosion, whereby the current is cut off and the style raised. It therefore makes its mark until the moment the explosion occurs, and then leaves off. The end of that line, therefore, shows the time of the explosion. Meanwhile, the first style is drawing a straight line, but as soon as the pressure begins to be felt by the pressure recorder, this style moves and the line slopes upward. Upward it goes as the pressure increases, until it has reached its height, after which it descends, until the style is drawing a straight line once more. Thus, the rise and fall of the line represents the rise and fall of the force of the explosion. Then comes the matter of time. How soon after the explosion occurred did the pressure begin to be felt? How long did it take to reach its maximum, and how long to die out again? These questions need answers which the apparatus so far described does not give. True, the speed of the paper may be known approximately, but all that I have described will occur within the space of a fraction of a second, and it is difficult to tell the speed of the paper with sufficient accuracy. Therein, we see the purpose of the third style. It is attached electrically to the 10th of a second time marker. This consists of a weight suspended at a height. The force of the explosion lets it drop. The moment it starts to fall, it causes the style to make a mark on the paper. When it has fallen a certain distance, the style makes another mark, and the distance that the weight falls between the making of the two marks is so adjusted that the space between them on the chart represents exactly a 10th of a second. Thus, a scale is formed upon the chart by which the other times can be measured. There is the line terminating at the moment of explosion, the straight line changing into an up and down curve, representing the time and the variation of the pressure. Finally, there are the two marks representing a 10th of a second by which the other marks recorded upon the chart can be interpreted. But the mere pressure and velocity of the explosion form but a part of the knowledge desired. How the explosion is formed, whether or not the coal dust is burnt up entirely, whether, indeed, it be the dust itself which burns or coal gas given off by the dust under the heat of the preliminary explosion, what the gas is which is left by the explosion at various stages, these are important things to be known, and they can only be ascertained by taking samples of the gases in the gallery at different moments during and after the explosion. To obtain these samples, bottles are used, but the question is how to get them filled at just the right time. Into the shell of the gallery holes are drilled, and to these the metal bottles or flasks are screwed, a pipe leading from the mouth of each bottle well in towards the center of the gallery. The end of this tube is closed by a cap of glass, above which there stands poised a little hammer. Controlling the hammer is an electrical device called a contact maker, so arranged that just at the desired moment the hammer falls, breaking the glass and admitting a sample of the gas in the gallery, the bottle and its tube having previously had the air exhausted from them, so that on the glass being broken the gas is sucked in. At the same moment a weight falls, attached to the end of a cord, and this, on reaching the end of its tether, closes the end of the tube, and the sample is imprisoned until such a time as the bottle can be disconnected and taken away to the laboratory for its contents to be analyzed. The contact makers are of two kinds. In one, the pressure of the explosion raises a piston which completes a circuit allowing current to flow through the very fine wire which prevents the fall of the hammer. This fine wire being fused by the current, the hammer falls and does its work. The other kind, which are used when the force of the explosion is not enough to raise a piston, is operated by one of the tinfoil circuit breakers. A magnet, being energized by current passing through the foil, holds up a curved bar over 2 cups of mercury. Broken by the heat of the explosion, the foil cuts off this current, de-energizes the magnet, and allows the bar to fall with its ends in mercury. This completes another circuit, permitting current to pass to the fine wire, whereby the hammer is released. By connecting a bottle to a contact maker at a distance, the sample can be obtained at any desired period of the explosion. If, for instance, the sample is to represent the immediate products of combustion, it is placed near to the contact maker. Then, the sample is drawn in practically at the moment of explosion. If, on the other hand, it is the after damp that is to be sampled, then the bottle should be connected to a contact maker a long way from the seat of the explosion, with the result that its glass cap would not be broken until some considerable time had elapsed after the explosion has passed the bottle. The time also during which the bottle is drawing in its sample can be adjusted by varying the length of the cord to which the weight is attached. And last of all, must be mentioned the employment of a kinematograph capable of taking 22 photographs per second for observing the effects at the ends of the gallery. Thus, records are obtained of the force and the heat of the explosion, its mechanical and thermal effects upon the walls of the gallery, or, if it were in a real pit, the effects which it would have in shaking and in heating the workings, and the men laboring in them. This, and the analysis of the gases producing and produced by the explosion derived from the contents of the bottles, give sound data upon which can be built up reliable theories as to the nature of colliery explosions and the way to prevent them, results which could be obtained in no other way. No one can help being struck with the thoroughness and ingenuity of the means adopted to these ends, and it is no exaggeration to say that it is a splendid example of thoroughly scientific methods applied to an important industrial investigation. It will be interesting to conclude this account with a brief mention of some of the results to which these painstaking efforts have led. First in importance, the fact is placed beyond doubt that coal dust, which in bulk will only burn slowly, will, when well mixed with air, explode, and no combustible gases need to be present to aid in the explosion. The dust-raising gun, by blowing some dust into a cloud which was ignited by the second gun, caused an explosion powerful enough to do all the damage experienced in the most disastrous natural explosions. So it is practically certain that the function of the gas is but that of the first gun, to raise the cloud of dust. A typical experimental explosion may be briefly described. On the cloud-raising gun being fired, a small cloud of dust was driven out of the ends of the gallery, even that end at which the fan was blowing air in. In other words, the current of air was checked, even reversed by the preliminary shock. This cloud was, of course, shown by the kinematograph. Then, when the second gun was fired and the real coal dust explosion occurred, there was first a cloud of dust shot out larger than the other one, to be followed by a cloud of flame 180 feet long. These also were recorded by the kinematograph. The sound was heard 7 miles away. Pressures as high as 92 pounds per square inch were recorded, and the force of the blast was found to travel well over 2,000 feet per second. In many cases, strange to say, the effects were very slight at the seat of the disturbance, the force seeming to increase as the wave traveled along the gallery. Probably the dust had not time to burn completely, but only partially at the first onset. Where props or timbers checked the flow of the flaming gases, there the damage was most, for no doubt the eddies caused the air and coal to be particularly well mixed at such points. An encrustation of coke was found on the sides and the timbers after all was over, probably because there was not sufficient air to burn all the dust, and some was only heated into coke to be deposited on the nearest surface, where the tarry matters would make it stick. Finally, the most important, perhaps, of all, it was demonstrated that an admixture of stone dust with the coal dust made it non-inflammable. If a small zone were treated in this way, stone dust being mingled with the other, the explosion became stifled at that point. True, the poisonous afterdamp swept on beyond, so that men there might have been poisoned by it, but the stone zone would certainly save them from the direct effects of the blast. If, however, stone dust be mingled with coal dust all along the gallery, then no explosion at all would occur, again proving that it is the coal dust which does the damage. In the colliery adjoining the experimental gallery, this plan had been in use for years. Soft shale is ground to fine powder and sprinkled wherever coal dust has collected. It is just strewn by hand, giving the workings the appearance of having been roughly whitewashed. And since that has been done, there has been no explosion in that pit. The experiment showed beyond doubt that that was no chance occurrence. They showed that in some way, not thoroughly understood, this addition of stone dust renders the coal dust harmless. It may be that it merely dilutes it. It may be that in some way it takes some of the heat and so prevents the coal particles becoming hot enough. It may be that, being a little heavier, it checks the formation of the dust cloud. However that may be, there is no doubt now that stone dust is the salvation of the miner so far as explosions are concerned. Water sprinkled upon the coal dust, by laying it and keeping it from forming a cloud, has the same effect, but it is less convenient for the simple reason that water evaporates, while stone dust stays where it is put. End of section 11. Recording by Arvindh Sundar from Bangalore, India.
Section number 12 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Marie Neilson, Vancouver, BC. Marvels of Scientific Invention by Thomas W. Corbin. The Most Striking Invention of Recent Times, Part 1. Probably no invention has made such a sensation during recent years as wireless telegraphy, and since it is the direct outcome of the most abstruse purely scientific investigations, there could be no more appropriate subject for a place in this book. For many years there has been a belief in the existence of a mysterious something to which has been given the name of the ether. Totally different, it should be noted, from the chemical of the same name. It is entirely a creature of the intellect. None of our senses give us the slightest direct indication of its existence. No one has either seen, felt, heard, smelt, or tasted it, yet we feel that it must exist, for the simple reason that some things which our senses do tell us are utterly inexplicable without it. It was originally thought of in connection with light. Standing at night upon the top of a hill, we see the lights of a town a mile away. How is it that those distant gas or electric lamps affect our eyes? They are a mile away, and the idea that one object can affect another at a distance is one which the human mind refuses to accept. We feel compelled to believe that there is something in contact with the source of light which is affected first, and through which the disturbance, whatever it may be, is conveyed to our eyes, with which it must also be in contact. We feel that there must be a something stretching from our eyes to the distant objects, by which the light is carried. Of course the air fills the space referred to, but that cannot be the carrier of light, for if we look through a glass vessel from which the air has been exhausted, we see distant objects undimmed. We also have good reason to believe that the air belongs specially to our globe, and does not extend upwards for more than a few miles. Consequently, it cannot be air which brings sunlight and starlight. We are forced to fall back, therefore, upon the belief in something, of which we have no other knowledge, which must fill all the vacant spaces in the whole universe, passing even between the particles of which ordinary matter is composed, reaching as far as the remotest star, able to penetrate everything, and consequently not excludable from the most perfect vacuum. It is something so different from anything of which we have any direct knowledge that one is tempted sometimes to doubt whether there must not be some other explanation of light. In order to transmit light at the speed at which we find it does in fact travel, the ether must be more rigid than the hardest substance we know of. Many, many thousand times more rigid, indeed. Yet it seems to offer no resistance to the passage of the planets through it. Still, there is no other alternative, so far as men can conceive, and we are compelled, therefore, to believe in the existence of the ether. The first things discovered by the telescope were the larger satellites of Jupiter. With that precision for which astronomers are noted, they soon drew up timetables, showing not only the past movements of these bodies, but also their future ones. They were soon puzzled, however, by the obvious fact that the moons of Jupiter were not working according to schedule, to use a railway expression. They got later and later for a time, then gradually quickened up until they got too fast. Then they slowed down again. This repeated itself, and is going on still, with this difference, however, that the cause has been discovered and the schedules amended accordingly. The solution of this puzzle was that when the earth and the great planet are at the same side of the sun, they are some 186 millions of miles nearer together than when they are on opposite sides of the sun. The evolutions of the satellites are quite regular according to the astronomers' calculations, but they seem to the earthly astronomers to vary, because of the time which light took to traverse that 186 millions of miles. When the two bodies were nearest together the occurrences seemed to happen about 1000 seconds (16 minutes) earlier than when they were farthest apart. Consequently, it became evident that light took 1000 seconds to travel 186 million miles, or that, in other words, it moved at the prodigious speed of 186,000 miles per second. That discovery was, of course, many years ago, but experiments since have proved the figure mentioned to be about right. It put beyond question the fact that the action of a distant light upon the eye was not an action at distance, for such action, were it possible, would take effect at once. Seeing that light passed from the distant satellites at a definite velocity and took a certain time to reach us, it was evident that it was, during that time, passing through a medium of some sort, and that medium must be the ether, for no alternative explanation will suffice. So it became recognized that light really consists of waves or undulations of some sort in the ether, that a distant, luminous body set these waves going, that they travelled with a definite velocity, and then, striking our eyes, produced the sensation known as light. Many things were found out about light in the years which followed the discovery of its velocity. The lengths of the waves were ascertained, that is to say, the distance from the crest of one to the crest of the next. The different lengths were sorted out and found to give rise to different colours, while longer waves, which produced no sensation of light, were found to carry heat, thereby explaining how the heat reaches us from a distant fire, or from the sun. Of the actual nature of the waves, however, little was known, although there was a vague idea that they were connected in some way with electricity, at which point in the story there comes in the famous name of James Clerk Maxwell, a professor of Cambridge University, who in 1864 produced before the Royal Society the explanation of the nature of the waves and their connection with electricity and magnetism. That in itself was a wonderful achievement, but far more wonderful still is the fact that he truly predicted the existence of longer waves than any then known, which no one knew how to cause, or how to detect if caused. That prediction has since been fulfilled. The long waves have been found. We know how to make them, and how to perceive their presence. They are the messengers which carry our wireless messages. The discovery of these, at that time unknown waves, on paper, by simply calculating and reasoning about them, is more marvellous even than the feat of Adams and Leverrier in discovering a planet on paper before anyone had seen it. It established Maxwell among the heroes of science for all time. A magnet acts upon a piece of iron some distance away. The pull must be transmitted through some kind of ether. A current of electricity behaves in the same way, acting precisely as a magnet, with power to affect things at a distance. Again, an ether is necessary. A dynamo works by moving a magnet past a wire which it does not touch, therefore generating current in it. There again an ether is necessary to transmit the effect from the one to the other. Taking, then, the known magnetic effects of an electric current and the electrifying effects of magnets, he was able to show that the same ether accounted for all, and for the transmission of light as well, that, in fact, there was but one ether which performed all these various duties. He proved from the known facts about electricity and magnetism that waves such as he imagined would, in fact, move with the speed of light, and once knowing the nature of the waves, he asserted that in all probability there were others of which men had then no practical knowledge. Maxwell's theory soon set experimenters searching for the means of producing the long waves which he had predicted would be found. Several authorities had before then stated their belief that the current derived from a Leyden jar was not simply a flow in one direction. They suggested, and gave grounds for the belief, that the current surged to and fro for some time before it settled down, that it swung to and fro, indeed, like a pendulum. There may be some of my readers who are unacquainted with this interesting piece of electrical apparatus, the Leyden jar. It is a convenient form of what is called an electrostatic condenser. This is two conductors, generally in the form of two plates, with an insulator between them. In the Leyden jar, the insulator is a glass jar, while the plates are coatings of tin foil, one inside and the other outside. On connecting one coating to one pole of a battery, and the other to the other pole, they become charged, one positively and the other negatively. One, that is, acquires an excess of electricity, while the other becomes deficient to an exactly similar extent. When the two are afterwards connected by a wire, the surplus on one flashes through it to make good the deficiency on the other. Rushing first of all from positive coating to negative, electrical inertia causes it to overshoot the mark and to recharge the jar with the charges reversed. Then current begins to flow back again, doing the same several times over until at last equilibrium is established. The power to absorb and hold a charge of electricity, which is the characteristic of a condenser, is called capacity. What, then, is electrical inertia? I have already referred to the effect which the creation of a magnetic field around a current has upon neighboring conductors. It also has an effect upon itself. As soon as the current begins to flow it builds up the magnetic field, and in the process some of its energy is exhausted. On the original current ceasing, however, the magnetic field collapses back on to the conductor once more, and in doing so restores that energy. This occurs whenever current flows, but it is specially noticeable in long conductors, like submarine cables. In them the battery has to act for a considerable time before any current reaches the farther end. It is in the meantime employed in building up the magnetic field around the wire. Then, when the battery has ceased to act, the current still comes flowing out at the farther end. The magnetic field is giving back the energy expended upon it. Thus a current is reluctant to start flowing through a conductor, and, having started, is disinclined to stop. This is called inductance, and it has exactly the same effect upon the current that inertia has upon a body. What inertia is to a material body, inductance is to an electric current. And lastly, the resistance which the conductor offers to the passage of the current is precisely analogous to the friction of the water in a pipe. So we see the capacity of the two coatings of the jar and the inductance which occurs in the connecting wire cause the current to oscillate to and fro for a while when the jar is discharged, which surging or oscillation is ultimately stopped by the resistance of the wire. The two coatings and the wire form what is called an oscillatory circuit. We can now resume our story. After much experimenting, Hertz of Karlsruhe discovered the fact that when a discharge was taking place in an oscillatory circuit, tiny sparks passed between the ends of a curved wire held some distance away. His apparatus is illustrated in Figures 6 and 7. The former, which is termed nowadays a Hertz oscillator, is simply two metal discs almost connected by a thick wire. The wire is broken, however, at the centre, and the two halves terminate in two metal balls. Each ball is connected to one terminal of an induction coil. Now the current comes from an induction coil in a series of spurts. It is not an alternating current exactly, since every alternate current is so feeble as to be negligible, but it is practically an intermittent current always in the same direction. Thus we may call one the positive end of the coil and the other the negative. A short current comes along with every backward movement of the little vibrating arm which forms a part of the apparatus. This breaking of the primary circuit may take place perhaps 50 times per second, so that the intermittent secondary currents will succeed each other at intervals of a 50th of a second, or even less. The brain reels at the attempt to think of a 50th of a second, but it is really quite a long interval as these things go, and during that interval quite a lot happens, for the current first of all charges the two plates as a condenser. When they are as full as they will hold, the current overflows, as it were, across the gap between the two balls. Now an air gap, a gap that is filled with air, between two conductors, is a very strong insulator. But when current has once broken through it, it becomes a fairly good conductor. Hence, as soon as the first spark has passed between the two knobs, the plates become connected almost as if a wire were passed from one to the other, and there we have quite a good oscillatory circuit. There is capacity at each end and a fairly long length of wire to provide the inductance. Consequently, that breakdown of the insulation of the air in the spark gap is followed by electrical oscillations which take place with inconceivable rapidity. Yet, because of the resistance of the spark gap, which is considerable even after it has been broken through, the oscillations do not continue for long. They have died away long before the lapse of the 50th of a second, when the next impulse comes along from the coil. In the meantime the air gap regains its insulating properties, and so, on the arrival of the next impulse, the whole thing occurs once more. Thus a little train of oscillations is produced for every impulse from the coil. Every train causes a corresponding disturbance in the ether, and sends off a train of electromagnetic waves, and these, falling upon the distant wire, generate it in a train similar to that which brought them into being. These trains, in Hertz's simple apparatus, manifested themselves in the form of minute sparks leaping across the small gap between the ends of the curved wire. Fig. 7. It was in 1888 that Hertz made this discovery of a way to detect long electric waves. He subjected the matter to many more experiments, and found that the waves have many points in common with light rays. He found that they were reflected from certain surfaces, just as light is reflected from the surface of a mirror. He made prisms which were able to bend them as light waves are bent by prism of glass. Some things appeared to be transparent to them, as clear glass is to light, while others are opaque. It does not follow that the same things which reflect light waves reflect electric waves, and so on. The latter can pass through a brick wall, for example, but the same divergence is to be observed between light and radiant heat, of which the action of glass is a familiar example. Clear glass will let light through almost undimmed, yet we use it for fire screens to shield us from too much radiant heat. The important fact is that all three, light, radiant heat, and Hertzian waves, in addition to travelling at the same speed, are reflected, absorbed, or refracted, according to precisely the same principles. This is almost perfect testimony to their essential identity. The difference between them, as has been said already, is the distance from crest to crest of the waves, the wavelength, that is, and the reader will wonder by what manner of means this mysterious dimension can be ascertained. In spite of its seeming mystery, the method is very simple. It is based upon the fact that two sets of similar waves travelling at the same speed in opposite directions interfere with one another in a peculiar way. Suppose that one set of waves travel along to a reflector and strike it vertically. Then another set will travel back from the reflector exactly similar to the first, except that their direction will be opposite, and the result will be that at certain intervals they will exactly neutralize each other, so that at those points there will be no wave action appreciable at all. Those points where no action is to be perceived are called nodes, and they are exactly half a wavelength apart. This will be quite easily understood from the accompanying diagrams. In each of these diagrams the set of waves marked A are supposed to be moving from left to right, while those denoted by B are reflected back and are moving from right to left. It will be noticed that each wavy line has a straight line drawn through it, dividing it into alternate crests and hollows, which line is known as the axis of the waves. Now notice that in Fig. 8 there are points marked X, where the A waves are just as much above the axis as the B waves are below it, and vice versa. Hence, at those points, the two sets of waves will neutralize each other. Now turn to the next figure which, be it remembered, shows the same waves a moment later, when they have moved a little farther on in their respective journeys, and it will be seen that there, too, are places marked X where the two sets of waves neutralize each other, and the same with the third diagram. And finally observe that the places marked X are always the same in all diagrams. That is to say, they are always the same distance from the line on the right-hand side, which denotes the reflector. It will be clear, too, that each node is half a wavelength from the next. Thus it can be shown that at every moment, and not merely at the three indicated in the diagrams, the two sets neutralize each other at the nodes, that the nodes are always in the same places and half a wave length apart. Everywhere else, except at the nodes, there is action more or less energetic, but there is a perpetual calm. But how can we tell where the nodes are? When we recollect that they are points at which no wave motion at all takes place, it is easy to see that we shall at those points get no spark in our detector. So what Hertz did was to set his oscillator going so that it threw waves upon a reflecting surface, and then move his detector to and fro in the neighbourhood until he found the nodes. Between the nodes, as will be seen by an inspection of the curves once more, there are other points at which the wave action will be twice as great as with the single wave, and so at those points the response of the detector would be especially energetic. This mutual action between an incident wave and a reflected wave is termed interference, and by it the wavelengths of all the ethereal waves have been measured. The plan used in the case of light waves, although the same in principle, is somewhat different because of the extreme shortness of the waves. So the experiments of Hertz not only showed that long electric waves existed, but that they were in all essentials similar to light, and their wave-lengths were ascertained. On that basis has been built up modern wireless telegraphy. It may be interesting to mention at this point a very curious and in a sense pathetic incident. Professor Hughes, whose name is associated with certain well-known instruments for ordinary telegraphy, 9 years before Hertz's discovery noticed that a microphone was affected by the action of an induction coil some distance away. He himself attached some importance to the matter, but he allowed himself to be dissuaded from following up the discovery by other scientists, more eminent than himself at the time, who thought that it was not a promising field for investigation. But for the influence of these friends he would possibly be the hero of this story in place of Hertz. Professor Sylvanus Thomson has said that he too noticed the sparks produced at a distance when a Leyden jar was discharged, but he makes no claim to precedence over Hertz, since, seeing the phenomenon, he did not perceive its real meaning, while Hertz, though a little later in time, realized the profound significance of it. Hertz himself in the account of his experiments is generous enough to assert that, had he not discovered the waves when he did, he is quite certain that Sir Oliver Lodge would have done so. Before proceeding to describe the principal apparatus used in the wireless station, I should like to devote a little space to the explanation of a term which will come up again and again, and which represents that which is responsible in the main for the marvellous advances which the art of sending wireless messages has achieved in the last few years. I refer to resonance. It will be a great help if the reader will try for himself a simple, inexpensive little experiment. Stretch a string horizontally across a room, and onto it tie 2 other strings, so they hang down vertically a little distance apart. To the ends of the 2 strings tie some small objects. A cotton reel on each will answer admirably. They will thus form 2 pendulums, and to commence with, they should be just the same length. Having rigged all this up, give one pendulum a good swing. It will impart motion of a to and fro variety to the supporting string, which in its turn will pass that motion on to the other pendulum. In a very short time, then, the second pendulum will be vibrating like the first. Indeed, the whole motion of the first will shortly become transferred to the second, so that the second will be swinging and the first still. Then the second will retransfer its energy back to the first, and so they will go on until the original energy given to the first pendulum is exhausted. The point to be observed is the quickness with which one pendulum responds to the impulses given it by the other, and the ease with which the energy of the one passes to the other. Now reduce the length of one pendulum. On setting the first in motion, a certain irregular spasmodic action is to be observed in the second, but it is very different from the whole-hearted response in the previous instance. In the former case the second one responded naturally and readily to the first. Now its response is reluctant in the extreme. It moves somewhat because it is forced to, but it is apparently unwilling. Energy has to be impressed upon it. There is no readiness, because there is no sympathy between them. That sympathy between the 2 equal pendulums is resonance. The same occurs between 2 violin or piano strings when they are in tune. The explanation is that a pendulum has a certain natural frequency which depends upon its length. Another pendulum of the same length, arranged as just described, therefore imparts impulses to it at just the frequency which is natural to it. Consequently, the effect is a cumulative one, and it responds quickly. Impulses at any other frequency tend more or less to neutralize each other. In the same way, a string of certain length and a certain tension has a frequency peculiarly its own, and it will respond to another similar string because the other gives its impulses at its own natural frequency. It is on record that an engine in a factory happened to run at precisely the same speed as the natural frequency of the building, with the result that after a little time the structure shook so much that it collapsed. Now, electrical circuits in which currents oscillate have a natural frequency of their own. That frequency depends upon the 2 electrical properties of the circuit, capacity and inductance, and if you want to set up an electrical oscillation in any circuit, you can best do it by giving it impulses at intervals which agree with its natural frequency. Sir Oliver Lodge seems to have been the first to appreciate fully the effects of resonance in wireless telegraphy. It is strange that in England the work of this eminent man in wireless matters is not more fully recognized. When wireless telegraphy reached the point at which the public became interested, Marconi was just coming to the front, and so, forever, will his name be foremost in the public estimation. Indeed, more than foremost, for in the minds of many he monopolizes the credit for this invention. Many people are under the impression that he is the one and only, or at any rate the original, inventor of wireless telegraphy. Now Marconi has done exceedingly valuable work in this field. Moreover, he has been the means of placing the affair on a good commercial footing. By all the same, he is by no means the original or only inventor. While admitting that he is a remarkable man who has done wonders, it is only common justice to refer to the others whose contributions to the solution of the problem are possibly of equal value, and of these few can compare with Sir Oliver Lodge. End of section 12. Recording by Lynda Marie Neilson, Vancouver, BC. Section number 13 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Marie Neilson, Vancouver, BC. Marvels of Scientific Invention by Thomas W. Corbin. The Most Striking Invention of Recent Times, Part 2. But to return to the question of resonance. At first, the distances over which messages could be sent were but small. Now a Marconigram can be flung across a hemisphere. At first, little could be done by day. Work had to be done mainly at night. Now communication passes by day and night alike, yet in principle and in many details the instruments are unaltered from what they were several years ago. The main source of all this improvement is the use of resonance. To enumerate broadly the apparatus used for the dispatch and receipt of messages, the following list will be useful. Transmitting end. 1. An antenna, consisting of a number of wires raised to a considerable height above the ground. 2. A spark gap, consisting of a series of metal balls with gaps between them, the outer ones being connected to the antenna and to the induction coil. 3. A powerful induction coil, with batteries or other source of current to work it. 4. A telegraph key, by which the induction coil can be started and stopped at will. Receiving end. 1. An antenna precisely similar to the other. 2. A coherer or other oscillation detector. 3. A receiving instrument, which may be a writing telegraph instrument, a telephone, any of a number of ordinary telegraph instruments, or a galvanometer. Transmitting and sending instruments are, of course, installed at both ends, and either of them can be connected to the antenna at will by the simple movement of a switch. The antenna plays part of one of the metal plates in the Hertz oscillator. Early experiments were made with Hertz apparatus, but the range of such a contrivance is very limited. For one thing, it neglects to take advantage of the earth. It is little realized what an important part the earth plays in the carrying of wireless messages. A very great step was taken when Marconi dispensed with one of the plates of Hertz and used the earth instead, while the other plate gave place to the elevated wires, the most familiar part of the apparatus to most people. The condenser is thus formed by the earth as one plate, the elevated wires as the other, and the intervening air as the insulator. The capacity must be exceedingly small in such an apparatus, but it is sufficient. while the long lines of electrical force stretching from the high antenna to the earth produce waves of great carrying power. Lastly, when the earth forms a part of the condenser, the waves cling to it, so that instead of being largely dissipated into space, they move along the surface of the earth. The advantage of this is obvious. At first it was customary to place the spark gap in the wire leading from the antenna to the earth, as in the accompanying sketch. Later, however, it was found better to place the coil and spark gap in a local circuit in which the oscillations are first produced. These oscillations pass through a coil which is interwound with another one connected to the antenna and to earth, and thus the local oscillations, as we might call them, induce similar oscillations in the antenna, just as the fluctuations in one part of an induction coil induce fluctuations in the other. Indeed, the coil in the local circuit and the one in the antenna circuit actually constitute an induction coil. The advantage of this is that by introducing condensers, the capacity of which can be varied, and coils of the inductance of which can be varied, into the oscillation circuit, it becomes possible to tune the circuits effectively. Thus resonance comes into play and the power expended can be made to produce the maximum effect. Some attempts have been made to displace the induction coil in wireless telegraphy altogether by a specially made dynamo. These machines can produce either alternating or continuous currents. In fact, the alternating current dynamo is really simpler than the more familiar continuous current machine. The difficulty is, however, to run it sufficiently fast to produce sufficiently rapid alternations. Nikola Tesla made an alternator, to give the alternating current dynamo its short title, which could produce 1,500 alternations per second, while Mr. W. Duddell made one which produced 120,000, but neither was satisfactory for the work in question. Could such a machine be made, would it be invaluable, for it would be apparent that a continuous succession of waves would be formed by it, and not a succession of short trains of waves such as is produced by the induction coil and spark gap. The difficulties are not electrical, but mechanical. It seems doubtful if a machine will ever be made to run with sufficient rapidity which would not knock itself to pieces in a very short time. Small alternators are used sometimes, however, to supply alternating current to the primary of an induction coil, or transformer, as it is more often called in larger sizes. The interrupter is only needed when the primary current is continuous, from batteries, for example. Alternating current needs no interrupter, and so that bother is removed. The alternations of 100 or so per second, which are quite the common thing with alternators, are just what is needed to excite an induction coil. Consequently, small machines of this kind are to be found in many stations. A Danish inventor, Vladimir Poulsen, has adopted an altogether different method of producing electrical oscillations, which method is the distinctive feature of his mode of telegraphy. He takes advantage of a curious effect of passing current between two rods, one of which is carbon, so as to form an arc, such as we see in arc lamps. My readers are already familiar with the term shunt in connection with electrical matters, and so will perceive at once what is meant when a second circuit is said to be arranged as a shunt to the arc. The accompanying diagram will in any case make the matter clear. The current comes along from the battery or continuous current dynamo to a hollow rod of copper which, to prevent it being melted, has cold water continually circulating inside it. Thence the current jumps across to a carbon rod, forming an arc between the two rods, and returns whence it came. In its journey it traverses the coils of an electromagnet, the poles of which are one each side of the arc. This tends to blow the arc out, as a puff of wind blows out a candle, an effect which a magnet always has upon an electric arc. The shunt consists of a wire leading from the copper to the carbon rod, with a condenser and inductance coil inserted in it. The latter coil also forms one part of that coil, by which the oscillations in the local circuit are transferred to the antenna. The electrical explanation of what happens when the current is turned on to an arrangement like this is rather too complex to set out here. It depends upon a curious behaviour of the arc. It is really a conductor, yet it does not behave as ordinary conductors do, and the result is that the continuous current flowing through the arc is accompanied by an oscillating current in the shunt circuit. And the important feature of the arrangement is that these oscillations are continuous, in one long train, not in a succession of trains. The advantage of this has already been referred to. One other feature of the apparatus just described should be mentioned, since it will seem curious to the general reader. For it to work properly, it is necessary that the arc should be enclosed in a chamber filled with hydrogen or hydrocarbon gas. Coal gas is generally used. Hertz's original discovery was that small sparks could be seen to pass between the ends of a curved wire when the electric waves fell upon it. Such spark detectors, as they are called, are useful in the laboratory, but not for practical telegraphy. Several people seem to have noticed in years gone by that a mass of loose metal filings, normally a very bad conductor of electricity, became a much better conductor when an electrical discharge of some sort occurred near by. The demand for a wireless receiver had not then arisen, however, and so the discoveries were not followed up. Consequently, it remained to be rediscovered by Branly, of Paris, in 1890. He placed some metal filings in a glass tube, the ends of which he closed with metal plugs. Lying loosely together, the filings would not conduct the current of a small battery from one plug to the other, but when a spark occurred not far away they suddenly became conductive and allowed it to pass. Several years after this, Sir Oliver Lodge took up the idea as a receiver for wireless messages, and believing that its action was due to the waves causing the filings to cling together, he christened it coherer. Marconi succeeded in making a very delicate form of this, although working on strictly the same lines. The trouble with coherer is that when once it becomes conductive, it remains so unless the filings be shaken apart. Lodge therefore arranged for the tube to be continually struck by clockwork or by a mechanism like that of an electric bell. Marconi effected a further improvement by making the current passing through the coherer control the striking mechanism, so that the latter is normally quiet but administers one or two taps at just the right moment. Sir Oliver Lodge and Dr. Muirhead devised another detector which, though quite different in form, is really much the same in principle. A steel disc with a sharp knife-like edge is made to rotate above a vessel of mercury. The edge just touches the mercury, but no more. On the top of the mercury there floats a thin layer of oil, a bad conductor. Now, as the disc revolves, it picks up on its edge a film of oil, which it carries down into the mercury. The film adheres so tightly that it prevents the moving disc from actually touching the liquid metal. Thus, under normal conditions, the two are electrically insulated from each other by the film of oil, and no current can pass from mercury to disc. Oscillations, however, caused by incoming electric waves are able to break through the oil film and so bring disc and mercury into contact, whereupon the current flows. The constant movement of the disc restores the oil film as soon as the oscillations cease. The reason why these detectors act as they do is not quite understood. One suggested explanation is that the oscillating currents heat the particles and so partially weld them together. Another is that adjacent particles become charged as the plates of a minute condenser, and so are drawn tightly together as the plates in an electrostatic voltmeter are drawn towards each other. Supposing that the original non-conductivity of the loose fillings be due to the film of air which may surround them, either of these things would account for the film being broken or squeezed out, resulting in better contact and improved conducting power. But both suggestions seem to be contradicted by the fact that if the pieces in contact be of certain substances, the coherer works the opposite way. Under those conditions, the conductivity is normally good, but the influence of the incoming waves causes it to become bad. In 1896, Professor Rutherford, now of Manchester, described some discoveries which he had made as to the magnetic effects of oscillations. A simple little contrivance which he had constructed was operated by the discharge of a coil half a mile away, at that time a great performance. This detector was simply an electromagnet with a steel core instead of the usual soft iron core. The reason the latter is used in the ordinary magnet is that it loses its magnetism the moment the current ceases to pass through the coil with which it is surrounded, while a steel core retains its magnetism. For most purposes a steel core would render an electromagnet useless, but in this case it was desired that the core should be permanently magnetized. So a current was first passed through the coil to magnetize the core, and then the coil was connected to a simple form of antenna, while swinging magnet was brought near so the magnetic power of the core would be indicated and any change made apparent. The effect of the discharge half a mile away was to demagnetize the core slightly. This was shown by the movement of the swinging magnet, and so the first magnetic detector was found. But here, perhaps, I ought to explain the use of the antenna at the receiving station. Its function at the sending end has already been made clear. The electromagnetic waves, coming from the distant transmitter, strike the receiving antenna and, in doing so, set up in it oscillations such as those which set them in motion. For every oscillation in the sending antenna there will be another, similar in every respect, except that it will be feebler, in the receiving antenna, and the oscillations are here led to the detector, of whatever form it may be, and in it they make their presence felt. In some few cases a Duddell thermogalvanometer has been employed as the detector, in which the oscillating currents report themselves directly. In coherers the detector works by causing the oscillating currents to control a continuous current from a battery, and it is the latter which actually gives the signal. But there are a number of extremely interesting means which have been invented to detect the oscillating currents by their heating effect. R.A. Fessenden, for instance, has perfected one which is a marvel of delicate workmanship. He depends upon the heating of a wire by the currents passing through it. Such heating is the result of the electrical force acting against resistance, and the difficulty is that if the resistance be great it will almost entirely kill the faint oscillating forces in the receiving antenna, while if, on the other hand, it be small, the rise in temperature will be inappreciable. So he encloses a fine thread of platinum in a glass bulb from which the air is exhausted. The platinum wire is first of all embedded in a wire of silver. The silver wire is given a core of platinum, in fact. Then the compound wire is drawn down until it is so thin that the platinum core is only 1½ thousandths of an inch in diameter. A short length of this compound wire is then bent into an U-shaped loop and its ends connected to thicker wires. Finally, the bottom of the loop is immersed in nitric acid, which eats away the silver at that point and leaves the bare platinum. This is produced a very short length, a few millimeters, of exceedingly thin platinum wire supported at its ends by comparatively thick wires. Being so short, this wire does not offer much resistance, and consequently does not materially check the oscillations. At the same time, since it is so fine, it does offer some resistance, and finally, since what heat is generated will be in an exceedingly small space, it will be appreciable there. A telephone is arranged so that the current also passes through the fine wire, and every slight variation in the temperature of the platinum wire, by varying in its resistance, varies the current through the telephone, and exceedingly slight variations can be detected by sound in the telephone. Thus the oscillations generated in the antenna affect the heat in the wire, that affects its resistance, and that again affects the telephone, which finally affects the ear of anyone who is listening to it. It must be understood, however, that this is not a wireless telephone, for the sounds heard are not articulate but merely long and short sounds, representing the dots and dashes of the Morse code. Electrolysis provides us with another form of detector. An exceedingly small platinum wire forms one electrode and a large lead plate the other, and both are immersed in dilute acid. The passage of current from a local battery sets up electrolysis, and so stops itself from forming a film of oxygen on the small electrode. This film, however, is broken by the oscillating currents from the antenna, so that as long as they are coming the battery current can flow, but as soon as they cease the battery current stops itself again. Thus the flowing and stopping of the oscillating currents is exactly copied by the current from the battery, which current is led through a telephone or a sensitive galvanometer. It may occur to readers to inquire why the oscillating currents are not passed direct to a galvanometer. The answer is that because they are oscillating, a very sensitive galvanometer is not possible. True, the Duddell thermogalvanometer has been mentioned in this connection, but although it is a beautiful instrument it cannot compare for delicacy with the direct current galvanometers. The latter are easily 100,000 times more sensitive, but the trouble can be overcome by rectifying the oscillating currents, by passing them through a unidirectional conductor, one, that is, which passes current one way only. These remind one of a turnstile as installed at certain public places, which let you out, but will not let you in unless you pay. In fact, they will not let you in at all. In like manner, rectifiers will only allow those currents to pass which are flowing in one direction, and so they cut out every alternate oscillation, thus producing something very like continuous current, which can be detected by the very delicate galvanometers which are usable when continuous currents are concerned, or more often by a telephone receiver. The rectifying conductors are in many cases crystals, hence these detectors are called crystal detectors. Carborundum is a favourite for this purpose. And that brings us to the important question of the secrecy of wireless communication, and the measures taken to prevent confusion from the number of independent messages flying through the air at the same time. This can be largely achieved by the aid of resonance. Trains of waves flung out by one antenna may strike several other antennae, but unless the latter are in tune with the sending apparatus, they will probably not be affected appreciably. Let one of them, however, be in tune, and it will pick up easily the message which is not noticed by the others. It is as if three people watching a distant lamp were affected by a form of colour blindness, which rendered them practically blind to all colours except one. Suppose one could see red only, the other blue, and the third yellow. A light sent through a blue glass, being robbed of all rays except the blue ones, would be visible only to the man who could see blue. The man who could see the blue would, in like manner, be quite blind to light sent through red or yellow glass. Each of them, in fact, could be signalled to quite independently of the others by simply sending him rays of the colour to which his eyes were sensitive. In precisely the same way, each wireless receiver is or can be made most sensitive to waves of a particular length and practically blind to others. The operator can adjust his apparatus for certain prearranged wave lengths, and so he can communicate with secrecy to stations whose wavelength he knows. The change, of course, is made by altering the capacity or inductance, or both. The instruments can be so calibrated that it is quite easy to make the alteration. Then, antennae can be so constructed that messages can be received with most readiness from one particular direction. In others they can be received from any direction, but the direction can be discovered. This, it will be easy to see, is of great value to ships in a fog. Antennae made with a short vertical part and a long horizontal part radiate best in the direction away from which their horizontal parts point. This is of great advantage in stations which are built specially to communicate with other particular stations. In such cases the antenna is carefully built so as to point in the required direction. Such antennae also receive more readily those signals which come from the direction away from which they are pointing. Reference has been made already to the interesting fact that wireless communication is easier at night than in the daytime. That is probably because of the ionization of the atmosphere by the action of sunlight. Along with visible sunlight there comes to us from the sun a quantity of light known as ultraviolet. since it makes its effect known in the spectrum of sunlight beyond the violet, which is the limit of visibility at one end of the spectrum. We cannot see it, but it affects photographic plates powerfully. It has energetic chemical powers, and it has the ability to make the air more conductive than it is ordinarily. Comparatively little of it penetrates our atmosphere, but it must exercise a good deal of influence. A little higher up. Now readers will remember that the process by which electromagnetic waves are propagated is checked when the wave strikes a conductor. The energy in the waves is then employed in causing currents in the conductor instead of forming more waves, and so partially conductive air forms a partial barrier to the waves. The effect is not appreciable in the case of the tiny waves of light and heat, but it is in the case of the long wireless waves. Everyone has seen the waves of an advancing tide coming up a sandy beach, and has noticed how the dry sand, a good conductor of water, sucks up and destroys the foremost ripples. In like manner are the wireless waves, sucked up by the partially conductive atmosphere, but the effect of the ultraviolet light does not last long, and so at night time it disappears. Therefore messages can be sent better at night than by day. For wireless telephony, what is wanted is a continuous uninterrupted train of waves, such as those from the Pelton arc, and a receiver of the magnetic type. The coherer is no good for this purpose, since it either stops the current entirely or lets it flow copiously. The magnetic detectors, however, respond to the variations in the strength of the incoming waves. As the latter increase or decrease in strength, so does the magnetic detector give out stronger or weaker signals. So a telephone transmitter of the ordinary type is made to vary the strength of the oscillations at the sending end, while an ordinary telephone receiver is placed in series with the detector at the receiving end. Thus every slight variation corresponding to sound waves spoken into the transmitter is reproduced in the receiver. It is strange that wireless telephony has not made greater progress, for it may be said, on the word of one of the greatest authorities, that wireless telephony is simpler and easier than telephony through a submarine cable. In the latter there are almost insuperable obstacles caused by the capacity and inductance of the circuit, while in the wireless method there is very little difficulty. There are, of course, several so-called systems of wireless telegraphy in use. There is the Marconi in Great Britain, the Secret Admiralty system in the British Navy, the De Forest in the United States, the Telefunken in Germany, not to mention the promising Pelton system, and there are still others, but it would be futile to attempt to explain how they differ from one another in a work like this. In principle they are alike. The precise forms of instrument used may vary, but even there is much in common between them. As time goes on, there will inevitably be a tendency to more and more uniformity. That is always the case, for some things are inherently better than others, and rival systems, although each is working along its own lines, always come to very much the same result in the end. Without making any comparisons, it is safe to say that if the Telefunken system, for example, has any points of superiority over the Marconi, the latter will sooner or later find out the fact, and will modify their apparatus accordingly. In all probability this will operate both ways, and some things which the German system is now using will give place to those which British have in operation. In another very modern industry this is very apparent. Having attended and carefully studied several annual exhibitions of flying machines, I have noticed with great interest how the varying types of a few years ago are merging into the more or less uniform types of to-day, and it has been the same with wireless telegraphy, and will be still more so in the future. The best means of generating the waves and the best means of detecting them at a distance, that is the whole problem, and all the workers in it will sooner or later come to much the same conclusions as to which are the best ways. Patents may do a little to delay this, but not much. For one thing, patents only last a few years. For another, a patent only covers a particular way of doing a particular thing. A machine that is termed patent is often the subject of 100 patents, each covering a particular little point. It is well nigh impossible to patent a whole machine. A general principle cannot be patented, only a particular application of that principle, and so there are in a great many cases little variations of a patented method which are quite as good as the patented one, and which can be used freely. So even patents will not have much effect, in all probability, upon this unification process. But however that may be, there is no doubt that the whole world owes a deep debt of gratitude to the men who have worked out this most beneficent of inventions. It is difficult to think of a single one which has ever brought such a load of benefits to poor, struggling humanity as this has. The ship in distress, the lighthouse man on his lonely islet, the explorer in the polar regions, the pioneer settler in the new lands, in fact, just those who most need some connecting link with their fellows, are the people to whom the wireless telegraph brings aid and comfort. All honor to the men who have done it. End of section 13. Recording by Lynda Marie Neilson, Vancouver, BC. Section 14 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Marie Neilson, Vancouver, BC. Marvels of Scientific Invention by Thomas W. CORBIN. How Pictures Can Be Sent by Wire. The sending of a message by telegraph is easily understandable. Various combinations of two simple signs, such as short sounds and long sounds, can readily be made to indicate letters by which the words can be spelt out. Nor does the sending of sound over a wire make a very good demand upon the credulity. We all know that sound consists of innumerable little waves in the air, and by the simplest of devices these can be converted into variations in an electric current, which variations, by means equally simple, can be made to reconvert themselves back into sound waves at the other end. But to transmit a picture is another matter altogether. It seems barely possible in the case of a drawing, such as a pen and ink sketch, which consists of a comparatively small number of definite lines, but with a shaded sketch or a photograph with its gradations of light and shadow, to transmit such would seem to be beyond the bounds of possibility, did we not know that it had been done. The description of the methods will therefore constitute a not uninteresting subject for a chapter. It is worthy of remark that an attempt along these lines was made many years ago by a man named Kasper, and a description of this pioneer apparatus will form a good introduction to the later developments. In Figure 13 we see a square which represents a sheet of tinfoil, upon which is drawn in non-conductive ink a simple geometrical figure. The ink may be grease or shellac varnish. Indeed, there are many substances which are available to use as an insulating ink. Across the square there are a number of parallel dotted lines, but these, it must be understood, are not actually drawn upon the foil. Their purpose will be apparent in a moment. Suppose that we connect the foil to one pole of a battery and the other pole by a flexible wire to a metal pen or stylus. If we place the point of the pen in contact with the foil, we make a complete circuit, through which, of course, current will flow. But if with it we touch one of the non-conductive lines, there will be no current. Taking a ruler, then, let us draw the point of the stylus across the foil in a series of parallel straight lines. It is these excursions of the stylus which the dotted lines are intended to represent. For nearly the whole of the time current will be flowing, but whenever the stylus is crossing one of the lines of non-conductive ink, there will be a momentary cessation. Thus, the reader will begin to perceive we obtain what we may call an electrical representation of the figure drawn upon the foil. And now let us turn to Figure 14. There too is a square, but in this case it is not foil, but paper which has been soaked in prussiate of potash. The reason for introducing this chemical is that it is susceptible to electrical action. Wherever current passes through it, it becomes changed into pursuant blue, so that if we place the point of the pen upon the paper and cause current to flow out of that point through the paper, there we get a blue dot. If while the current is flowing we draw the pen along, we get a blue line. Figure 13 therefore represents in principle the sending apparatus of Kasper's writing telegraph, while Figure 14 represents the receiving instrument. The two pens are connected together by the main wire, in such a manner that, when the point of the one is in contact with the bare foil, current flows out of the other and into the paper, but as the former crosses an ink line all current ceases. If then, while the sending pen is drawn line by line across the foil, the other is drawn at the same speed, line by line, across the chemically prepared paper, we shall get on the latter a series of lines as shown in Figure 14, almost continuous, but broken here and there. Each breakage represents a passage of the sending pen across a line, and taken together, as will be seen, they constitute a reproduction of the geometrical figure drawn upon the foil. As shown, the lines are rather far apart, and so the reproduction is not a very good one. They are only drawn so, however, in order that the principle may be shown the more clearly. They may be drawn so that they overlap, and then the effect is much better, the received picture being almost an exact reproduction of the other. It will be noticed that an essential to the success of this method is that the two pens should move in perfect unison, and that was the great difficulty. Kasper used an arrangement of pendulums, the best thing available at the time. The reproduction is, in photographic language, a negative, a somewhat unsatisfactory feature of the method. A simple modification, however, of the electrical connections will reverse that, so that the reproduction shall be a positive. There are two ways of cutting off a current from any particular circuit. One is to interpose a resistance, through which current cannot pass in an appreciable quantity, and the other is to provide a second path for the current so much easier than the first that practically all the current will pass that way, leaving the first circuit, to all intents and purposes, free. It is as if a farmer wished to stop people passing across a certain field. Two methods would open to him, one to put up a high gate over which no one would dare to climb, and the other to provide a shortcut so much more pleasant and convenient than the old path that no one having the choice of the two ways would think of going the old way. What the farmer would call a short-cut the electrician calls a short circuit, and a short circuit is often a more convenient way of cutting off a current than a switch which interposes resistance. At all events, in a case like this, a short circuit enables that to be accomplished which would be very difficult by any other means. In the apparatus as already described, the battery had to drive the current along a long wire, terminating at the distant receiving instrument, whence the current returned via the earth. The foil and pen, acting as a kind of electrical tap, controlled this. When foil and pen touched, the tap was open and current flowed. When the line of non-conductive ink interposed itself, the tap was off and the flow ceased. But connect the battery directly to the wire, and place the foil and pen in a short branch circuit, and the whole thing is reversed. Then the opening of the tap sent current to the other end. Now the opening of the tap causes it to flow round the short branch and leave the main wire. Then the closing of the tap stopped the current reaching the farther end. Now it causes it to do so. In fact, the entire action of the apparatus is completely reversed, and the bare parts of the foil become represented by blank paper, while insulating lines produce the marks. In short, a positive results instead of a negative. Such was the scheme of Caselli years ago. It is mentioned here at some length, since the principle of it largely reused in an improved form in the most successful of modern apparatus for a like purpose. It undoubtedly was a very excellent scheme, simple and effective, which ought to have succeeded, but it did not do so for the sufficient reason that at the time knowledge of electricity and skill in constructing delicate mechanism were not so highly developed as they are today. For success, as has already been said, one thing was essential, and that thing very difficult to obtain, a perfect synchronism between one stylus and the other. If the one were but the slightest degree out of step with the other, failure followed inevitably. So the electrical transmission of sketches dropped for the time being. More recently, a perfect successful solution of the problem has come in another way altogether. This apparatus, at first called the telautograph, but now known as the telewriter, it will be more convenient to refer to later. Of modern systems for the transmission of pictures, the most successful probably are the Korn telautograph and the Thorn-Baker telectrograph. Both of these are able to transmit very fair reproductions of photographs besides line drawings. The difficulty with photographs is, of course, that many parts of them are not of equal blackness or whiteness, but shade off gradually from one into the other. Take the case of a simple portrait. Part of the subject's face will be pure white, while the side in shadow will be comparatively dark. There is not hard and fast line between the two, but a graduation through an infinite number of shades. the one tones into the other. How can it be possible to convey that, more or less mechanically, over a wire? The solution is due to the fact that the eye will blend together a number of distinctly different shades, if properly arranged, into a gradual change. Really, the change is step by step, but the effect is apparent quite continuous. This can be seen in the half-tone illustrations in this book. Close examination will show that a picture is cut up into small squares. In the pure white part of the squares are invisible, while in the perfectly black parts, if there be any, they are so merged into one another as to be inseparable. But everywhere else in the picture it will be seen there are squares each with a dot in the middle. In the darker parts the dots are large, in the lighter ones they are small. We get the effect almost of colour, although the picture is done entirely in black ink. The eye does not see the individual dots when we are just looking at the picture. We have to examine it very closely to find them. Yet they are there all the time, and it is simply the peculiar action of the eye which sees beautiful half-tones, shading imperceptibly one into another, whereas in real fact there are only a vast number of equidistant dots, all equally black. We see, therefore, that it is possible to split up a picture of any kind into a number of small squares, and to treat each square as being of equal darkness throughout. Then, if we can communicate by wire that particular degree of darkness to a distant station, where the small parts can be put together in their proper order and given their correct shade, the picture as constructed at the receiving end will be something like that at the sending end, and we have only to make the size of each separate square small enough to obtain copy which will resemble the original very closely indeed. In the early days it was actually proposed to telegraph pictures by ordinary telegraphy, using this principle. The suggestion was agreed upon a code of 26 shades, called by a letter of the alphabet. One shade was to be A, the next B, and so on. Then the picture was to be divided up into squares, and the particular shade of each square telegraphed by means of the corresponding letter. The shades thus communicated were to be put together at the receiving end on a prearranged system, and so the picture was to be built up. Given plenty of time, that scheme might be moderately successful, but to get a really good reproduction the subdivision needs to be so minute, and the number of squares therefore so immense, that it would be quicker to send the picture by train than to telegraph it by such laborious means. In a fairly coarse half-tone block the squares are, say, 2500 to the square inch. That number of letters would therefore have to be telegraphed for every square inch of picture transmitted, to say nothing of the difficulty of building up a picture of such great number of parts and giving to each the desired shade. That idea, abortive though it is in its crude form, illustrates very clearly the fundamental principle on which this work is done. The problem is really to devise a machine which will do the same thing rapidly and automatically divide up the original into a large number of squares, and then send an electric current to represent each square, such current by its strength to indicate the shade of the square, and finally a similar instrument is needed to act as receiver, and to reproduce those squares in the proper order, giving to each its correct shade. In practicality, all of them, the mechanism is rotary, the original being placed upon a drum which turns round under a stylus, or its equivalent, while the stylus gradually travels along from end to end after the manner of the needle of a phonograph, or else the same result being achieved by the drum itself having an endwise movement as well as a rotative one. The receiving instrument is of similar form, and both must start together, move at the same speed, and indeed preserve a perfect correspondence with each other. If the distance be great between the two, there might be difficulties due to the retardation of the currents passing between them. Electricity does not pass through long wires, particularly if they be under the sea, with anything like the quickness which we are apt to think. Over a short line and under favourable circumstances, the receipt of a telegraph signal at the farther end is practically instantaneous, but on long lines, and under certain conditions, that is far from being the case. Then something has to be done to quicken the action of the current, or else the receiving drum must be made to lag behind the sending drum by the requisite amount. In some cases, too, the transmitting apparatus loses a little time in sending off the currents, and that, too, has to be allowed for, so that, all things considered, the reader will see that the successful solution of the problem is hedged about with many subtle difficulties which are probably only appreciated by those who are well acquainted by sad experience with the little vagaries of both electricity and mechanical devices. Neither of them does quite what we want it to do. Each suffers from little faults, which in the case of a delicate problem like this, where a difference of 1/100th of a second would be fatal to success, introduce difficulties almost insuperable. To transmit line drawings, Professor Korn uses a sending instrument very like that of Caselli. The picture is placed, either by hand or photographically, upon a sheet of copper foil, which is fixed round the rotating cylinder, the lines being formed of non-conducting material. The foil being electrified and the stylus connected to the line or main wire, currents pass to the farther end just as in the old apparatus. At the receiving end the drum is covered with photographic paper and enclosed in a light, tight box. Through a hole in this box a fine pencil of light passes from a lamp, suitable lenses being used to ensure that the pencil shall have, as it were, a very fine point, producing a very small spot of light upon the paper. If the light remains quite steady, the drum meanwhile rotating, a line will be drawn by it upon the paper which will be visible when the latter is developed. Since the drum not only turns upon its axis, but also moves endwise 1/100th of an inch at every revolution, this line will be a spiral, the turns of which will be 1/100th of an inch apart. Thus the paper will be blacked practically uniformly all over. Should the intensity of the light vary, however, the line at times will be lighter than at others, while should it be cut off altogether for a moment, then there will be a corresponding gap in the line, and it is easy to see that if these lighter parts or gaps occur in the correct places, they will form a picture. In other words, by controlling that light we can build up a picture upon the paper. The question is how to control it. Professor Korn uses a form of the Einthoven galvanometer already described. Instead of the silvered fibre generally employed in this instrument, a silver wire is fitted, the movement of which partly or entirely cuts off the pencil of light. The Korn transmitter for photographs is quite different, although the receiver is practically the same as what has just been described. The basis of it is a peculiar power possessed by the metal selenium when in a certain state. This, like all metals, is a conductor of electricity, but of course offers resistance in some degree. Now the special feature of selenium is that its resistance is reduced if light shine upon it. Suppose then that current be flowing through a mass of selenium, and that the latter be suddenly illuminated brightly, the resistance will at once fall and the current increase. On the other hand, should the light falling upon the selenium diminish, its resistance will increase and the current flowing through it will decrease. In short, given a suitable arrangement, the current flowing in a circuit of which a selenium cell forms a part will increase or decrease with the increase or decrease in the light falling upon the cell. A while ago the papers were telling striking stories of a way by which blind people, so it was said, were to be recompensed for the loss of their sight. A new sense, as it were, was to be given them by which they could hear light, even if they could not see it. All this had reference to this curious property of selenium, as being, of course, an undoubted fact that it will vary an electric current in accordance with the variations in the light, and if that current be led through a telephone receiver, a man, by holding that to his ear, could, in a sense, hear the variations in the light. In the Korn transmitter for photographs, selenium is employed as follows. A transparent photograph is made on a celluloid or gelatine film, and this is fixed upon a glass cylinder mounted as already described. A pencil of light falls upon this in much the same way as in the case of the receiver just described, and as the cylinder revolves, describes a fine spiral line all round and round it. Moreover, the light passes right through the photograph and falls upon a mirror inside, of which it is reflected on to a selenium cell. At every moment, then, the light is falling upon some small part of the photograph, and the amount of it which gets through and ultimately reaches the selenium depends upon the density of that part. Current, meanwhile, is flowing from a battery through the selenium, and thence over the main wire to the distant station. As the light pencil traces its spiral path over the rolled-up photograph, every variation in the density of the picture is reproduced as a variation in the current through the selenium. This, at the remote end, operates the Einthoven galvanometer, the movements of which vary the shade of the spiral line being drawn upon the photographic paper. This process takes place with remarkable celerity, so that in a few minutes the innumerable variations constituting a complete photograph can be transmitted and faithfully recorded at the distant end of the wire. But perhaps the most successful of these methods is that known as the telectrograph. It is surprisingly like the scheme of a Caselli in principle, and forms another example of the fact that good ideas often fail through lack of a proper means to carry them out. Mr. Thorne-Baker, the inventor of the telectrograph, has had at his disposal accumulated stores of knowledge and skill which did not exist in Caselli's time. Consequently, the former has made a brilliant success, where his predecessor produced only an interesting but somewhat ineffective attempt. Reference has been made already to the half-ton blocks wherein a host of small dots of varying sizes make up a picture. Now, instead of parallel rows of dots, parallel lines of varying thicknesses will give very much the same result. The former are made by photographing the picture through a sheet of glass ruled with two sets of lines at right angles to each other. The latter can be made by using a screen with lines one way only instead of 2 ways. It is therefore quite easy for a blockmaker to produce a process block wherein lines are used instead of dots. For this particular purpose, however, it is not an ordinary block that is needed, although it is in essentials very similar. The picture to be transmitted is photographed through a screen as if a half-tone block were to be made. The negative so obtained is then printed by the gum process onto a sheet of soft lead, and after washing, the picture remains upon the lead in the form of lines of insoluble gum on a background of bare lead. A squeeze in a press drives the gum into the lead, and so gives the whole sheet a smooth surface over which a stylus will ride easily, but which is, nevertheless, made up of conductive parts and non-conductive parts, the latter forming the picture. The lead sheet is then put upon a revolving cylinder and turned under a moving stylus in the manner with which we are now familiar. The sheet is placed with the lines lengthwise of the cylinder so that the current passes to the stylus, except as it passes over the breadth of the lines, and so similar lines are built up at the distant ends. The receiving mechanism is of the electrochemical type which Kasper used. The current passes from the receiving stylus to the paper, and there makes its mark in a way that will be understood from the description of the earlier apparatus. The supreme advantage of this method of working over that of Professor Korn is that the operator can see what he is doing. To obtain good results, a number of electrical adjustments have to be made, and whether he has got them right or wrong can be seen as soon as the picture begins to grow upon the receiving paper. If a little readjustment be needed, the operator sees it and can set things right before the really important part of the picture begins to appear, whereas the Korn apparatus he does not know what is happening at all, since he can see nothing until the picture is finished and the photographic paper has been developed. It will be apparent, too, to anyone who has carefully considered the wireless telegraphy chapters that it ought to be possible to make the sending stylus, or its equivalent, control a wireless transmitter and a wireless receiver to operate the receiving stylus, so as to be able to send pictures by wireless. Experiments to this end have been made with some measures of success, and sooner or later we are almost sure to hear the difficulties, which are by no means small, have been overcome. But we cannot conclude this chapter without a fuller reference to that marvellous invention, the telewriter. In this a man makes a sketch with a pen on a piece of paper, or maybe he writes a message, and simultaneously a pen, hundreds of miles away if need be, does precisely the same thing. The receiving instrument draws the sketch line by line, or it transcribes the message in an actual handwriting of the sender. A little touch, almost weird in its naturalness, is that every now and then the receiving pen leaves the paper and dips itself into a bottle of ink, after which it resumes its work at the very spot where it left off. Now how the complicated lines and curves, the strokes and dots which make up a written language, even the little shakes and deficits which give each man's writing a personality of its own, how all these can be sent over a wire is at first sight very difficult to understand. The inventor of this apparatus has discovered an extremely simple way of doing it. But even he does not attempt to do it with one wire, it should be said, for he uses 2. This is no drawback when, as is often the case, it is used in conjunction with the telephone, for the latter, to be effective, also requires 2 wires. Years ago single wires were employed for telephones, as for telegraphs, the circuit being completed through the earth. But the difficulty arose that every wire through which currents flow is apt to induce currents in neighbouring wires. The induction coil is based upon that fact, and so messages in one wire were overheard on others, or, what was perhaps more annoying still, the dots and dashes passing in a telegraph wire would produce loud noises in a telephone wire that happened to be near. The use of two wires, however, entirely removes that trouble, for the neighbouring current then induces two currents instead of one in each, and it so happens that these are opposed to each other, so that they neutralize each other. So every telephone wire now is double, and therefore is ready, as it were, to have the telewriter fitted to it. But even with two wires the difficulty seems insuperable until we remember that most complex of curves can be resolved in two simple movements. The sending pen, with the original writing or drawing is attached to the junction of two light rods. The farther end of each rod is attached to the end of a light crank, fixed so that it can rotate or oscillate after the manner of cranks, in the plane of the desk upon which the paper lies. All the joints mentioned are of the hinged nature, so that as the pen is moved about, the rods turn, more or less, one way or the other, the two cranks. This simple mechanism, it will be observed, carries out very effectively the principle just mentioned, for it resolves the motion of the pen, no matter how complicated it may be, into a simple rotating motion of the two cranks. So the cranks turn this way or that, as the draughtsman makes his picture, and it is very easy to arrange that their movement shall vary the strength of two electric currents, whereby we obtain electric currents varying in accordance with the movement of the cranks. This is done by making each crank operate a variable resistance or rheostat. When in its extreme position on one side, the crank permits current to flow freely, but as it moves over to the other extreme position, the resistance in the path of the current is increased. Such an arrangement is a common feature in its electrical apparatus. So current from a battery flows to the two wires leading to the distant station, each passing through the rheostat connected to one of the cranks. We may think of the rheostats as taps which can be turned on or off by the actions of the cranks. Let us imagine that crank A is in the position when the current flows freely, when the electrical tap is fully open. Then a strong current will flow along wire A, returning to the sending battery via the earth. As that crank is moved, the current will gradually be reduced until, if moved right over to the other extreme, the current will be at its feeblest. Arrived at the other end, this current passes to a device which we may describe simply as a magnet, so arranged that its action pulls round a crank against the restraining action of a spring. Now the stronger the current, the more does the magnet pull, and the farther does the receiving crank turn. The sending crank varies the resistance. The resistant varies the current. The current varies the strength of the receiving magnet, and the magnet varies the position of the receiving crank. Properly adjusted, then, the motion of the crank at the one end is communicated through that long chain of causes and effects, until at last it is repeated exactly by the movement of the crank at the other end. This same thing occurs simultaneously over each of the two wires, crank A at the sending end communicating over wire A to crank A at the other end, while crank B communicates its motion over wire B to the other crank B. Each sending crank is closely imitated in its every action by the corresponding one at the distant station. The two receiving cranks are connected by light rods to the receiving pen in precisely the same way that the sending pen is connected. Consequently, not only are the separate movements of the two cranks repeated at the remote station, but the complex movements of the sending pen, which gave rise to the action of the cranks, are also conveyed to, and repeated by, the recording pen. The movements of the first pen are resolved into rotating motions by the two cranks. These are transferred to the other cranks, and their movements are in turn converted back into the written curves. Thus, as the pen in the artist's hand draws his sketch, so does the automatic hand at the other place. It may be at a great distance, repeat faithfully his work, and the sketch grows line by line simultaneously at both ends. There is no space here to detail how, by another current superposed upon those referred to already, the receiving pen is made to dip itself periodically into the inkwell at the will of the sender. By a cunning use of alternating current this is done without any way interfering with the action of the cranks as described above. But of course there is severe limitation to the usefulness of this machine, inasmuch as the drawing has been made at the time of transmission, and it can only be put on a wire by the hand of the artist himself. End of section 14. Recording by Lynda Neilson, Vancouver, BC.